This is browser.
F11 is maybe.
It says I have a problem sharing. Can you see my screen?
Yes, we can use your screen, but it's a little bit small. Maybe you make zoom in.
Can you see the screen? No.
We can see your screen.
Okay. Let me try again.
Okay. Maybe you can close and rearrange one more time.
Can you see my screen?
Yes, now it's very well.
Oh, you can see it. Okay, very good.
Yes. Okay, it's time to open our last day, and then let me introduce you. Hello everyone, welcome to our last day of the webinar. Dear ladies and gentlemen, today our last day, and our program is going to start with our invited speaker, Professor Mok, with the presentation entitled by Holomorphic Isometries of the Poincare disk. He is attending from Hong Kong. I would like to welcome to him for making his presentation. Professor Mok.
Thank you. Yes. So let me start. Okay, so let me explain a bit about the context of the lecture. First of all, I'd like to thank the organizers for inviting me to this conference or this webinar. I am by training a complex analyst and a differential geometer. So the Poincare disk is something that everybody knows, and I choose this topic because it's a subject in the complex differential geometry, but it has applications to other areas, especially to arithmetic geometry or problems in number theory, which have a geometric interpretation. Okay, so let me start with the objects of my study. So I do several complex variable. So I work on domains. These are irreducible bounded symmetric domains. They are realizations of Riemannian symmetric spaces of the non-compact type and of the Hermitian type. So they have Hermitian metrics. They are complex manifolds. So these domains are extremely important. Not just these irreducible ones. Sometimes you take products of them and you look at lattices in them. Lattices such as SP and NZ, for instance, in the case of type 3 domain, the quotient with respect to these lattices give you the moduli spaces. Like the example, this is actually isomorphic to the Ziegel upper half plane. So these are matrices, symmetric matrices whose imaginary parts are positive, and the quotient by SP and Z parameterizes what we call the polarized abelian varieties. The case of one dimension gives you the moduli space of elliptic curves. Okay. Now, what are the tools available for studying these? Of course, you have the Bergman metric. The Bergman metric is the same as the invariant complete Kähler metric, the canonical invariant complete Kähler metric up to a constant. And so I'm listing the kernels, the Bergman kernels of these classical domains. The Bergman kernels are important because after taking the log of the k omega z, you get a potential for the Bergman metric. So when you take the complex Hessian, you get the complete Kähler metric, which is the gives you the symmetric structure. So one importance of the Bergman metric is the following. So I'm studying here the holomorphic isometries, or rather germs of holomorphic isometry. So you have here two different bounded symmetric domains of possibly different dimensions, and you have a germ of map. So you can fix a base point, and you look at a map, a holomorphic map that is defined in some small neighborhood of X0, which is an isometry between the Bergman matrix up to a certain scalar constant. And now you suppose the Bergman kernels to be of a special type, namely that they are rational functions in Z and W bar here, for instance. And if you do that, what you get is, okay, so if you make the assumption that they extend to rational functions. So these are satisfied in the case of a bounded symmetric domain, as I've shown in the classical cases, and even in the exceptional cases, this statement is correct. So it's the Bergman kernels are special. They are rational functions in Z and W bar. Then the statement that I proved in 2012 in Journal of European Mathematical Society says the following. If you just have a germ of holomorphic map, which is a holomorphic isometry, up to a constant, then this germ actually has properties of analytic continuation. It would extend not just to, the graph will extend not just to D cross omega, but actually beyond it. D is realized as a standard way in Cn, and omega, again, it's in a standard way in C capital N. And so you have this extension. I should say that within D cross omega, this was already known to Calabi. So what I did was actually to prove that this extends beyond the boundary, all the way to Cn cross Cn. And the statement is the following. Assume these are complete Kähler manifolds, which is the case when omega and D are bounded symmetric domain. Then the graph extends to the holomorphic isometric embedding. And if furthermore, this is also complete, the D is complete, then F is a proper map. So it's a proper holomorphic isometry. Now, of course, there are standard ways like the geodesic embeddings, but it was not known for some time whether there exists holomorphic isometries which are not standard. So I gave the first examples. So you take a unit disk. A unit disk is isometric, is isomorphic to the upper half plane. And so I take the upper half plane, and I take a map from the upper half plane to a product of upper half plane as follows. For a point in the upper half plane, you take its piece root, and then you multiply by some primitive root of p root of unity. So precisely this number, and you multiply, and you get a map with p components. And the statement, this is called a piece root map, and the statement is that this is a holomorphic isometric embedding. So the way to prove it is actually just to check that the pullback of the potential function is actually the potential function of the unit disk up to a constant, a precise constant. So why did I come up with this map? I was exploring the asymptotic behavior of any holomorphic isometry that could exist, and I saw that maybe there's a chance of getting an example by taking the piece root map, and it turns out to be the case. Now, it is very difficult problem to classify all holomorphic isometries between two spaces. From the unit disk into the polydisk, for instance. It seems to be the simplest case possible, but then the classification is extremely difficult. There's a working hypothesis. I wouldn't say this is a conjecture. In that all structural theorem that have been proved, in the case of delta into delta to the power R, comes from the piece root map up to some congruence and composition and so on. Now, this is of course not known, but there are some low dimensional results obtained by in 2011 and also by Chen in 2016. In particular, they characterize the piece root map. So if you add some additional property, you can say that that map must be the piece root map. And then they classify all holomorphic isometries of delta into polydisk of dimension less than or equal to 4. Now, but there are other examples. So for instance, one can construct one from the disk into the zero upper half plane of genus 3. In this case, this is just by hand. You write down something that involves the cube root of unity, and you check that the potential functions are respected. I should say that this map cannot possibly be obtained by congruence by composing the piece width map and embedding of the polydisk into the zero upper half plane of genus 3. So this is a different map from those that could be obtained by the piece width map and together with certain standard operations. Now, then it was unknown for some time whether there are holomorphic isometric embeddings which are not totally geodesic for high dimensional balls. Now, I should say that this is the next interesting case, because it is known that if I replace this by a bound symmetric domain irreducible of higher rank, then one knows from my earlier work on Hermitian metric rigidity going back to 1987 or sometime around that, that this map must be totally geodesic if you replace this by something of rank at least 2 and irreducible. So in 2016, I got an example which turns out to be very important for other reasons, which I will explain. So denote by this the collection of all directions where there exists a rational curve. So what is X? I can, if I take omega, omega has a compact dual. For instance, type 1 domain can be embedded into a complex Grassmannian. So you take this guy inside this X, omega is inside X, and then the X is Hermitian symmetric space of the compact type. So there's a notion of minimal rational curves, or rational curves of degree 1 under the standard embedding, the minimal embedding, for instance, the Krieger embedding of the Grassmannian. And you just collect all those directions through which you can pass a rational curve of degree 1 or minimal rational curve. And this variety, which is very important in the theory I had developed with Jimo Huang of Kias, Korea, this guy is the variety of minimal rational tangents. It dictates to a large extent the geometry of the manifold X. So it is a new kind of geometry. Now you take P to be the dimension of this variety of minimal rational tangents, and then define this variety, which is a collection of all lines passing through X, or minimal rational curve passing through X, and you get a variety of dimension P plus 1, because you have P dimensional family and each member is a rational curve. Then the statement is what I obtained in actually 2016 actually, that if you take omega to be an irreducible bound symmetric domain of rank at least 2, embedded into this compact dual Hermitian symmetric space, X like type 1 domain into a Grassmannian, or you can embed the zero upper plane into the Lagrangian Grassmannian. You take VQ to be intersection of this cone with omega, and this is the collection of minimal disks. The intersection of a minimal rational curve with omega is a minimal disk. So this is again a P plus 1 dimensional space. Then VQ is actually the holomorphic isometric embedding of a high dimensional ball. So this is the image of this embedding. And the reason why that is the case, because the VQ has some symmetry, or some group acting, some non-compact acting on it, preserving it, and then the behavior of this VQ can be, a geometric property of VQ can be identified as the asymptotic geometry of itself, and one can check it asymptotically must be of constant holomorphic sectional curvature, and that implies that this is the ball. So well, actually 1 year later, there was an article that I published with Chen in Mathematische Zeitschrift, in which we prove the following result. In the case of type 4 domain, these are the simplest domains that are closest to the ball. We were able to classify all holomorphic isometric embeddings of the ball into it. The classification gives examples with isolated singularity at the boundary, this VQ, as well as smooth examples. So this is a case where the classification can be done. In case of K equal to n-1, that's the maximal ball that can be embedded. The result was also obtained by 2 other groups of people. But in this result, we were able to do it for all dimensions. Okay. Now then I can come to something, the central results of this talk. We were studying, actually, we can start by looking at this. So this is a theorem that was just appeared as in a Journal of Differential Geometry in January. So you take a map from delta into omega. So this is a holomorphic isometry with isometric constant lambda, scaling constant lambda. And this is a standard embedding, just the domains I wrote. Then the statement is that F is asymptotically total geodesic at a general boundary point. So this is a study of the boundary behavior. Now, what one proves is actually a substatement stronger than this. Namely, we can just take any map, any holomorphic map that is defined up to the boundary of the disk, or a portion of the boundary of the disk, the boundary circle. And you make the assumption that the boundary circle is mapped into the boundary of the boundary symmetric domain. Then the statement is that the asymptotic behavior, namely the absolute value or the norm of the second fundamental form, will go to 0 as the point approaches a boundary point, a point on the boundary circle, if you choose this generically. Now, in the case of holomorphic isometric embedding of the Poincare disk, by my theorem in 2012, this must be algebraic, and therefore you do have something going to the boundary. And then we also know that this must be a proper map, so the boundary goes to the boundary. So this theorem therefore applies. So the question I want to explain heuristically why one should expect that the Poincare disk would be asymptotically geodesic. So the heuristics is the following. There's the argument used in several complex variable called the rescaling. The thing is that we're talking about domains with a lot of symmetries. So non-compact group, a semi-simple Lie group acting transitively on the domains. And therefore, once you have a map, you can compose with the automorphisms sort of to anchor it. So you might take a sequence of points going to a boundary and pull back the point to a center of the disk and the center of omega. So you do the composition. And then you take limits. There's some kind of normal family argument. You can take the limit. The limit will give you a holomorphic isometric embedding as well. But this holomorphic isometric embedding reflects the asymptotic behavior of the original holomorphic isometric embedding. And therefore, what one wants to do is, after rescaling, one gets non-standard holomorphic isometry, which is close to being an equivariant holomorphic isometric embedding as possible. And you want to prove then finally that this equivariant holomorphic isometric embedding must be totally geodesic. So that is the line of argument. I put it another way, assuming that it is not the asymptotically total geodesic, you would be able to pull back and take limits to get something like an equivariant holomorphic isometric embedding, which is not totally geodesic, but whose second fundamental form is in some sense the same at every point. So the norm of the second fundamental form would be constant. You can require more. You just apply the rescaling map, rescaling argument several times. Now, then there is a difficulty of this type of argument by contradiction. This type of argument by contradiction must, if it is to succeed, one must be using some properties of omega. So the first property of omega would be that this is of negative Ricci curvature, for instance. Because in the case of positive curvature, it is possible for the Riemann sphere to be with Gaussian curvature plus 1 to be embedded into Pn, which is not totally geodesic, and this is given by the Veronese embedding. Or you can have the lots of other examples, like the Sager embedding, Plug embedding, etc. So therefore, to solve it, we must make use of negative curvature. How do we make use of the negative curvature? We make use of the fact that actually of differential equations. So we first consider tube domains. What are tube domains? If you consider those given by matrices, these are the square matrices. The Lie spheres, the type 4 domains, are always tube domains also. The Siegel domains, the Siegel upper half plane is a type domain, etc. So these are important domains. So we get a contradiction by using a differential equation. This is a second order differential equation called the Poincare-Lalonde equation, which I will explain. Then we so we solve the problem for the tube domain case. Then we solve a non-equidimensional integrability problem in the following way. Suppose I'm in a general irreducible arithmetic domain, and you get an example which is a sort of non-standard map, which looks like a equivariant. Then you want to insert some domain inside it, which is a tube domain, and in such a way that actually the Poincare disk in some sense is embedded in a maximal way. So okay, so here's a statement of the theorem. By rescaling argument, it is possible to get a holomorphic isometric embedding. So starting with F0, and you compose with automorphisms and take limits with the following property. All the tangent lines are equivalent under automorphism omega. So imagine that you have a disk inside a high-dimensional manifold, might be a high-rank bound symmetric domain. The isotropic group does not act transitively on the sphere bundle, but nonetheless there are some normal form arguments. What one can get is actually that after composing and taking limits, you can arrange it such that all the tangent lines, or you can say a unit tangent vectors at each point of the embedded Poincare disk, are equivalent to each other under the automorphism of omega. So in some sense, it looks like homogeneous. We don't prove that it is homogeneous. We don't need that much, but we need that it is homogeneous. They're equivalent under the action of the automorphism group. Okay, so here is the argument in the case of the tube domain. Now, in the tube domain, and suppose you have a case where the embedded Poincare disk give you tangent vectors which are general tangent vectors. What is a general tangent vector? If you take symmetric matrices or just matrices of order n by n, then you can take the determinant. A vector is said to be general if the determinant is non-zero. So most vectors have non-zero tangent vectors. So suppose you, after this renormalizing argument, get a minimal disk such that at each point it is a general vector. So what does that mean? Well, you look at omega, and on omega you can take the tangent bundle. You can projectivize it. This is a complex manifold. And there is a certain cycle, a hypersurface inside here, which is defined by those vectors with vanishing determinant. So this is the cycle. This is a hypersurface. And this hypersurfaces can be identified, well, the cohomology class of this is given by two standard line bundles. So this is a tautological line bundle, and this is a line bundle on the base omega, which is dual to the compact to the O1 on the compact dual. So for instance, the Plug embedding, then you have O1 because Plug embedding gives it inside Pn, and Pn you have O1. And by duality theory, you will have an omega some line bundle dual to it, and then this hypersurface gives you this guy. Now the assumption that I have a certain disk assess that Poincare disk means that I can lift the pointer disk to the projectivized tangent bundle, and in that case, it will have empty intersection with this hypersurface. This hypersurface is defined by the vanishing of the determinant. And on the other hand, my example is one with the non-vanishing determinant, and therefore they have empty intersection. So this is the Poincare-Lelong equation. So there are certain Hermitian metric, certain invariant metric on the line bundle, and the lifting of the pointer disk gives you a section, and you restrict a canonical section on it. This canonical section is going to be constant because of the equivalence of the tangent vectors, and therefore this psi is equal to 0. On the right-hand side, you get curvature, and the curvature is given by this, because this guy is isomorphic to this line bundle, and you get this curvature. Now, this psi is equal to 0, and this psi, when you restrict to the lifted Poincare disk, has to vanish at every point. And a standard and straightforward computation gives you actually that you have this can only occur if the second fundamental form is equal to 0, and if all vectors are tangent to have Gaussian curvature minus 2 over R. So this is what we need. So we have the vanishing of sigma. Okay, this I wouldn't explain this very much because I just said that it could be settled, could be solved in a special case, and then the general case can be reduced to the special case by solving some integrability problem. So my omega might not be a tube domain, or even if it is a tube domain, my Z, this is a local holomorphic curve, might not be of the tangent vector. The tangent vector might be smaller than the maximal. So the determinant might still vanish on Z, although this is a tube domain. So in that case, what one does is to insert in another tube domain so that Z would have maximal rank in this omega prime. And this is done by solving some integrability problem, which is not easy. But in any case, by the sort of classical arguments. The other thing is that if you get maximal type, and then it's not a tube domain, then one can do the same by inserting Z into some tube domain inside omega. So this would be another omega prime inside. So there exists an omega prime, which is a tube domain. Okay, so the importance of this type of argument or this type of result is their application to other problems from differential geometry, but also from arithmetic geometry. So the Clausel, my former colleague in L'Orsay in France, had this result in the classical case. You take D and omega to be bounded symmetric domain, and you assume them to be of classical type. So each irreducible factor is of classical type. Then Clausel proved in 2007 that actually any equivariant holomorphic map is necessarily totally geodesic. And the general case was proven by Chen and myself by a completely different method. So Clausel's method is Lie theoretic, having to do with risk systems and so on. And our argument is completely different geometric. The point is that this works also for the exceptional domains. Okay, now you can reduce this problem. D and omega are bounded symmetric domains. D contains a lot of totally geodesic copies of the Poincare disk. You can restrict to this Poincare disk delta inside D, apply the result that I had with Chen Mok about the asymptotic total geodesic. Now, when you have something that's equivariant and it's asymptotically total geodesic, means that it is actually totally geodesic because the properties are homogeneous through the disk. So asymptotic is equal to 0, so it actually is equal to 0 everywhere. And then you can restrict to this disk, get the total geodesic of the restricted map, but then you have lots of holomorphic isometric copies of Poincare disks of different type. And by some polarization argument, you get that actually this is totally geodesic. Okay, now comes a result. This goes to a group of researchers working on what is called bioalgebraic geometry. And what they were looking at typically is the following picture. You have a biosymmetric domain and you have the uniformization map. So you have a quotient, you have the uniformization map. Now, the biosymmetric domain itself has an algebraic structure. You declare a variety on omega, an irreducible complex analytic variety on omega, to be algebraic if it is an irreducible component of the intersection of an algebraic variety of Cn with the omega. So this is not just regarded as a complex manifold, but it's embedded inside Cn in a specific way. The boundary is in some sense semi-algebraic. The boundary can be defined by algebraic equations, and the domain can be defined by algebraic inequalities. So then the statement is that of Ulmo Yafayev in 2011 stated that this is actually, if you have Z being algebraic, then quotient is also being algebraic, then Z in omega must be totally geodesic. But the important assumption here is that they assume that X gamma is an arithmetic motion. So you quotient out by gamma. Now, of course, by Margulis superrigidity theorem, in case of higher rank, if you take a lattice, then this is always going to be arithmetic, but it is not the case with the ball. So their proof relies on some results from André Delin about the representation of the fundamental group. This is called monodromy results. And this in turn depends on Hot structure and mixed Hot structures. So without the arithmeticity assumption, such results are not known to hold. Okay, now, so this is a result that Chen and myself obtained in 22 as a consequence of the earlier stated results about the total asymptotic total geodesy. It says the following: if you take gamma as omega mod gamma, and let Y be an irreducible subvariety. Okay, and assume that this Y is actually compact. So if it's compact, then this is actually projective. Then the statement is that this Z is totally geodesic. Okay, you assume Z to be algebraic, you assume the quotient to be algebraic. But actually, our result is stronger. It is the following statement. So this is the analog in the compact case. So in the case where Y is compact of Ulmo Yafayev. So we haven't proven the finite volume case yet, but we make no assumption on the lattice gamma. The gamma can be non-arithmetic. So that's the difference. But actually, the statement that we can prove is the following. If you take Z to be stabilized by a certain discrete subgroup inside the morphism of omega, such that the quotient is compact, then already Z in omega is totally geodesic. Now you see that this gamma check stabilizes Z, but of course it also acts on omega. And you can also define omega modulo gamma check. And this is in general a quotient of infinite volume. So our result says that this type of bioalgebraicity results still hold in the projective case for a projective variety of a quotient of omega, which might be of infinite volume. So this is not even a lattice. So that's the difference. The argument that we gave is from complex analysis, and the important component comes from the maximum principle. It's the maximum principle for so-called weakly polyharmonic function. Okay, so this is the proposition. So since this is an algebraic set, and you have gamma check, which is infinite acting on Z, so there must be some algebraic group acting on Z. So it has a certain degree of symmetry or homogeneity. The statement we could prove that this Z is actually quite big. I'm sorry, that this group H0 is actually quite big. A priori, we only know that it must be at least one dimensional. But actually, we can prove the following. If you take this group, H0, which stabilizes Z, it has this complexification. So G0 is the automorphism group of omega, G is its complexification, so X on the compact dual. And you can also complexify H0 and get H here. So in some sense, this Z is pseudo the homogeneous under this group H. What do I mean by pseudo homogeneous? This H actually, of course, does not preserve Z itself. It preserves only its completion. So that Z is contained inside a project variety Z hat. And H keeps Z hat invariant. It does not keep in general Z invariant, but H0 keeps Z invariant. So you get a sort of homogeneous manifold, and this Z is the intersection of a homogeneous manifold with omega. So here's the argument. So I am repeating just in words. So suppose the proposition fails. Okay. So there would exist some project variety contains Z such that E contains the intersection of H with Z. One is afraid that this X might be too small. Now, so there's this variety E which can be completed to E hat in the compact dual. And so this can be defined by a system of a set of polynomials, this common zero set of a set of polynomials. Now we want to derive a contradiction. You take phi Z to be the supremum of the value of these polynomials under the action of gamma. So gamma are elements of gamma check. So this is an infinite group. And the supremum of this would be finite because the function actually is bounded on omega. So, and it's not just finite, it's even a very nice function because you have Cauchy estimates. So this is a uniformly Lipschitz family on omega on any compact sets. And therefore you can take the supremum, and this is even a Lipschitz function. In particular, this phi is a continuous function. Then phi is a bounded Poisson harmonic function on omega, which is invariant over the action of gamma check. So you restrict to that. You have that this is equal to 0 whenever it lies on E. But then this function, because of invariance, descends to a function that is inside the function on the quotient. So hence we obtain by descent a non-constant bounded Poisson harmonic function small phi on Y check. And since it's bounded and it is Poisson harmonic, it can be extended to a compactification. So by Riemann extension theorem, this can be extended to this compactification, and this is projective. You have a Poisson harmonic function, the function must be constant. And this is a contradiction because by construction, it is not constant. It is equal to 0 along the quotient of E, but then it is non-zero elsewhere. But at least at elsewhere actually. So this is the argument that gives the, after some refinement of the argument, which shows that this this orbit under the complex group essentially covers Z check. It covers, by taking topological closure of this, you would get Z check, and that gives you the essential argument. Okay, now in order to apply this to the uniformization theorems, we make use of a result of N. Nadel that goes back to 1990. If you take a compact Kähler manifold with ample canonical line bundle, and you take this to be a uniformization map, he was studying the automorphism group of uniformization, a universal covering of compact Kähler manifolds with negative first chain class. Then he proved that this is actually a semi-symbolic group without compact factors. We can take this Z to be inside omega by replacing omega by some omega prime, the smallest total geodesic complex manifold containing Z. So this is just a reduction, and this is the proposition. The proposition is that we were looking at this group H0. We proved that this H0 is, using the argument of Nadel, essentially just paraphrasing Alan Nadel, you can see that this group as a subgroup of automorphism omega is a semi-symbolic group without compact factors. And what one want to prove is we only prove pseudo-homogeneity. What we need is actually homogeneity. So H0 is not known to act transitively on Z. Only its complexification acts pseudo-transitively on Z. So what one wants is more. So now we want to study this group, at least from Ritos theorem or slight modification of this. This is a semi-simple Lie group. Now, since it's a semi-simple Lie group, it has a certain representation, a discrete representation into G0, the automorphism group of omega. And therefore, you can get a map into this gadget. L is the maximal complex subgroup. So H0 L is the maximal complex subgroup. And so you get a map from F into this. Now, then you already get two maps. One map is the original inclusion map of Y into the quotient of omega by gamma check. You get another map by just making use of a semi-simplicity and passing to the compact quotient, maximal compact subgroup. So you get a map. These two maps are a priori different maps. And what one can prove is the following. Yeah, so you can realize this map by making use of the fact that omega is a Gardner manifold. Okay, so then you get a map from Y check into S gamma check. This is a real manifold. This is a real manifold, and this is a complex manifold. So you have two K pi ones, and one is the inclusion map, and the other is obtained from the Ritos theorem, and they are homotopic to each other. It's the same representation. And now you can do integration. There's a certain Kähler form, which is the Kähler-Einstein metric, and then you can do the integration. By homotopy, you pull back by either the inclusion map or the constructed map F, and this would be equal. On the other hand, on the one hand, this guy is the volume of Y check, whereas this guy must be equal to 0 unless the dimension is maximal. The contradiction will arise if we had a strict inequality of dimensions. So this comparison about the dimensions, one is Y check, the original quotient, and this is coming from the maximum complex subgroup. You have inequality by construction, but actually they must be equality. They must obey an equality due to the fact that the integral of certain MM forms must be equal to each other, and one would be vanishing, the other would be non-vanishing, unless you have equality of the inner dimensions. What one has proven is therefore that this Z is not just pseudo-homogeneous, but it's homogeneous under H0, and H0 is of Hermitian type. Now you can apply my result with Chen to get the following, that this is the image of an equivariant holomorphic map between bounded symmetric domains, and then by Chen mock, we get that this is totally geodesic. So this is a path which allows one to prove the bioalgebraicity result, even for a projective quotient manifold lying inside an X gamma, which X gamma check, which might be of infinite volume. So here comes the end of my talk. Thank you for your attention.
Thank you very much, Professor. It was a very exceptionally good talk. Let me ask the attendees about the question or comments. If you have any comments, you can use the question and answer part in the bottom of the screen, and you can write from here. I'm checking that. It seems there is no question. Then
Maybe I can make some comments. I can make some comments about the end of the.
Please.
Okay. Okay. So the reason for this. Okay. So these are mathematicians who have training in number theory, and in algebraic geometry, and their interest was to study what is called bioalgebraic geometry. The reason for the importance of this special manifold is the following. They are this is the first step towards what one calls functional transcendence theory. Functional transcendence theory, I can state one result here. So suppose you take this x gamma equal omega mod gamma, and you take this y, okay? Now, so there is a z inside omega. So z is algebraic. This is a very special case when you take the image of z under the map pi, this uniformization map. The image would be y, and this is projective, okay? Or this is quasi-projective in general. What they were interested in is much beyond this. So if you take this z, this is algebraic, you take its image, the pi of z inside x gamma, so you get some set inside gamma. So this is quasi-projective, but this image inside x gamma is actually could be very chaotic. And what you can do is to take the Sarisi closure. If you take the Sarisi closure, you get something projective. And the statement in what one calls the Ax-Lindemann conjecture was to say that when you take the Sarisi closure of the image of Z under pi, that should be a totally geodesic subset. Unless, it should be a totally geodesic subset, a proper totally geodesic subset, unless you have some very special case which can be identified. So this is the so-called Ax-Lindemann conjecture, and this Ax-Lindemann conjecture is an essential result in the functional transcendent theory, on which a lot of number theorists, algebraic geometers, and logicians were working. And actually, beyond that, we also you can also go beyond that to the so-called Ax-Shanuel conjecture, so which is an analog of results in transcendental number theory to the function field. And recently, I have collaborated with Piller and Zimmermann to solve the so-called Ax-Shanuel conjecture for in functional transcendent theory for bounded symmetric domain omega. And the proof is a combination of the methods in logic and the method of complex general geometry and algebraic geometry that I had. So let me just conclude with this remark.
Thank you very much again, Professor. It seems there is no question or comments. So let me thanks one more time on behalf of our committee and participants. It was a very good talk.
It was my pleasure. Thank you for the invitation.
Thank you very much. We are very glad to see you here.
Thank you. Bye-bye.
Bye. Dear participants, now we are going to continue our program at 8 o'clock with the regular session. Now we are in a little break. See you soon. Hello again. Welcome to the first regular session of the last day of the webinar. Dear participants, now we are starting with the first presenter of our schedule, Sayo Ebijos from India. Professor Ebijos, can you hear me?
Yeah, I can hear you. I think I'm audible, right?
Yes. Welcome to
Okay.
our webinar. If you are ready, you can share your screen.
Okay, sure.
Yes, now we can see your screen. Can you make it full screen?
Yeah, I think it's fine. Right?
Thank you very much. Now, if
Okay,
you are
okay.
ready, you can start.
Okay. First of all, thank you so much for the organizing committee for this an opportunity for me. I'm Sayuj Epijals. I'm a great breakout graduate fellow, Department of Mathematics, doing research under the guidance of Dr. Raja, and I'm a Center for Mathematics, Salakappa University, Tamil Nadu, India. So I'm going to present a topic on stability analysis and comparative study on different eco-epidemiological models, the state structure for prey and predator concerning the impulsive control. So this is my outline of my presentation. So first is about the introduction and some milestone regarding to ecology and epidemiology. So then I goes to the different eco-epidemiological model for the pest control, and finally discussion and comparative study, and about some conclusion and the future scope also. So as we know that the mathematical models have plenty of application of real world problems, and also the population dynamical systems are often to subject to the environmental issues. So mathematical model can help to solve the real life problems. So here I am discussing about the eco-epidemiological models. That is the combination of ecology and epidemiology. So before starting the main thing, so a brief intro about the modeling and mathematical models. So model is a representation of a given system or who can conceive of. So everyone is familiar with the model. So here we are talking about the mathematical model. So the process of developing a model, that is called the modeling. And here I'm discussing about the mathematical model. So mathematical models, nothing but so is a process of constructing a mathematical object such as system of equations, algorithms, geometrical structure, such as. So when we go to mathematical model, the important question is that why these mathematical models are studying. So it helps to gain understanding the thing, to predict or simulate, to optimize the performance. So this is the main ultimate aim of the mathematical model. So we can, when we go through the mathematical model, we can see that some of the problems related to the prediction, some of them related to the control strategies, the importance of control strategies, that many things related to that. So that is the main advantages of mathematical models. So this is just a schematic diagram for mathematical models. So we have a real world problem that converted to working model. After that, we represent it to mathematics. So it's maybe mathematics or algebra, whatever it is. So we can represent it in mathematical manner. So next is about the computational thing or theoretical results. We are simulate or we are confirm using the something technique, and finally with conclusion. If it is okay, we will move to the real world problem. So as we know that last 1 year, this conference also the after effect of COVID-19. Otherwise, it would be a offline mode. So this online only because of COVID-19. So we can see that there are many papers and many research are going on or related to the COVID-19 and the pandemic things also. So some of the problem related to the what happened after the a few months later, what is the transmission rate and how much people affected, and like these manner of studies, and some of the research going on, the advantages of or what effect of lockdown such as. So if is it lockdown is effective or not, and how many days we will need for the lockdown, like that way. So some of them is related to the vaccination, and is it effective or not, like that. So different mathematical model we can see that different of aspects. And also we can see that there are fractional differential equations are different models are creating related to Caputo, Atacana Bellano, ABC derivative, RL derivative. We can see different mathematical models related to the things also. So we can see that if a mathematical model, a formula, there is an interaction between each other. When we go to the epidemiological models, we can see that there is an infected person and there is a susceptible person. So there is an interaction between each other. So for this interaction, we formulate a mathematical models and we analyze the interaction and infecting rate and all the things related to that. So when we go to the plant-based natural enemy for in the school level also, we study these things like that food chain system. So we can see that each thing is connected. One is the food of another, another is the food of another, like that way. Here also we connected to the plant-based natural enemy models, these interactions. So these are some milestones of ecology and epidemiological models, starting with the predictive prey model from Dr. Walter in 1925 and Hussing et al. In 1993 et al. And food chain model from Payne and Paul in 1991, Mandel in 2010 and more. And epidemiological model from Hammer, Rose, Spore and more, and eco-epidemiological model from Hayden and Friedman and Kung from 1996 and CEO from 2001 and many more. We can see that in recently also there are many research related to eco-epidemiological model, because that the economy is also down due to the COVID-19 and this type of pandemic. So, and also the pest attack is one of the major problem in biological sector. And for solving this type of problem, the farmers are using the pesticides regularly. These type of the pesticides is badly affect your economical and ecological system. So that's why there are many research going on ecology and epidemiology, because there are many mutation happening in pest also. So we generalize those things, and we further move to the different stage structures of prey and predator also. So we investigate how this transmission, how with the interaction with them. So actually, these are the main outcome of my research. So first is about that this manuscript or this presentation is mainly deals with the effectiveness of things, and we different comparative study of 4 different models. And we can see that there are few work related to eco-epidemiological models, and particularly the stage structures. So when we go to the agriculture sector, we can see that there are target pests and not target pests. Some of the pests are there are also friendly for the crop also. Some of them are not friendly. So we can say that there are target and non-target pests. So in this paper, I'm focusing the influence of the target in special consideration to these 2 things, the target and non-target. And also I'm using different controls. So these controls, how influencing the stability and like that way. So I'm considering 4 different models like that: plant, pest, and natural enemy models. In additional, the pest is divided into 2 categories: target pest and non-target pest. And also target pest in the first case divided into susceptible and infected. In second model, I divide into susceptible, exposed, and infected. And third way, I divide into the natural enemies as a mature and immature natural enemies. And model 4 is the more generalization of these 3 models, like that: susceptible, immature larva, susceptible, mature adult, and exposed and infected in that way. So the main significance of this work is that the conservation of target pest and interaction with the plant and influence of non-target pest is remarkable. Like that way, we can see that. So the model formation is we can see that there are interaction between each other. So depending on some assumption, we formulate the mathematical models, and there are 2 impulses we are using here. One is infected pest and another is natural enemy. So here I am using the impulsive differential equations. That means that the sudden changes happening at a particular point of time or particular interval of time. At that time, creating differential equation is called the impulsive differential equation. This type of study, the normal differential equation is not enough for finding that thing. So what I did that t not equal to this is t not equal to nd. The system is exist, and t is equal to nd. We produce the impulses like that, the the pesticides and natural enemy, and finding the stabilities like that way. So for proving the stability, we need some lemmas. This lemma prove the boundedness of the things. Next is about we have a solution, and is state p of t, ts of t, tn of t is bounded by g. And also this is the motivation from the Bioalgebraic theory. And here the impulsive system, how the system, it have a periodic solution, that is z cap and cap. And also here we have consider the pest to become extinct. So we will get 2 systems and we find the solutions. And also we consider the plant, it have 2 equilibrium point, one we will find the equilibrium points. So we can see that I'm not going to the proof of this thing, and we can see that this solution is unstable in the plant plus eradication periodic solution as unstable, that is 0, 0, 0, ti and n cap. This is unstable, and 1, 0, 0, because we considering and the stability at the 0 and 1. So we can see that this stable is only if t less than or equal to t max. Here I'm using the Floquet theory. Floquet theory means that we are linear is the we are linearly standard system of equations, and we finding the fundamental metrics, and fundamental metrics together with a period is called the monotony metrics. And also we find the eigenvalue of the monotony matrix. And so all eigenvalue is negative, we can see the system is stable. Another case is unstable. So when we go to corresponding to 1, 0, 0, Ti cap and n cap, we can see that all eigenvalue are negative except 1. We cannot nothing to say about that eigenvalue. So we will find that in which period that eigenvalue is negative. That period is called the T max. So we can say that total eigenvalue is negative in this period. So we can, which means that the best is what stable in this region, the 0 to this period. So we need to reduce this, or we need to produce the impulses in this period. So we can get this idea. So next model is the generalization of first model. We considering the target space of the exposure class. They have some assumptions. So from that we formulate the model, and the same way the impulses are releasing, and we find the stability, and we get the another T max for this model also. And the third model, we considered the stage structure for enemies also, and also we formulate a model, and also we find the T max. So we will get different T max for the different models. And finally, we formulate the most generalized model, and we consider all stage structures of plant and predator, and we will get this is the model for that thing, and this is the impulsive thing in T is equal to NT. We will produce new cap, new 1 cap, new 2 cap, and new 3 cap, and we will find the T max for this thing also. So we can say that system is stable only T max, like that way. So this the comparative study and discussion of this thing. These are the parameter, and we can see that in table 2 says that if all impulses are non-zero value, the first model is 13.52, because we need to 13 week again for the releasing the natural enemy, or the infected pest also. We need to release this thing in the 13th week. And the model 2 says that we need to release the impulses in the same week, because we take in the parameter like that way. In model 3, we need to release the impulses in 12 week. The model 4 says that we need to release the impulses in the 11th week. So 11.8, maybe it should be 12 week, like that way. So we can get the clear picture of the comparative study of the difference model, and when in which week we need to release the control measures, like that way. We can extend these things to different way, and we can take a one agriculture sector, we can consider some paddy field or sugarcane field, like that way, and we can consider what are the pests attacking there, and how we control there, and what are the quantities to in which quantity, and how much quantity need for the releasing the Tmax, like that way. We can investigate different type of things in these studies. And also we must go to the further thing corresponding to the each model, and finding the in this paper mainly focusing on threshold limit for the impulsive period, and must study about that. In one of the control is 0, another is non-zero. What will happen? What the value of Tmax in that way of research in this way. So this is also the way means that we changing the threshold limits. Threshold limit means that the impulsive releasing raising to 0, 0.1, 0.2, 0.3, 0.4, like that way. And we can see is that the period of impulse is also increasing. So if we not releasing the eta 1, it is 8 week we need to releasing those things. Suppose if we are releasing this thing into 0.7, we need 14 weeks, like that way. So we can say that if maybe there is a many reason for that thing. We also COVID-19, there is a lack of many pesticides, so we can extend those period for these things. We need to use the different hybrid impulsive strategies also. And also this is also the study that we releasing the 1, 2, 3, like that way. We can see that there is an increasing in the impulsive period also. The same things is we can see that. The conclusion is the same, that in the different mathematical model we will get the different ideas, and it's this model we will get most accurate result of in which time period we need to releasing these things, and in which time period the system is stable in that way also. So these are the key features and future scope of this work. The pulse releasing amount the impulsive period was found to be responsible for eradication of pest population and consideration for the different life cycles of ensure accuracy and pest management without the pesticide save ecology and prevent the extinction of non-target pest. And numerical part we can see is that time period also, and future we can extend these consideration for the mutation of pest, genetic changes in plants and random releases, because here I am considering impulsive releasing of controls at a particular time. And maybe we can use the random manner also. So or required equation changes to the stochastic manner. So further we can develop this model to the different aspects like the fractional differential equations, and we can understand the different dynamics of that also. So I'm also thanks to the International Mathematical Union Breakout Graduate Fellowship. This paper is the partially financial support from IMU. These are my references. Thank you. So if you have any doubt regarding that, you can email me. So I will, if I know, I surely discuss with you and share some reference also with you.
Thank you very much, Professor Ritos. Let ask the participant whether there is a question or not. Let me remind one more time for the participants. If you have any question, you can use the question and answer part in the bottom of the screen. I would like to thank one more time, Professor. It was a very interesting and well-designed presentation. It seems there is no question, but I think all participants took your email address, and if they had a question, they would reach to you for
Sure,
asking.
no problem with that. Yeah.
Thank you very much.
Thank you so much. Thank you so much.
Okay, now we have a little break for 3 minutes, then we are going to continue with the Zehra Özdemir from Turkey to our program. See you soon. Hello again, we are here after a little break. Now we can continue our program as scheduled. Our next speaker is Professor Zehra Özdemir from Amasya, Turkey. She is going to give a speech entitled by a kinematic model of the Ritos Law in the optical fiber via split quaternions, application to electromagnetic theory. Hello, hocam.
Hello.
Welcome to webinar. Are you ready?
Yes, I'm
If
ready.
you are available, you can share your screen. We are seeing very well.
Okay.
Okay, you can. Yes.
Thank you. I am Zehra Özdemir. I am associate professor in Amasya University, and I talk about the Ritos laws and the electromagnetic curves in the optical fiber in semi-Riemannian space. First of all, I want to describe the electromagnetic wave. In here, we can see an electromagnetic wave model. In here, E is the electric field, and it is also called as polarization vector. And B is a magnetic field, and it is divergence-free vector field. And the plane depended by the E and B called as polarization plane. And in here, the Z-axis can be assumed as an optical fiber, and in here we can see that the tangent vector of the optical fiber perpendicular to the polarization plane, and thus if we want to see a linearly polarized light wave along an optical fiber, the polarization plane make a rotation motion. During this rotation motion, the tip points of the electric field trace a curve called as Ritos curve. In here, the red one is Ritos curve, and this law called as Ritos Law. And the transportation of the polarization vector E along an optical fiber was initially investigated by Ritos. Then the extensions of the Ritos law was given by Vladimirsky. The author showed that the polarization vectors E and magnetic field B perform rotations with respect to Fresnel frame T and B along a light ray. The first geometric phase was introduced by Pancrahan. Then Berry observed some characterizations of a dynamical phase and the geometric phase shift. Berry's phase possesses remarkable geometric property, and it depends only on the geometric structure of the space and does not depend on the duration of the evolution. And the linearly polarized light wave is coupled into an optical fiber. It can perform rotations of a polarization during propagation. Ross and Kugler examined this geometric rotation in the optical fiber and present various characterizations. Then this motion is observed by many authors in some areas. In here, we investigate that the polarization plane make a constant angle with the tangent vector of an optical fiber. If the polarization plane and the tangent vector of the optical fiber make a constant angle, then if you want to see a linearly polarized light wave, then the polarization plane make a homothetic motion. And if we make a homothetic motion, and for model of this form of motion, we obtain the split quaternionic forms of this motion and use the split quaternion. And now I want to introduce some information about the quaternions. The real quaternions were discovered by Hamilton, and then split quaternions were defined by Puckle. And the fundamental role of the quaternion algebra is that easily describe the rotations in three-dimensional space. In Euclidean space, the spatial rotations can be expressed via the real quaternions. Similarly, in Lorentzian tree space, the spatial rotations can be expressed via the split quaternions. Moreover, quaternions are used in computer graphics, robotic systems, video games, computer programs, navigation systems, and various physical laws are also easily described due to quaternions. And in here, we use the inner product is given equation 1. And since the Lorentzian metric has a minus, then we have three types of vectors: space-like, time-like, and null. And the Frenet frame equations related to the in Lorentzian Minkowski space defined by the equation 2, and the semi-Riemannian curvature tensor on M is given by equation 3, and then the sectional curvature of M is defined by the equation 4. And if the surface M has constant sectional curvature, then it is called semi-Riemannian space form. Then the curvature tensor of a semi-Riemannian space form is given as equation 5. And in here, we investigate the behavior of the charged particle in an electromagnetic field using the Killing magnetic vector field. And Killing magnetic vector fields, we know that the Killing vector fields are the lead derivative of the Killing vector fields are 0. Then this gives in three-dimensional space, the Killing vectors are divergence-free vector fields, and they define a special class of magnetic vector field called as Killing magnetic vector field, and the related Killing equations given by the equation 6. And the split quaternions, a split quaternion given by equation 7, and the set of the split quaternions given by the equation 8. And the split quaternion product given by the equation 9 and 10, and the metrical form of the split quaternion product given by the equation 11, and the conjugate, norm, and the inverse of a split quaternion given by the equation 12, 13, and 14. And since the vectors in semi-Riemannian manifolds have casual character, the polar form a unit split quaternion defined by the following three cases. And the rotation matrix associated with a unit split quaternion given by the equation 16. And the homothetic motion given by the equation 17, and matrix representations of the homothetic motion given by the equation 18. In here, the eta is homothetic scalar, R is rotation matrix, and T is translation vector. And again, since the casual characters of the vectors in Minkowski space, the angle between the two vectors in semi-Riemannian 3 manifolds have following characterizations A, B, and C. And so in the spherical coordinates and using the casual characters of the vectors in semi-Riemannian manifolds, the electric field can be defined by the following four cases. And now we investigate the polarization states during the homothetic motion. The geometric path can be described by a space curve PC. And in here, we assume that the polarization plane make a constant angle with the tangent vector of the optical fiber. Then we can define that, we can assume that in here, E and the tangent vector T are time-like vectors in the same time-like cone. And then the angle between these vectors defined by the equation 19. And using some operations, and the spherical coordinates of the electric field, we obtain the geometric phase model of the electric field in equation 20. In here, we want to see a linearly polarized light wave and the homothetic motion of the polarization vector in a single mode fiber, then we must take the angle beta is equal to integrations of tau. And then we can see that the rotational part of a homothetic motion make with the angle tau. And in here, we can say that the relation between parallel transportation and Fermi-Volkel transportations gives equation 22. And this gives that during the homothetic motion of the polarization plane, the electric field moves with the Fermi-Volkel parallel transportation rule, and thus by means of the Fermi-Volkel parallelism, we may say that this form of optical fiber describes a curve as E1 Ritos curve. Namely, we obtain that the polarizing vector varies in the direction of the vector field E1. Then the polarization vector related to the fiber can be expressed as in equation 24. And then we can give some theorems related to the geometric path equations. Let us consider that linearly polarized light is coupled into an optical fiber related to the curve PC with the Frenet frame fields T, N, and B, and the angle between the tangent vector T and the polarized vector E be constant, such that E and T are time-like vectors in the same time cone. And then the polarized light may perform a homothetic motion of polarization during propagation towards the unit split quaternion sigma. The parametric representations of the E1 Ritos curve is obtained as follows. Toward the split quaternion product, we obtain the equations 25. And toward the homothetic motion, we obtain the parametric form of the E1 Ritos curve in equation 26. In here, the angle beta is equal to minus integrations of tau. And we can give a corollary during the homothetic motion of the motion of the polarization plane. In here, since the tangent vector and the electric field is a time-like vector, then they are not perpendicular vectors. And if the other cases, if the angle between the homothetic between the polarization plane and the tangent vector of the optical fiber is a perpendicular angle, then the plane makes a rotation motion. And then during the homothetic motion of the polarization plane, the electric field trace a curve on the Lorentzian sphere. And this curve is given by the following, by the quaternion product and the homothetic motion, toward the homothetic motion, the parametric equations of this spherical curve given by the equation 27 and 28. And using similar cases, we obtain that if E space-like and T time-like vectors, and E and T are space-like and B time-like vectors, E and T are space-like vectors, and N is time-like vector. We obtain similar characterizations and similar calculations above. We obtain the geometric phase models related to the polarization plane make a constant angle with the vector N, and the polarization plane make a constant angle with the binormal vector B. And now using the geometric phase model, we can characterize the electromagnetic curve. The electromagnetic curve described by a curve, if a charged particle moves in an electromagnetic field, then the tangent vector of this particle is affected to the magnetic field. Then it is obtained a force called as Lorentz force. And with the influence of this Lorentz force, the particle moves in a new trajectory. This new trajectory called as electromagnetic trajectory and satisfy the equation 29. And using the obtained electromagnetic, if we consider all of the geometric phase models, we obtain the equation 30. And using the geometric phase models, we obtain that the Lorentz force equations related to the Frenet frames satisfy the equations 31, 32, and 33. And then using the Killing equations and the geometric fuzz models and the electromagnetic Kerr equations, we obtain that PC is a E1 electromagnetic Kerr if and only if Killing magnetic field B has the form in 34, and PC is a E2 electromagnetic Kerr if and only if Killing magnetic field B has the form in 35, and PC is a E3 electromagnetic Kerr if and only if Killing magnetic field B has the form in equation 36, and similar characterizations can be given for the E perpendicular N and E perpendicular B. And then we obtain this theorem. Let us consider that B is a Killing vector field in three-dimensional semi-Riemannian space form. Then curvature and torsion of E1 electromagnetic Kerr satisfy the following differential equations. And if B is a Killing magnetic vector field and the E2 electromagnetic Kerr in the optical fiber are satisfy the following equations, and if B is a Killing vector field in three-dimensional semi-Riemannian space form, then the E3 electromagnetic Kerr in the optical fiber are Halages with constant curvature and constant torsion. Now I can give an example. In here we give a parametric representations of Kerr PC in equation 30, and the related geometric state of this Kerr given by following three cases. In here, the shape of the homothetic motion of the electric field given by two types. In the first figure, in here we see that the blue Kerr are blue Kerr is optical fiber, and the red vectors are electric field, and the electric field during the homothetic motion of the electric field moves with Fermi-Volkel parallel transportation rule, and the tip points of the electric field trace a curve, this curve called as E1 Ritos Law and given by the in figure 2. And the other example is the polarization plane. Perpendicular polarization plane make a constant tangent with the normal vector and the related E2 Ritos Law. And the last one is the polarization plane make a constant tangent with the binormal vector and the related Ritos Law. And these one are the a charge point particle, a trajectory of a charge particle in the electromagnetic wave during the homothetic motion of the polarization plane given by the three cases. And this is my reference. Thank you for your attention.
Thank you very much, Professor Özdemir. It was a very interesting presentation. Let me ask whether there is a question from the participants. Let me remind one more time, if you have a question or any comments, valuable comments, you can use the Q&A, in other words, question and answer button at the bottom of the screen. Let me check. It seems there is no question. I would like to thank one more time. We are very glad to attend our webinar. So thank you very much.
Thank you. Also, I thank you to give me an opportunity for presentations in this webinar.
You're welcome. It's our pleasure. Okay, we can stop in your sharing. Now we can continue our program as scheduled with the third presenter, Salmi Saidi from Algeria.
I am here. Hello.
Hello, can you hear me?
Me?
Yes, we can hear us.
Okay. Can I begin this sharing the presentation?
Yes, of course. If you are ready and if you are also available, open your video camera. You closed your sharing screen. Please try one more time. Professor Saudi, can you hear me?
Yeah, I hear you. Please wait a few seconds.
Okay, we are waiting you.
Okay, wait. It's okay?
Yes, it's okay. Let me introduce you. Our speaker is attending from the Algeria. Now she is given presentation entitled by a differential inclusion of second order and application to control. Now microphone with you. If you are ready, you can start.
Yeah. First of all, I would like to thank the organizing committee for offering us the chance to participate to this wonderful meeting. Dear participants, thank you for joining me. I'm Mrs. Soumia Saidi from University of Jijal. It's a pleasure to me to contribute with an oral talk entitled A Differential Inclusion of Second Order and Application to Control. Let's start with a brief introduction. Recently, considerable attention has been given to the existence of optimal solutions to control problems subject to differential inclusions. Optimization and discrete approximation of sweeping processes with controlled moving sets and perturbations have been investigated in the scientific literature. We refer to, for example, these references. In light of the recent paper published in 2016 dealing with controlled maximal monotone operators, the current work is a new contribution on this topic. We use the following notation: A for an interval of R, H a real separable impact space, BH the closed unit val of H, CAH the space of continuous functions from A to H, L2AH the space of square integrable functions from A to H, W12 is the space of absolutely continuous functions from A to H with derivative in L2. And we denote by A0TX the element of minimal norm of the operator ATX. We deal with the pseudo distance between two maximal monotone operators A and B introduced by Vladimirov in 1991, defined as follows, and satisfying these properties. We need the following lemmas proved by Kunz and Monteiro Marquez in 1997. These lemmas involve the elements of minimum norm of maximal monotone operators and also different modes of convergence. Also the pseudo distance between maximal monotone operators as follows. In our study, we need also the following lemma proved in the paper recently published by these authors. If we consider a time and space dependent maximal monotone operator that satisfies a condition H1 that involves the pseudo distance between maximal monotone operators, we say that the operator varies in an absolutely continuous way in time and in a Lipschitz continuous way with respect to state. In this condition, we consider an estimate involving the elements of minimal norm. Then, for any x in the space W1, 2, there is a unique absolutely continuous solution to the first order differential inclusion governed by time and state dependent maximal monotone operator with initial condition in the domain of the operator such that the velocity derives this estimate, where beta dot, of course, is in L2. That is, it is square integrable. Following some arguments used in the proof of Theorem 3.1 in the recent paper by the author Saidi, published in EECT, the journal, we are able to prove the existence and uniqueness of the solution to the second order differential inclusion involving time and state dependent maximal monotone operator with a single valued perturbation that acts as an external forces with initial conditions U0 and X0 as follows. So our first theorem is the following. If we assume that the operator ATY is a maximal monotone operator that varies in an absolutely continuous way in time and in a Lipschitz continuous way in state, that involves the element of minimal norm as in condition H2 that satisfies a bulk compactness assumption. Then if we consider a single value perturbation, which is measurable in time and continuous with respect to its second and third variables, and such that this estimate holds true, we impose also a local Lipschitz condition on bounded sets as follows. Then, for any V in W12, the second order differential inclusion admits at least one solution, and we have this estimate of the velocity U dot. Now we move to state our main theorem concerning control theory. Assume that the time and state dependent maximal monotone operators varies the assumptions H1, H2, H3. If we consider F that satisfies the conditions above, if we consider a cost functional which is measurable, lower semi-continuous for each t and convex with respect to its third variable, then the set V of control defined by the function V in W12 such that the velocity is square integrable. Then the problem that consists of minimizing this integral functional on the set V has an optimal solution where xv is the unique absolutely continuous solution to the first order problem with single valued perturbation. Now we prove that the set V is convex compact. So first we observe that the mappings in V are equicontinuous. Then the images belong to a convex compact valued and integrably bounded set valued map, so that the images are relatively compact. It remains to use Ascoli's theorem to deduce that this set is relatively compact, then to prove that V is closed, which means finally that the set is compact in the Banach space C0TH. Now we begin our proof concerning control. In view of our first theorem concerning the existence and uniqueness of this problem, there is a unique solution denoted XV to this problem, and that satisfies this estimate. Let Vn be a minimizing sequence of the problem, our problem 5, that is, the limit equals Vn on V of this integral functional. Suppose that Vn uniformly converges to V in the compact set, and denote by XV the corresponding unique solution to this approximative problem, which satisfies this estimate. Then we observe that there is a map such that we have the pointwise convergence of the sequence to X, the pointwise convergence to the sequence of the velocities to X dot, and we have this weak convergence in L2. Using lower semi-continuity theorem published in this book, applied to the lower semi-continuous convex integral functional associated with G, we deduce that the limit nth of this integral functional is greater or equal than this quantity, and it remains to show that this integral quantity corresponds or coincides with the nth of this integral. That is, we are going to prove that X coincides with XV, and which finishes the proof. For this purpose, we are to make some computations. We prove the pointwise convergence to the perturbation in such reasoning, and we have the boundedness assumption that allow us to deduce the convergence in L2. Also, we invoke the pseudo distance between maximal monotone operators and use the limits recalled above to check that this inclusion holds true. So we have to do some computations. We prove the weak convergence in such a sense to get finally that the following differential inclusion holds true, and X coincides with XV, which is the unique solution associated to the control of this problem. From our main results, we easily deduce that the solution set to the second order problem governed by time and state dependence maximal monotone operators with single valued perturbation is compact in the Banach space CAH. In our future research, we intend to investigate control problems by differential inclusions involving maximal monotone operators when the control acts in the perturbation. And here, recall that here the control acts as in the states acts in the state of the operator. In our future research, we may deal with the case when the control acts in the perturbation or in both the perturbation and the state of the operator. We are inspired in this work by these references dealing with optimal control of the sweeping process and maximal monotone operator. We have used these references, the first one dealing with the pseudo distance and different lemmas. The second one using the lower semi-continuity for integral functional. This recent paper published in mathematics, we have considered the lemma that ensures the existence of the solution for the unperturbed differential inclusion, and is an interesting paper that these with fractional order of evolution inclusion coupled with the time and state dependence maximal monotone operators. Also, we refer the reader for these recent papers that consider maximal monotone operators with time and state in the time and state dependence case. The first one involves fractional differential equations with differential inclusions. The second one deals with the second order but using an anti-monotone condition. And the third one is about the second order differential inclusion with finite memory. And finally, I would like to thank you very much for your kind attention. Thank you.
Thank you very much also, Professor Saidi. It was a very nice presentation. Let me ask about your questions. Dear participants, if you have any question or any valuable comment, you can write them into the Q&A button. Let me check the window. It seems there is no question, but on behalf of the committee and participants, I would like to thank you one more time. Also, we are very glad to for your attending the webinar. Thank you very much.
Thank you.
Okay, now we can take a little break until our next speaker, Alper Vural from Turkey. It's only 2 minutes. See you soon. Hello again. Now we are continuing our program with our next speaker, Alper Vural from the Istanbul, Turkey, with the presentation n-dimensional lattice path enumeration. Can you hear me, Professor Vural?
Yes, I can.
We can hear you also. And also we can see your screen. If you are ready, you can start after making your screen is full screen.
Can you see it now, full screen?
No, it is not full screen now.
Can
Maybe
you see
because
now?
of... Yes, now it's okay.
Okay. Hello, I am Alper from Istanbul. I'm going to present you the n-dimensional lattice path enumeration. In the literature, lattice path is defined as one of the paths from one point to another in a model that consists of horizontal and vertical paths that intersect each other perpendicularly. Various researches have been carried out on the lattice path for many years. These studies gained momentum, especially after the 19th century, and the most comprehensive studies on the subject have been made in recent years. We refer 13 for a history of lattice path enumeration. We enumerate lattice paths in an n-dimensional space for a fixed set of vectors, Vn, who consist of all vectors that have coordinates 0 or 1 besides the 0 vector. Our goal is to find a formula that gives number of paths from the origin to the point L1, L2, Ln using the vectors in Vn for n greater or equal to 2. We usually refer to these vectors as step. Figure below gives concrete examples of lattice paths in 2 and 3 dimensional spaces. For example, this path right here is at 3, terminates at 3, 2, and this path right here terminates at 2, 2, 2 in 3 dimensional space. There are 2 to the power of n minus 1 steps in Vn. Each aj with one smaller or equal to j, smaller or equal to 2 to the n minus 1 represents a different step in Vn. Rj is the number of aj steps used in a path. A bundle of steps is an unordered group of steps that do not have to be different. Given all values of Rj, we can form exactly one bundle of steps. For example, if n is equal to 2 and R1, R2, R3 is 3, 1, 0, we get the bundle A1, A1, A1, A3. There are 3 A1 steps. Number of all possible paths in n-dimensional space that doesn't have to terminate at a fixed point can be found with the following formula. All possible bundle of steps are generated with the sums, these two first sums. And for a given bundle of steps, these two second, this sum and this product finds all possible permutations of that bundle. We find a function that determines whether a path terminates at the point L1, R2, Ln, the point that we want to go to. Determining the terminal point of a path is the same as determining the terminal point of the bundle that the path was created. It follows because all arrangements of a bundle of steps terminate at the same point. We systematically assign vectors to the notations of the form aj. First, we establish another notation for steps. Let h1, h2, hn be a step in Vn. Note that these h1s are just ones or zeros. We write db to the notation of that step for every hp equals 1. And we have u smaller y for du dy. For example, the step 1001 is given by the notation d1 d4. This notation tells which axis the steps move on. Note that the notation d1 d4 represents 1001 only if n equals to 4. For example, d1 d4 represents 1010 if n is equal to 5. We call the length of a step is the number of axes that the step moves on. That's equivalent to the number of ones in the vector h1, h2, hn, and also the number of db terms in the notation of that step. We start sorting the steps by their length. The length of the steps ascends from 1 to n. That means that the notations aj with like that represents the steps with length of k plus 1. And for a fixed length, the arrangement is similar to an alphabetical arrangement. Assuming db denotes the beat letter in the alphabet, we do the classical alphabetical arrangement. The arrangement of steps for n equals 4 is shown below. For example, this A5 vector can be think as AB. This A6 is AC, AD, BC, BD, CD. We determine the distance traveled on a specific axis for a given bundle of steps. We call this axis the observed axis and represent it with di. We find all steps that have di in its notation. We can show such steps with in this form, where p is the number of axis that's written before the observed axis, and k plus 1 is the length of the step. The valid interval for I is 1 to n, because I is the observed axis and there are n axes in the n-dimensional space. The valid interval for k is k is between 0 and n minus 1, because we said that k plus 1 is the length of the step, and the length of the step can be 1 to n. The valid interval for p is maximum 0, k plus I minus 10, and minimum k, I minus 1. We find all steps that travel on ith axis for fixed values of I, k, and p. We know the function that finds the coefficients of all such steps in n-dimensional space by fn I, k, p. We say that all steps with given I, k, and p values whose parts before the observed axis are the same form a section. For example, when observing D6, D3 in 6-dimensional space, D1, D3, D4, D1, D3, D5, and D1, D3, D6 form a section because the part before D3 is fixed. Let the part before the observed axis be fixed, more specifically D. Let AQ plus 1 be the step, D, DI, D plus 1, DI plus 2, consecutive terms here. Then all AJ steps with Q plus 1, smaller or equal to J, smaller or equal to Q plus, M minus I choose K minus P, move on the ith axis. Thus they form a section. For fixed values of I, K, and P, there can be I minus 1 P different parts for the observed axis, because there are I minus 1 different dB terms, and we have to choose only P of them. For example, if I is equal to 3 and P is equal to 1, there are two different parts. It could be D1 and D2, and we get sections D1, D3, D2, D3. If the part before the observed axis is D1, D2, D dot dot dot, DI minus 1, pretty much all of the consecutive terms, then the first step in this section is exactly this. That's the first step with the length of k plus 1. If the part before the observed axis is missing some of these dB terms, to find the first step in the section, it's required to add more terms besides this term. We create sequences that have B for each dB term missing in the part before the observed axis. The empty sequences are subsets of 1, 2, I minus 1 with I minus P minus 1 elements. All different subsets of that set with I minus P minus 1 elements are the sets in the form like that. We found empty sequences for I is equal to 4 and I is equal to 5. These are the empty sequences. For each missing term in the part before the observed axis, it's required to add m minus mt, choose k minus gt. We found the following gt sequences. The sequences on the top are empty sequences, and the sequences on the bottom are the gt sequences corresponding to that empty sequence. And we found the following relation in gt sequence. Finally, we can write fn I, k, p as follows. If I is equal to p plus 1, then there are no parts missing before the observed axis. Thus, there are no empty or gt sequences. So we wrote fn I, k, p piecewise like this. Finally, the distance traveled on ith axis is k equals 1 to m minus 1. P's interval is like that at fn I, k, p. Define Rx 1 if x is equal to 0, 0 if x is not equal to 0. Then the total number of paths to the point L1, L2, Ln can be found with the following formula, where we subtract the distance traveled on the ith axis from the distance that we want to travel. And if all of these terms are 0, then we can get a 1 here. In n-dimensional space, the number of paths to the point 1, 1, 1, 1, 1 corresponds to the number of weak coordinates of a set consisting of n elements. These are the total number of arrangements n competitors can have. The answer is not just n factorial, as competitors can have equal points. Let K be a set of vectors, and L, L1, L2, Ln be the number of lattice paths from origin to the L1, L2, Ln point. Then the recursive relation in this sequence is as follows. Let M P to P prime denote the number of lattice paths from P to P prime without restrictions. The number of paths from P to P prime that do not stop at the last points in a given set R can be computed by the following algorithm. Let Rm be an m-element subset of R. For Pi element Rm, calculate the quantity -1 to the power of m and these for all permutations of Rm. There cannot be more than one non-zero value, and if there is one non-zero value, note it down. Do this for all subsets of R. The sum of results in the number of paths from P to P prime that do not touch the points in R is the sum of those numbers. We multiply by -1 to the power of m because of the inclusion-exclusion principle. These are my references. Thank you for listening.
Thank you very much for your exceptional talk, Professor Vural. Let me ask the attendees for their questions. If you have any question, you can use the question and answer button to write your question to the Professor Vural. Let me check. It seems there is no question. I would like to thank you one more time, Professor. Thank you for your attending to the webinar. So now we can make a little break until our next speaker, Ibrahim Demir from Istanbul, Turkey. So see you soon, 9 minutes later. Hello again, everyone. Now we are ready to continue our last speaker of the session. He is Ibrahim Demir from Istanbul, Turkey. The professor is going to give a speech entitled by Correlation Coefficients of Interval-Valued Fermatian Hesitance Fuzzy Sets with Their Application. Professor, can you hear me?
Yes, I hear.
Thank you very much. Welcome to the webinar. If you are ready, you can make your presentation full screen.
Okay, is that show?
Yes, now we can see it.
Okay, thanks. Hi,
You can start. Okay.
my presentation correlation coefficient for interval valued Fermatian hesitant fuzzy set with pattern recognition application and other making decision method. 6 section, one section will be introduction, literature will be given, preliminary section, I give you definition and theorem. Correlation coefficient is my procedure method and application, advantage of the new approach and conclusion. An interval valued Fermatian hesitant fuzzy set is a combination of interval valued Fermatian fuzzy set with Fermatian fuzzy hesitant fuzzy elements in the form of interval values. Therefore, interval valued Fermatian hesitant fuzzy set are existence of Fermatian hesitant fuzzy set, which are powerful tools to represent more complicated, uncertain, and vague information. This strategy aims to focus on all kinds of correlation coefficients for Fermatian hesitant fuzzy set and extended term of correlation coefficient and weight correlation coefficient for interval valued Fermatian hesitant fuzzy set. At least the numerical examples show the feasibility and the applicability of the proposed method in the multiple criteria decision. The Fermatian fuzzy set was initiated by Senapati. In the FS Fermatian fuzzy set, the membership degree and non-membership degree accomplish property. The FFS, which is included in the literature as a new concept, gives better result than the intuitionistic and Pythagorean fuzzy set indefinite uncertainties. In Senapati, some properties score accuracy function FFS are solved. Further, the Topsis method, which is the frequency used multi-criteria decision problem, has been applied to FSS. In addition to Senapati, the Topsis technique, which is continuity unitized in making decision multi-criteria making decision program has been updated. As a continuation of this work, Senapati investigated several new operations, subtraction, derivation, Fermatian arithmetic mean operators over FFS, and applied Fermatian fuzzy weighted protected model to solve a multi-criteria making decision making program. In this study, aggregation operator belong to the FFS and have been defined, and the properties related to these operators have been examined. In study Tanghai, the notation of Fermatian fuzzy linguistic term set is offered. Operation score and accuracy function belong to this set were given. An if similarity measure related to Fermatian fuzzy linguistic term set is constructed. The nav measurement is a combination of Euclidean distance measure and Cousin similarity measure. Kirish defined Fermatian fuzzy soft set and give the measure anthropology based on Fermatian fuzzy soft set. In Kirish's paper, a new hesitant fuzzy set, which is called the Fermatian hesitant fuzzy set, has been given and investigated some properties. In other paper by Christie, the ELECTRA method is defined by formatting fuzzy set according to the group decision-making process in which more than individual interact at the same time. Shahgazi paper, a decision support algorithm in accordance with the formatting fuzzy set, soft set concept presented to the maximization effectiveness of antivirus mask. In another paper, various formatting fuzzy reference relations have been defined. An additive consistency based on a probability vector has been given. In addition, a model is presented to obtain a missing decision in complete formatting fuzzy set profession relations. In the study, there are different applications such as aggregation operators and information measures to solve a decision-making problem. Except that this solution method, another method for choosing the best alternative is correlation coefficient, which are used to measure the level of dependency between two sets. SSC are used to measure how strong a relationship is between two variables. SSC is a bivariate statistic when it summarizes the relationship between two variables, and it is multivariate statistic when you have more than two variables. Therefore, there is a very wide field of study, from science to economics, from engineering to medicine. Although existing probabilistic methods have successful results, they also have limitations. For example, probabilistic techniques are in the accordance with a mass collection of data, which is random to acquire the necessary confidence level. However, on a gray scale, the complex system has massive fuzzy ambiguity, owing to which it is to acquire the complete possibility of the events. Hence, outcomes according to probability theory don't all the time ensure beneficial information to be professional, owing to the limitation of being able to operate only quantitative information. Furthermore, occasionally there is inadequate data to accurately operate the statistic of parameters in real-world practice. As a natural consequence of this limitation, the outcomes in accordance with probability theory do not all the time ensure beneficial information to the professional, and the probabilistic examination approximation is insufficient to account for such built-in uncertainties in data. There are many possibilities to overcome this difficulty. One of the most successful results of these possibilities for handling uncertainties and the impreciseness in the decision-making is method based on fuzzy set theory. In Chang studied correlation of fuzzy information according to classical statistics, solved and ensured a formula for SSC of fuzzy sets. In Liu paper, the assess of fuzzy information by utilization of the mathematical programming approximation according to the standard definition has been investigated. Based on the result were obtained through FS theory. More comprehensive and more accurate results were obtained with institutionalistic fuzzy set. The theory of IFS considers non-membership degree together with the membership degree and requires that their sum be 1 or less than 1. The CC derived based on IFC have been operated in numerous different fields as cluster analysis, image processing, pattern recognitions, etc. Many DM problems related to Pythagorean fuzzy set information have entered the literature thanks to PPFS, which has introduced to overcome the limitation IFS. SSC derived according to IFS, where PFS theories are available in the literature. It is the aim of this study to give the coefficient, correlation coefficient and weighted correlation coefficient formulation to measure the relation between two IFHFS. The effectiveness of the proposed techniques will be demonstrated by giving the numerical example of the pattern recognition and multi-criteria decision making. Definition: institutionalistic fuzzy set is defined like this. Zeta is said to be membership degree, eta is said to be non-membership degree. Pythagorean fuzzy set is described like this, and Fermatian fuzzy set is described like this. The hesitant fuzzy set is described like this. And the Fermatian fuzzy set is described like this, and the conditional is three conditional days. Information energy of Fermatian fuzzy set N is described like this, and theta indeterminacy degree is calculated like this. And N and M is Fermatian fuzzy set. Then correlation is calculated like this, and correlation coefficient calculated two method. One like this method is classical correlation coefficient, for example, and the other correlation coefficient like this. In this define information energy is maximum. Then the last definition, interval value Fermatian hesitant set is defined like this. And this interval valued set we define the informational energy of Fermatian fuzzy set like this. Then we correlate, evaluate like this, and interval valued fuzzy Fermatian set FG if choose correlation coefficient, this is described like this. And this Fermatian fuzzy set, there's three conditions even like this. Example, if F and G, their value is this, informational energy F 1.9, information energy G 2.74. Then correlation calculate like this 1.81, then the correlation coefficient is 0.734. Then maximum information energy correlation like this, and the conditions F and G like this. Take a weight vector, yani weighted correlation coefficient is defined equation for satisfied like this condition. Then maximization function'da CC between, weighted CC between this condition satisfied. Pattern recognition application example, if we choose the PR1, PR2, PR3 and infinity universe like this, and another unknown pattern UP like this, then we determine the correlation method, and we computed from UPR to PR are the given the follows. Then we show that PR3 UP the same set because the correlation coefficient is then upper the others.
Sorry for interruption, Professor. You have left 2 minutes.
Okay, thanks. Then another example, multivariate criteria methods like this. A scientific committee should evaluate for possible project LI according to 3 criteria KI. Here, C1, C2, and both benefit criteria, and C3 is the cost accreditation. Take the weighted factor of criteria like this. This decision matrix is given by the expert as a table like this. Then the correlation coefficient is calculated. Then we evaluated these solutions. Then F3 is the upper value like this. Okay, then computation in this static correlation coefficient for interval value Fermat-Hesselton fuzzy set has been proposed. The shortcoming of the existing operations have also been highlighted in this study. Based on that, the presented paper have extended the theory of the correlation coefficient from Pythagorean fuzzy set and to Fermatian fuzzy set, in which is the constrained condition of the sum of membership and membership degree. Less than 1 has been relaxed. Numerical examples have been given that demonstrated that the proposed correlation coefficient can easily handle the solution, where the existing correlation coefficient in Pythagorean fuzzy set environmental fields, the proposed correlation coefficient Fermatian fuzzy set has been developed by taking the degree of membership, non-membership, and the degree of the Hesselton between them. Thank you.
Thank you very much, Professor Ibrahim Demir. It was a very interesting presentation. So let me ask whether there is a question for you. Dear participants, if you have a question or any comments, you can use the question and answer part. Okay, it seems there is no question. I would like to thank one more time. We are very glad to see you here, Professor.
Thanks.
Welcome. Then it was the last presentation for the first session of the last day of the webinar. So now we are giving a little break after the second session. After the break, we will start the second section at 10:45. Then my colleague Urcan Eser will moderate this session. Let me remind one more time, you can follow our timer from the screen. See you soon after the break.
Good morning, everyone. I am Uğurcan Eser, ladies and gentlemen. Now, I kindly invite Professor Rashid Abu Dawaz to do his presentation. Professor Dawaz is coming from Irbid, Jordan. Professor Dawaz, welcome.
Thank you.
Title of the talk is Ungraded and Absorbing Primary Ideals. Professor Dawaz, your time is 15 minutes. Please,
Okay.
Can you share your screen? Thank you.
It's
You can
okay?
start now. Okay, you can start now.
Thank you. Thank you very much for giving me this opportunity to join your wonderful webinar. It's my pleasure to share with you our way or my way. The title, as you see, is Ungraded when Absorbing Primary Ideals. This work is joint work with my friend, Professor Patani from Jordan University of Science and Technology. First of all, we will talk about the basics or the definition, what's a graded ring. Throughout this article, G will be a group and R a commutative with commutative ring with non-zero unity. R is said to be G graded if we can write R as a direct sum of components, R sub G. R sub G are additive subgroup, and they should satisfy this condition, Rg, if we multiply, and this multiplication is the usual multiplication of the ring. Rg by R sub H should be a subset from Rgh, and the operation between Gh is the operation on the group G. So the product between R sub G and R sub H is the product of the ring, and the operation between G and H is the operation of G. Should be maybe addition, maybe multiplication, maybe star, as you like. And this should be true for all GH in G. As we said before, the component R sub G should be an additive subgroup for all G in G. In fact, this comes from the direct sum. If we take any X in R, then X should be written uniquely, in fact, as a summation of Xg, and Xg are the component of X in Rg. We will call the set of all homogeneous elements of R is H of R. And R sub E, the component R sub E, where E is the identity of the group G, it will be subring, and it will contains the unity when R contains the unity. So this was proved in reference 5 that Re is always a subring of R and contains the unity. Now, what about the definition of a graded ideal? If we have a graded ring R and we have an ideal I is said to be a graded ideal if it can be written again as a direct sum of the component I intersection R sub G. Or in other words, equivalent characterization for the definition, if we take X in I, and of course X will be written as sum of components, all the components of X should be remains inside the ideal. This is the definition of a graded ideal. The first question, if we have a ring and we make it graded, can we have all the ideals inside this ring graded? The answer is no. So here the following two examples show that an ideal of a graded ring is not necessary to be graded. We have two basic examples. If you take the Gaussian integers, z of I, and you take g equals z2, it's the group of integers mod 2. If we have the following basic, in fact, calculation, you take R0 equal set of integers and R1 equals I of z. It is easy to see that every element in R is written as A plus IP. So A will be the first component, R0 equals Z, and IP will be the second component, IZ. So this is a graded ring. If we look to the ideal generated by 1 plus I, this is an ideal of R, but in fact it is not graded, because if it's graded 1 plus I in I, so each component of this element should be in I. So in particular, 1 should be in I, and this is not true because, you know, if the ideal contains the unity, it will be the whole ring, and this is a contradiction. So this is an example, an ideal inside a graded ring, but it is not a graded ideal. Another example, we go to the ring of polynomials. We take K a field and the group Z of integers, and we take the ring of polynomials K of X. This is the ring of polynomials with coefficients from a field K. We make graduation over Z, so we take R sub n equal 0 when n negative, R0 equal the constant, and Rn equal Kx to the power n when n is positive. This, in fact, this is called the standard graduation or the usual graduation of the ring of polynomials. Again, if you look to the ideal generated by x plus 1, this is an ideal inside R, but it is not graded because the element x plus 1 inside I, if I is graded, all the components of this element should be inside I, but you know, x, it's a component, x lives in R1, should be in I, and this is not true. Again, 1 is a component living inside R0, so it should be inside I if I is graded, and this is not true. So these two examples show that not every ideal inside a graded ring is a graded ideal, and this is give importance for our work. In fact, if we have two graded ideals, then the sum and the product and the intersections of them will be graded ideal. This is proved in reference 4. And another result, if we take a homogeneous element, then every ideal generated by this element will be graded. And this is important one, in fact, too, because this is the easy way to construct a graded ideal. To construct a graded ideal, just you take a homogeneous element living in some component, and you take the ideal generated by this element, you will directly obtain an graded ideal. This is the definition of a graded radical. You know the radical in the ring, so we just redefine using the graduation. So this is the graded radical of I. If we have a proper graded ideal, then the graded radical of I is defined as follow, and it is similar to the definition of radical. In fact, this ideal is always a graded ideal, and this is, it has been proved in reference 8. So we can find every time graded ideal if we want. Our talk is about generalizations of a graded prime ideal. First of all, recall the definition of a prime ideal. A proper ideal B of R is said to be prime ideal if whenever xy belongs to R such that xy belongs to I, then either, sorry, this is a mistake, this is the ideal I here, xy in I, then either x belongs to I or y belongs to I. This is the definition of a prime ideal. Now, what is the definition of a graded prime ideal? Just we redefine the same definition, just we replace the elements you are taking from R. Now you are taking them from homogeneous of R. So again, if we have a graded ring R and we have a proper graded ideal, so the first condition should be graded ideal, then I is said to be graded prime if whenever x, y, and h of R. So this is the difference. Here you take the elements from R when you're talking about prime ideal. When you are talking about a graded prime ideal, you take the elements from h of R, so they should be homogeneous. And the remaining of the definition is the same, such that xy belongs to I, then either x belongs to I or y belongs to I. Clearly, from the definition, if I is a prime ideal of R and R is a graded ideal, then of course I will be graded prime ideal. But the converse is not true, and this gives importance for this way. So it's worth it to study such ideals. Now I will give you an example about a graded prime ideal, which is not a prime ideal. So see the following example. Indeed, the following example shows that the converse is not true in general. So again, we take the Gaussian integers and make a graduation over Z2. We have R0 equal the integer Z and R1 equal IZ. We take the ideal that generated by 17. Because if the 17 is a homogeneous element because it belongs to R0, so this ideal is graded. Every ideal generated by homogeneous element will be graded by the previous lemma. So this I is a graded prime ideal. We show that this I is a graded prime ideal now. We take two elements from H of R such that the product belongs to I. We are going to show that either X belongs to Y or Y or to I or Y belongs to I. So when you take two elements from H of R, the components are just two components, R0 and R1. So we have in fact four cases. Either both elements from R0 or both elements from R1 or one from R0 and one from R0. So we have three cases, in fact. Case one, we assume that the both elements are from R0. In this case, they are integers, such that 17 divides the product. And you know 17 is a prime, so 17 should divide one of them. 17 divides X or 17 divides Y, as 17 is prime number, and you are working inside the integers, which implies that X belongs to I or Y belongs to I, and we are done. The case two, I take the both elements from R1. So in this case, X equal IZ, IA, Y equal IP for some AP integers. Again, 17 divides XY, which is minus AP. When you product X, make the multiplication XY, you will have minus AP. So 17 divides AP, and again, 17 is a prime. 17 divides A or P, and then easy calculation, you will have 17 divides X or 17 divides Y, which means that X belongs to I or Y belongs to I. Case 3, we take X from R0 and Y from R1. We have Y equal IP for some integer P. Again, 17 will divide XY, which is IXP. And this means that IXP would be written as a 17 multiplied by an element from R for some, again, alpha, beta, and Z. Again, when you have to solve these equations, you will have XP equals 17 beta, and this means 17 divides XP, and you should remember that both of X and P are integers. So again, 17 divides X or 17 divides P, we will have our result. Of course, one can similarly show that X belongs to I or Y belongs to I in other cases. So in fact, we proved that I is a graded prime ideal. Indeed, on the other hand, I is not a prime ideal because I can choose two elements from R, which are not homogeneous, 4 minus I and 4 plus I. If you make the product, it will have 17, so it will belong to I, but neither 4 minus I belongs to I, nor 4 plus I belongs to I. So this is an important example talking about graded prime ideal, which is not a prime ideal, and this is to make our work worthy to study this course. The graded prime ideals have valuable performance in the graded commutative rings. There are various procedures to generalize this concept. In fact, in HTTP Journal of Mathematics in 2019, we gave a generalization of a graded prime ideals called the graded to absorbing. The definition is a propagated ideal P of R is said to be graded to absorbing whenever APC belongs to H of R, such that the product inside P, then either AP belongs to P or AC or PC. So you absorb two elements. On the other hand, in Turkish,
you have 2 minutes.
Oh,
Please summarize.
So my concept is a propagated ideal is to be graded one absorbing primary if whenever three elements in H of R such that the product in P, then X, Y, in P or Z in the radical. This is an example talking about graded one absorbing primary, that it is not a graded primary. So this is an important example that we are talking about a new class, in fact. And we proved that, you should, I will back here. We proved in this implication, in fact, graded primary gives our concept, and our concept gives graded to absorbing primary ideas. And we proved the converse of each implication is not true. This is another example about the converse. So our results, we prove that if B is a graded one absorbing primary, then the radical is a graded prime. This is important one. This is another proposition, but I want to talk about this one, in fact. If we have a graded one absorbing primary ideal, then the residue ideal, this is always a graded primary for every non-unit element belongs to H of R, but it is outside B. This is very important too. We proved that if we have the graded one absorbing primary ideal, then for every non-unit, you have either P is a proper subset of residue ideal or the radical equal the radical of B. We proved some characterizations, the following. B is a graded one absorbing primary ideal if and only if B is a graded primary. We proved that B is a graded one absorbing primary if and only if P is a graded primary ideal of R. So this is important characterization. And this one. Finally, we prove that the intersection will be graded one absorbing primary under the condition they have the same radical. They should have the same radical. And we have example that in this necessary condition. We study this concept about ring homomorphism and ring epimorphism, in fact. And we make another characterization, this one about this concept. In fact, I should mention that we follow this reference in our work. This reference, it's from Journal of Algebra and its application 2020. It is for Ayman Badawi and Jellikel. And our results somehow motivated by this reference from Badawi and Jellikel. Thank you for your attention.
Thank you, Professor Davas. Dear attendees, is there any questions? You can use question answer section now. There is no questions, I see. Thank you, Professor Davas.
Professor, before I go, I want to thank my friend, Professor Murad Sari. Thank you. And I miss him. Inshallah, I see him soon in Istanbul.
Inshallah. Okay.
Thank you.
Dear attendees, for the next presentation, I would like to invite Professor Esma Gomila to do her presentation.
I'm here, sir.
Welcome. Professor Gomila is coming from Elouet, Algeria. Professor Gomila, welcome. Title of the talk is Some Inequalities for Bounded Linear Operators in the New Norm on BH. Professor Gomila.
Yes, sir.
Can you share screen? Okay. You can start now. Your time is 15 minutes.
Yes, thank you.
Thank you so much.
Hello, my name is Esma Gamoula. I am a PhD student from Hamal Akhdar Al-Wad University, Algeria. I will talk about some inequalities for bounded linear operators in the new norm on pH. Walk plane, 1 abstract, 2 introduction, 3 preliminaries, 4 main results, 5 references. Abstract. In this presentation, we study some important properties for the alpha-beta norm newly introduced in reference 12 and obtain pounds for the said norm on the space of bounded linear operators on complex Hilbert space, from which we obtain pounds for the numerical radius of operator. Some other results are also given. Introduction. Let pH denote the C star algebra of all bounded linear operators on a complex Hilbert space H with usual linear products. An operator T in pH is called positive if this for all x in H, For T in pH, T star denotes the adjoint of T. The numerical range of T denoted by WT is defined by this. The numerical radius omega T is defined as the radius of the smallest circle with centered at the origin, and containing the numerical range is defined by this. In reference 12, a new norm named alpha beta norm on pH for T in pH. The alpha beta norm of T denoted by that is defined as this. Where alpha beta are real positive constants with alpha beta are not nil, we know that if alpha equal 1, beta equal 0, then alpha beta norm of T equal omega T, and if alpha equal 0, beta equal 1, then alpha beta norm of T equal norm T. Also, if we consider alpha equal B equal 1, then we have the modified Davis-Wieland radius of T that is equality. See reference 3. The organization of the work is as follows. We present some results on the important properties for the alpha beta norm and upper bounds for the said norm, from which we obtain bounds for the numerical radius of operator. Some other results are also given. Preliminaries. We present here some lemmas and corollaries which are useful for show our result. Lemma 1. The following inclusion relations for the classes operators as it shown. Lemma 2. Let A be E in H with norm E equal 1, then we get this inequality. Lemma 3. Alpha beta norm defines the norm on pH. For alpha beta are positive, such that alpha beta are not nil, and is equivalent to the numerical radius norm omega and the usual operator norm, satisfying the following inequalities. Lemma 4. For A, B are positive and alpha between 0 and 1, then we get this inequality for R big and equal 1. Lemma 5. Let A in pH and A are positive, and let X in HB and in unit victory, then we get the inequality 1 for R is big and equal 1, and we get the inequality 2 for R between 0 and 1. Main results. We present some results on the important properties for the alpha beta norm and upper bounds for the said norm, from which we obtain bounds for the numerical radius of operator. Some other results are also given. Remark. Let I is an identity operator. We can verify that this equality, where alpha and beta are positive, which alpha beta are not nil. And if alpha plus beta equal 1, we find alpha beta norm of A equal 1 equal norm A. Proposition. The alpha beta norm on pH satisfies the following properties. 1. For any lambda in complex space, then we get this equality. 2. If U E pH is an unitary operator, then we get this inequality. Proof. For every bounded linear operator, T defined defined on complex Hilbert space from the definition of alpha beta norm, where alpha beta for non-negative real scalars, alpha beta are positive such that alpha beta are not null. 1. Let lambda in complex space, we have this equality clear. 2. Let U in pH is an unitary operator. By using some equalities and inequalities, we get the required inequality. Theorem 1. Let T be a normal operator in pH. T star its adjoint. Then we get this equality where alpha and beta are positive, which alpha and beta are not null. Proof. Let T is a normal operator using the definition of the alpha beta norm and some inequalities we have. On the one hand, we get these inequalities. Proof. By using some equalities and inequalities and lemma 1, on another hand, we get these inequalities, so we get the proof. Theorem 2, let T as R in pH such that T commutes with S and R. Then we get these inequalities where alpha and beta are positive, with alpha and beta are not null. Let X in H norm X equal 1 using the definition of the alpha beta norm and lemma 2, we get the proof of the previous theorem. Using the previous theorem, we get this corollary. Corollary 1 using equation 1 and lemma 3, namely this equality, we obtain the following equality. Theorem 3. Let A be X in pH such that A and P are positive. Then we get this inequality where lambda are between 0 and 1, which alpha and beta are positive and alpha and beta are not null. Proof. Let X in H be a unit vector by using the definition of the alpha beta norm and the equalities and inequalities and lemma 5 and lemma 4, we get the proof of this inequality. Corollary 2. Let lambda tilde be the generalized alleged transformation of T such that U is the unitary, which the polar decomposition of T. Then we get this inequality where lambda between 0 and 1 with alpha and beta are positive and alpha and beta are not null. Proof. If we take A equal B equal absolute value of T and X equal U in theorem 3, by using some simplification, we get the required equality. References. These are the references which we use to get these results. Finally, thank you for your attention.
Thank you, Professor Gamala. Dear attendees, is there any questions or comments? Please use question answer section. I think there is no question or comments. Thank you, Professor Gamala.
Sure.
Dear attendees, we take a break until 11:25. Thank you. Dear attendees, for the next presentation, I would like to invite Professor Samet Sarıoğlan to do his presentation. Professor Sarıoğlan is coming from Hacettepe University of Turkey. Professor Sarıoğlan, welcome.
Welcome.
Title of the talk is Freeness of Generalized Spline Modules on Cycles over Bivariate Polynomial Rings. Professor, can you share your screen, please?
Yes. Is it okay?
Yeah. Professor, you can start now. You have 15 minutes.
Okay, thank you. I hope the sound and the video is okay.
Okay, everything's okay.
Yeah. So, hi everyone, welcome to my talk. As you can see, first of all, actually, I would like to thank the organizers for this conference. As you can see on the title, I'm going to talk about the freeness of an algebraic structure, which is called generalized splines. And this is a joint work with Professor Selma Altınok. Before introducing the fundamental concept of this talk, we need another notion, which is called the edge-labeled graphs. Let G be a connected finite graph. Here, V is the set of vertices, E is the set of edges of G. R be a commutative ring with identity. I denote the set of ideals of R, and alpha is a function that labels each edge of G by the ideals of R. We call alpha an edge labeling of G. The pair G alpha is called an edge labeled graph, and the ring R is called the base ring. Let me give an example like this. Here we have the tree cycle as the graph, and the base ring is integers here. As you can see, the edge label on this edge, V1, V2, is the ideal generated by 7. The edge label on this edge, V2, V3, is the ideal generated by 2. And you can see the other edge label like this. To simplify the demonstrations, we don't use the generator brackets. We just write this one. We just use the generators of the ideals. Now we can give the definition of generalized splines. A generalized spline is a vertex labeling on an edge labeled graph G alpha, such that for each edge UV, the difference on the adjacent vertices is an element of the corresponding edge labeling ideal. Let me give an example like this. Just consider the first edge labeled tree cycle. A generalized spline on this graph can be given by 2, 16, and 26, which means that we can just label V1 by 2, we can label V2 by 16, and we can label V3 by 26. Now you can see the spline conditions like this: FV1 minus FV2, which is 2 minus 16, which is equal to minus 14. And this is an element of the edge labeling ideal generated by 7. And the other spline conditions also holds like this. We can talk about the algebraic structure of generalized splines. The set of all generalized splines on G alpha with base ring R is denoted by RG alpha. And this set has a ring structure with component-wise addition and multiplication. Also, this set has an R module structure with component-wise addition and scalar multiplication. After giving the algebraic structure of generalized splines, we can talk about the motivation of the theory. As you can see in here, we just solve a puzzle on a newspaper, something like this. What it comes from, I can talk about it right now. Assume that we have a GKM manifold X, which is a manifold equipped with a nice torus action, and the name is given by the three mathematicians, Goreski, Kotwitz, and McPherson. The generalized splines arises from the algebraic topology and algebraic geometry. If you have a GKM manifold X, you can find its moment graph Gx alpha, which is an edge-labeled graph. And then the equivariant cohomology of X is just the same as the generalized splines on Gx alpha with the base ring, polynomial rings with complex coefficients. Details on this motivation of the theory can be found on the paper of Juliana Chimosko I can just put it on the references. You can see it. So now we can talk about the main concept of this presentation. We first define a submodule of Rg alpha, which is MV. If we fix a vertex V, the submodule MV is defined as the generalized splines such that the component on the vertex V is 0. We call this submodule by MV. By theorem of Juliana Chimoska and the others, we have Rg alpha is direct sum of R, the base ring, and the submodule MV. We can just know this equality. Let me give an example right now. Just consider the edge labeled graph again. Just fix V1, the vertex V1, then MV1 is given by these two generalized splines, which means that the generalized splines on this edge labeled graph, whose component on V1 is 0, is generated by these two splines. Okay. We have now another definition, which is the edge label ideal. Given an edge label graph G alpha, we define the edge label ideal IG by all the edge labeling ideals like this. Alpha UV, UV is in the edge set of G alpha. Now we have two short exact sequences. The first one is canonical short exact sequence, which is much more clear, I think. IG, from IG to R, the base ring, and from R to the quotient ring, R over IG. And we obtain from here, from this short exact sequence, projective dimension of IG is just equal to projective dimension of this quotient module minus 1 if projective dimension of this quotient module is greater than 0. We have another short exact sequence like this. Here comes the MV actually. Another short exact sequence can be given as follows. From MV to Rn. Here n is the number of vertices of G alpha, and from Rn to Ig, which is the edge label ideal. And here we have projective dimension of MV, the submodule, is just equal to projective dimension of Ig, the edge label ideal, minus 1 if projective dimension of Ig greater than 0. Now we have the main result of this talk. Assume that R is the polynomial ring with two variables and G is a cycle, then Rg alpha is a free R module. Let me explain the proof. Let me give the sketch of the proof actually. First of all, projective dimension of R over Ig, the quotient module, is less than or equal to 2 by the Hilbert-Syzygy theorem. Then if projective dimension of this quotient module is positive and projective dimension of Ig, the edge label ideal, is positive, we have this equality, which means projective dimension of MV, the submodule, is equal to 0, which means that MV is a projective R module since the projective dimension is equal to 0. Then Rg alpha is also projective since Rg alpha is a direct sum of two projective modules. And finally, Rg alpha is a free R module by Coulomb-Suslin theorem. Because of all free modules are projective, we know it, but not all projective modules are free, except if the base ring is the polynomial ring, which this is the statement of Coulomb-Suslin theorem actually. So we have some examples. The first one is if G is not a cycle, then Rg alpha may not be free, even the base ring is Kxy, the polynomial ring with two coefficients. Here is the example. And also, if R is not the polynomial ring with two variables, then Rg alpha may not be free, even the graph is a cycle. How do we know this one or this one is not free? We can use some computer-aided softwares like Cocoa or Macaulay 2, and this gives us the freeness of these computes, some computations, and gives us the results. Also, one last word I can talk. Our results are not limited with cycles or the polynomial ring with two variables. We can extend our results to some type of graphs and to multivariable polynomial ring under some restrictions, but we have only 15 minutes here, and I think that's all to talk. Here are my references, and thank you all for your attendance.
Thank you, Professor. Dear attendees, is there any question or comments? Please, you can use the question answer section. I think there is no question or comments. Thank you again, Professor.
Thank you.
Dear attendees, we take a break in 10 minutes. Thank you. Dear attendees, for the next presentation, I would like to invite Professor Mustafa Soyertem to do his presentation. Professor Soyertem is coming from Uşak University of Turkey. Professor Soyertem, welcome.
Thank you, Professor.
The title of the talk is Reduction of Exhausters by Set Order Relations and Cons. Professor Soyertem, you can start now. Your time is 15 minutes.
Thank you. This is a joint work with İlknur Atasever Güvenç and Didem Toskan from Eskişehir Technical University. First, I will give some main character of the talk. I will start with the preliminaries, motivation, and reduction of exhausters for constrained case and unconstrained case. Here are some basic notations and definitions we used in this presentation. Here is the definition of contingent con, which is very important for our study. Algebraic sum and Minkowski difference of sets also given by this way. Partial order relations for sets is given here. And this is a partial order relation for non-empty bounded subset of Rn. Here's the definition of minimal sets for a family of sets. Here is the definition of upper and lower exhausters and generalized upper and lower exhausters, which are used for constraint optimization problems. The motivation of this talk is the reduction of exhausters, because exhausters are very useful tools for checking the optimal conditions of a point. So dealing with small exhausters or less exhausters are very important for using exhausters. Here's the definition of smaller exhauster by inclusion and the minimal exhauster by inclusion. This is a general definition of a constraint optimization problem. And here is an optimality condition given for this optimality problem. This is the Hadamard upper and lower derivatives for that optimality condition. And here is some important properties of sets and cons. Reduction of exhausters is a very important, as I said before, but for constraint case, the derivative and the con with respect to that derivative changes. Here we give examples for Hadamard upper and lower directional derivatives as in given the previous lemma and contingent con. But this can be adapted to other optimality conditions also. Here we will use these notations to avoid some misunderstandings. Here's the our first theorem with respect to M1 order relation if C1 and C2 are elements of generalized level exhaustor A star, and if we have this relation, which means C1 is less than or equal to C2, then we can omit C2 from the exhaustor and still use the exhaustor for optimality conditions. Here's an example. We use this theorem as an application. Here is the function, and the set S is given in this way in R2. And an exhaustor is given by two sets, A and B, which are closed both with radius 1. First one center at 0 and second one 1, 0. Here is the geometry of this set of points, and the K is the negative dual of the contingent con. Here are the elements of generalized exhaustor. and this is the A minus B, the point of A minus P, which is an element of K. So we can say that B is less than or equal to A, hence we can omit A from the A star, and still it is a generalized lower exhaustor of H. The immediate result of that theorem, we can reduce a lower exhaustor to a set if this set C0 satisfies this condition for all other sets. But this may not be the minimal elements of A star may not be the minimal by inclusion. This example is given in this way. As you can see, we have closed balls at centers at unit circle in first quadrant, and these cannot be compared with respect to M1 order, but still we can omit some sets from this lower exhaustor, and still it can satisfy the optimality conditions. So minimality doesn't require the being the minimal exhaustor by inclusion. We can use the M2 order relation with this relation with M1 and M2 for upper generalized exhaustors, and these are used for maximal elements of exhaustors. We also give the extend our results to unconstrained optimization problems. As you can see, we give this here this property. If it is satisfied, we still omit and set from the exhaustor. I will explain this theorem on an example. Here are the function H, positive homogeneous function, and the lower exhaustors have three sets, A, B1, and B2. We can show them in here, as you can see, B1 and B2. These points are the Minkowski difference from A to A minus B2 and A minus B1, and these are the sharp sets of these vectors, and the union of these sets is equal to R2. Hence, it satisfies this relation. So we can conclude that we can omit A from A star, the lower exhaustor, and it is still a lower exhaustor of positive homogeneous function H. Yes. This is another example. I want to also outline, this is a result which cannot be obtained with theorem 2.6 in the reference in 3, which was a work of Roshina. This is another example, a similar function, positive homogeneous function. A star is the, again, unit circles which center at x zeros. X is from -1 to 1. And we can say that if we have x1 less than x2 less than x3, we can get these sets, which is also a lower exhaustor of H. Here I will give the geometry of these sets. You can see this red dot is Bx21 Minkowski difference, Bx31, and the blue dot is bx2 1 Minkowski difference, bx1 1, and these sets are the negative dual cones of these points. As you can see here, still the union of these sets are R2. So we can say that we can omit any point, any set, middle of the other sets. This representation, but this cannot be obtained with the results of the fifth reference. And we get these statements are true. And as a result of this lemma, with our theorem 18, we can get that we can omit the set A from a lower exhauster if they satisfy this condition. Here are our references we used in this study. Thank you for your attention.
Thank you, Professor.
Thanks.
Dear attendees, is there any question or comments? Can you use question answer section? I think there is no question, Professor. Thank you so much. Dear attendees, we have a little break. Thank you. Dear attendees, for the next presentation, I would like to invite Professor Firdouz Ahmet Mala to do his presentation. Professor Mala, I think Professor Mala, it seems to that Professor Mala is not with us. Okay. Dear attendees, the next session will be continued by my colleague Figen Takılmutlu after a short break at 12:30. Thank you.
Good afternoon, everyone. Welcome to this session. I am Figen Takılmutlu. Now, I would like to invite Professor Niovi Kayopoulou from Research Institute for Fundamental Sciences TÜBİTAK in Turkey. We are really proud of her contribution to our webinar. She has over 230 publications with 1,700 citations. The title of her talk is on hypersemigroups. Professor, you are welcome to do your presentation, please. Professor Kayopoulou, can you hear me?
Konuşmamın başlamadan önce beni duyuyor musunuz?
Duyuyoruz hocam, buyurun.
Evet. Konuşmamı başlamadan önce TÜBİTAK Başkanı Sayın Profesör Doktor Hasan Mandal ve Türk Matematik Dergi Baş Editörü Sayın Profesör Doktor Adnan Tercan Bey'e bu değerli web semineri için ve ayrıca beni davet ettikleri için onur duyar, çok teşekkür ederim. Şimdi konuşmaya başlayayım. Bu makaleyi görüyor musunuz?
Ekranınızı göremiyoruz şu anda. Kameranızı açabilir misiniz acaba?
Bu makaleyi görüyor musunuz şimdi?
Hayır, görmüyoruz hocam. Ekran paylaşımı yaparsanız eğer aşağıda yeşil bir ok var. Share screen.
Start videoyu mu?
Evet hocam, start video.
Evet.
Evet, şu an sizi görüyoruz hocam ekranda.
Beni görüyorsunuz ama makaleyi görüyor musunuz?
Hayır, görmüyoruz hocam.
Görmüyor musunuz? Ne yapacağım görmeniz için?
Hocam aşağıda ekran paylaşımı ya da share screen var, aşağıda yeşil bir ok.
Share screen mi?
Evet hocam, ona tıklarsanız.
Tıkladım ona.
Evet, buradan sunumunuzu seçin hocam. Ekranınızı paylaşın, okey derseniz.
Ay nasıl yapacağım şimdi ben?
Hocam arkadaşlarımız sizin ekran paylaşımını alsın isterseniz.
Ben yardımcı olmaya çalışayım. Sayın Nevan Hocam, sunumunuz açık mı şu anda?
Büsbütün bozuldu bu.
Açık hocamın Zoom'u şu anda.
Görüyor musunuz?
Sunumunuz açık mı hocam?
Makaleyi görüyor musunuz?
Hocam görmüyoruz da ekranınızda şu an sunumunuz açık mı? Kendi ekranınızda.
Ay bilmiyorum. Siz bu makaleyi görüyor musunuz? Ben görüyorum. Görüyor musunuz siz?
Evet.
Bir saniye.
Ay nasıl olacak şimdi bu?
Ya hocam bir saniye müsaade edin. Murat Bey arka planda halletmeye çalışıyor.
Bize makaleyi e-mail ile atarsanız hocam paylaşımı biz yapabiliriz. Siz ilerleyin dedikçe ilerleyebiliriz isterseniz.
Makale açık.
Hocam
Evet.
e-mail atabilir misiniz makalenizi hemen PDF'ini?
Şimdi bakın.
Tamam hocam, gördük şu anda ekranınızda.
İyi, güzel.
Buyurun hocam konuşmanız için tekrar.
Çok teşekkür ederim. Çok teşekkür ederim. Şimdi abstraktan mı başlayayım? Vaktimiz varsa abstraktan başlayalım.
Hocam, yaklaşık 1 saat vaktimiz var. Buyurun.
This is from the paper Hypergroups Canonic Value and Hypervalue by Ritos in Mathematica Japonica. The concept of hypergroup, makaleyi iyi görüyor musunuz?
Hocam görüyoruz. Buyurun devam edebilirsiniz.
The concept of hypergroup introduced by Marty is as follows. A hypergroup is a non-empty set H endowed with a multiplication such that this one holds this and this. The first condition expresses that the multiplication is an hyperoperational H. In other words, the composition of two elements is a subset of H. It is very easy to prove that for any x, for any this, we have this one is non-empty. Although according to Ritos, it's very easy to prove that this is not possible. The notation this has a meaning, of course, if we identify this one with this and define an operation between sets. The authors working on the parsing groups aided in the definition by Ritos the following. This means this, not given by Ritos. But we never use this last equality in the papers on parsing groups, in which we always use this one. As a result, most of the results of ordered parsing groups are copies from corresponding results on ordered semigroups, in which the multiplication has been replaced by circle. According to the recent bibliography, (197 till today), the theory of parsing group is one of the most active fields of research in the area of hyperalgebraic structures, having many applications in automata, probability, geometry, topology, cryptography, encoding theory, lattices, binary relations, graphs, hypergraphs, theory of fuzzy and graph sets, and other branches of science such as biology, chemistry, and physics. See, for example, the book by Davos and the review of this book by Jiang Dang in Mathematical Review and by Dariush Haidari in Central Plat. Also, you can see the review of another, of a paper by Corsini by Jiang Dang. The aim of the present paper is to give the right information about the structure. This is from Central Plat, Barthi. Bunu görüyorsunuz, Marty'nin review'su. Ona bakın, ondan sonra devam ederim. In all published papers on ordered parsing group, almost all published papers on this structure, related or not, correct or not, are cited in references. Information on ordered semigroups from which the results on ordered parsing group are obtained are omitted, and the introduction is the same in all of them. Begin with Marty, then hundreds of papers appeared, etc. Can you ever imagine something like that in any paper on algebra, groups, semigroups, or in another structure? We have to do that, of course, with special care for survey articles or books, where you have to give complete information about the bibliography, but not for every paper on ordered parsing groups, where the papers using the articles should be cited. The cited articles on ordered semigroup are usually different than the articles used in the papers. Even if they are cited, they are cited among so many not related articles on ordered parsing groups that it is almost impossible for the editors referee to evaluate them correctly. This is the definition of an LA semigroup. It is a semigroup, at the same time a lattice, with a greatest element, usually denoted by E, such that these two properties hold. An ordered semigroup is a semigroup, at the same time an ordered semigroup, ordered set, such that this implies this. Every LE semigroup is an ordered semigroup. We have seen that for many results on LE semigroups, corresponding results on ordered semigroups can be obtained. Then the results on the pair semigroups can be obtained in a very easy way from ordered semigroups. It is enough to prove very few necessary lemmas, like the analogous one for this one of the ordered semigroup in case of an ordered pair semigroup. Most of the peoples on ordered semigroups can be transferred to ordered hypersemigroups. It is just a transfer, useful for students and nice structures, but one can never say that it is something important, as there is no any independent original idea in it. All the results come from ordered semigroups. Every example can be obtained from a corresponding result on ordered semigroup, but many results, not to say all, in the bibliography are based on definitions without any sense. This is from Ritos, his paper published in Mathematica Balkanica in 1971. The notion of hypergroups due to Frederick Marty is the following. A hypergroup is a non-empty set endowed with a multiplication such that for every this x, y, z, and h, we have first this, second this, and third this. And he also writes that it is very easy to prove that if this is non-empty, this is non-empty for every x, y, in h. Duyuyor musunuz beni?
Duyuyoruz hocam, buyurun.
Teşekkür ederim. As one can immediately see, this definition has no sense. And certainly it is not possible to prove that x, y is non-empty. It is no sense because x is an element, y is an element, and xy is a subset of h. Then here x is an element, and this product is a subset. And according to one, this is not possible. So there is no any explanation in his paper what the second and third conditions mean. If I accept that this is true, then these they are not true. There is no any explanation in his paper what the second and third conditions means. In the same paper, Ritos defines the hypergroup using addition instead of multiplication as well, and gives the first and the second definition as follows. As you see, if this one is true, then it has no sense, any meaning, because this is an element, this is a set, and according to one, both should be elements. This theory of hypersemigroups actually began in 1969 with Ritos and Corsini in this sense. Earlier, some Marty worked on this subject, but in a completely different way, mainly on projective geometries and descriptive geometries and multigroups. To pass from a semigroup to an ordered semigroup, we have to put circle instead of multiplication of the semigroup. To see the connection of this definition with the definition of semigroup, let us write down the well-known definition of semigroup. A semigroup is a non-empty set for which there exists a mapping that is an operation on S such that is associative. If we get this definition and put circle instead of say dot, then we have the following. An hypersemigroup is a non-empty set for which there exists a mapping such that this holds for every ABC in X. Since the mapping, this mapping assigns to each element a non-empty subset and not an element of S, is called hyperoperation. It might be called operation as well. Operation clearly means that this property holds 1 and 2. According to the recent bibliography, beginning with Corsini in 1972, this means that this, not given by Mitas, while the property 1, 2 is written just to explain what this one means. Otherwise, we had to stop at this point and no further investigation on hypersemi groups was possible. But we never use this property in the text, in which we always use this one, always. If we use this one, then no problem was ever possible. But we never use it, never. In a report of one of my papers, the referee said something not related, and then he concludes that the meaning of writing this is very, very clear and correct. If the meaning of this property was true, then for any elements of S, we could write, of course, this. But this property is just a notation for which an explanation is needed. We mean it is not enough to replace the multiplication of a semigroup by the circle of the hypersemigroup to pass from a semigroup to hypersemigroup. So this condition should be written in a suitable way to pass from semigroups to hypersemigroups. This being so, the following should be noted as the first step to correct this property. S A is an element, B circle C is a set, and this one an operation between elements. This in property 1, has no meaning. The expression this has no sense as well. Operations between elements and sets are considered as the same operation in the bibliography. We can do that if this is just a definition or if it is convenient for the article. But we can never do that for a paper on ordered hypersemigroups or hypersemigroup hypergroups, where the two operations are used continuously at the same time in the same result. These are from the reference of submitted paper of mine. Referee, I do not understand what the author is trying to say. But really, these are the same operations. Another referee, I do not understand the meaning of this paper. These two hyperoperations are the same. So why this strange notation? The other referee, unfortunately, these new operations coincide with the old one. No any difference between these two operations. Another referee, as in groups, the star operation should be identified with a basic operation. I mean that people working on hypersemi group believe that two operations are the same. In spite of that, phrases like the operation is extended to subset of S in a natural way S, or if AB are subset of S then this, make this very simple definition not understandable. In what sense the operation this between elements has been extended in a natural way to subsets? It is natural extension for a semigroup where AB is defined as like that. but there is no any natural extension for any hypersemi group dealing with sets and elements at the same time. What that then means? Is it a conclusion? Is it a definition? For a group 8, we have one operation corresponding to each element, the unique element AB of S. For an entire group 8, we have two operations. One of them is the operation between the elements of S, called hyperoperation, and the other is an operation between subsets of S. According to the bibliography, this is this. But what is this? We are not in a semigroup where the meaning of this is clear and simple. In order to be a semigroup, this is this. This is this. This is this. And this is this. And this, after proving the associativity of circle that it first appeared in 2015. We use the term left ideal, right ideal, bi-ideal, quasi-ideal, instead of rough hyper-ideal, bi-hyper-ideal, etc. And this is because in this structure, there are no two kinds of left ideals, for example, to distinguish them as left ideal and left hyper-ideal. The left ideal in this structure is that one that corresponds to the left ideal of semigroups, to left ideal elements of an elite semigroup. First of all, the definition of the hypersemigroup in the bibliography should be corrected, and the aim is to show that it is not enough to get the proof of a result on ordered semigroup, to replace the multiplication by circle and to pass to an ordered hypersemigroup. From every result example of an ordered semigroup given by a table of multiplication and an order, in a very easy way, a corresponding example on an ordered hypersemigroup can be obtained. So we do not have to search for such example directly for an ordered hypersemigroup, which is a much more complicated structure. For any such example, reference to the original example on ordered semigroup should be given. If we get an example on ordered semigroup given by a table of multiplication and an order, and delete one of its elements so that it is again an ordered semigroup, then still the corresponding example of ordered hypersemigroup does not belong to the authors of hypersemigroups, and a proper citation should be given. This is the definition. Now, an hypersemigroup, group 8, is a non-empty set with an hyperoperation and between elements of S and an operation between subset of S such that this one holds. As a consequence, we have these two properties that we use very often. If X is an element of this, then X is an element of AB for some, and this, the other one. From this two property holds, and we use it very often. On the other hand, this one holds. The singleton X, this is equal to this. So, in group 8 is called hypersemigroup if this one holds. If it is convenient and no confusion is possible, we can identify the singleton X with its element and write for short this one. For two non-empty subsets of H, we write this if and only if this one holds, and then we can define the ordered hypersemigroup in a natural way as an hypersemigroup in which this one holds. This means for every set of these elements, there exists for every U in this, there exists a V in this, such that U is less than or equal to V, according to this one exactly. Before we start working on this subject, we have to show that this operation is associative. This first appeared in 2015. This is very essential since under this associativity relation in an expression of this form, we do not know where to put the parentheses. And this one has been first proved in Lobachevsky's Journal of Mathematics, but a very simple proof is as follows. You see, here we use both the circle and the star. Every semigroup is an hypersemigroup with this operation, and also with this operation, Every ordered semigroup with this operation is an ordered hypersemigroup, and with this operation is again an ordered hypersemigroup. We consider the semigroup given by table 1. From this proposition, this is not necessary to say it because it is very simple. From this applying proposition to this proposition, we have, according to the first part, we have this ordered semigroup, and according to the second part, this ordered semigroup. It has been proved by Corsini, Shapir, and Mahmoud that every ordered semigroup with the hyperoperation is an hypersemigroup. This is very important because if we have, this is very important, and I have proved that these are not only hypersemigroup, but an ordered hypersemigroup. Many examples on ordered hypersemigroup in the bibliography have been obtained by ordered semigroups, while the papers from which this example has been obtained are usually not cited in references. We will give few of them. According to examples by Farouk, Khan, and Dawaz in soft computing, the set S endowed with the hyperoperation given by table 4 and figure 1 is an ordered hypersemigroup. This is also an example by Corsini, Shapir, and Mahmoud in Iranian journal. We observe that this is not an hypersemigroup. This is not an hypersemigroup. If this example were true, then it should be constructed by the ordered semigroup given by this table and figure 1. And figure 1. But table 5 does not define a semigroup. Using the light associativity test, we can see it immediately by this table. Apparently, the authors of the above two articles constructed the example from a published example on ordered semigroup, deleting one element, presented it as their own, and have not observed that that was not an ordered semigroup anymore. According to example by Tang, Davaz, and G, for this example, the authors refer to Bioalgebraic and Davaz. According to example by Davaz, Tang, Davaz, and G, with a small amount of effort, one can verify that these sets are quasi-ideals of S, but these sets are not ideals of S. It is not necessary to verify anything, since this example has been obtained from ordered semigroups given by table 6, and figure 2. And has the same right-left bi-ideals and quasi-ideals with the ordered semigroup. I have published it in Turkish Journal of Mathematics. According to example by Bioalgebraic, Vanatuk, and Davaz, the table of figure 9 of table 9 and figure 2, where is the figure? Table 9 and figure 3. Define an ordered pair semigroup. The authors refer to Corsini, Shabir, and Mahmoud. The same example is the example 2 in Tipa-Kutoh, Bioalgebraic, who refer to Bioalgebraic Davaz. While this example has been obtained in a very easy way from the example given by table 10 and the same figure 3 that appeared in Mathematica Japonica. The authors present it as their own. According to an example by Farooq Khan and Davaz, this set endowed with the hyperoperation given by table 11 and figure 4. Table 11 and figure 4. Is an orderly pair semigroup. There is also the example 4 in Jambaz Davaz. It is the example also work by Kamali Davaz. According to Jambaz and Davaz and to Kamali, Ardegani, and Davaz, it is easy to see that the quasi-ideals of this orderly pair semigroup are these sets. The orderly pair semigroup has been constructed by the ordered semigroup given by table 12 and the same figure 4 in the way indicated in proposition 2.6 and published in Mathematica Japonica. In fact, it is not easy to check that this is an orderly pair semigroup or to find the sets of quasi-ideals of S, while one can see it immediately without any effort directly by the example of ordered semigroups published in Mathematica Japonica, not cited in the above articles by Davaz et al. If we have the same pair semigroup with this order, it is still an ordered pair semigroup. According to example 7 by Bioalgebraic Davaz, one can show that the table 13 and figure 6, this table and this figure, define a strongly regular ordered pair semigroup. The authors give right reference for this example, but it is very difficult, not to say impossible, to check that this is really a strongly regular order repair semigroup. Besides, it is not any reason to check it, as it is enough to check the order semigroup from which the example can be constructed. This also has been published in Turkish Journal of Mathematics. The next proposition shows that from every order semigroup having incomparable elements, any pair semigroup can be obtained. This is the proposition. You can have a look at it. If we have an order semigroup and fix to incomparable element A, B of S, if such elements exist, and define an inoperation as follows, then this is any pair semigroup. But this is not an order semigroup in general. For example, if we get the incomparable element E and D, this is an hyper semigroup, but not an order hyper semigroup. But if we get the incomparable elements A and C, according to proposition this, we obtain the table 15, and the figure octo defines an hyper semigroup. One can check that this is not an order, this is an order hyper semigroup. We also have this and this. I mean, it can be or not. It is not an order semigroup in general. It is very difficult, not to say impossible, to make examples on order hyper semigroup by hand, to write programs, or even to check if they are correct or not. Besides, we do not need to do since we can get whatever we like from ordered semigroups. So, for the examples on ordered hyper semigroups, a reference to ordered semigroups should be given, especially as it is difficult to check them by hand, say an example of 5 or 6 elements. If we use an algorithm to do that, then still the reference is needed to be able someone to check if they are correct or not. There are wrong examples in the bibliography. That is a further indication that the referee was not able to check them during the refereeing process, or he just believed they are correct. One of them, I explained one of them, I showed one of them. Regular and intraregular ordered hyper semigroup. An ordered semigroup S is called regular if this one holds. This has been published in 1993. If we want to extend it to an ordered hyper semigroup, then we have to write circle instead of say dot. We write it. But as this one has no sense, we have to write something like that, or that, they are equal. Then this one is a subset of H, this one is a subset of H, and this is an operation between sets, and so this is okay. So this part of the regularity has been written in a suitable way as this. As this is a set, we have to write this instead of A in this one. As this set, but we write it, but then this is a relation between elements. As this is a relation between elements, to transfer it to an ordered hyper semigroup, we have to use the relation between sets. Let us show it this one, and we write this one. And this is the definition for an ordered hypersemigroup. So an ordered hypersemigroup is called regular if this one holds. That means that for every A in S, there exists xt in S such that T is in this set and A is less than or equal to T. An ordered semigroup is called intraregular if this one holds. This has been published in 1993 in Semigroup Forum. According to the abstract by Jambaz Davas, the concept of intraregular ordered semigroups has been introduced and generalized the concept of intraregular ordered semigroups. This is the definition in the above mentioned article. An ordered semigroup S is called intraregular if for every A in S there exists such that this. We see that this is exactly the definition of an ordered semigroup and not the definition of an ordered hypersemigroup. To correct this, first to get the definition of the ordered semigroup, and to put circle instead of shadowed. And we have this one. This one does not have any sense, so should be written as this. This being a set, the R should be replaced to this. This being a relation between elements should be changed to a relation between sets. And so we get this one. What is this one now? A natural definition is the following. This. So the definition of intraregularity is as follows. An ordered hypersemigroup is called intraregular if this one holds. This is an example by Jambaz and Davas. We have an ordered hypersemigroup where the operation and the order is defined by this. Now we have this, and this. You see, apparently the elements X and Z in table 1 are in fact the singletons. Otherwise, table 1 does not define any hypersemigroup. But in this property, they write this. Looking at the table, the x square is the element x. So they write this is equal to x is this egality. But x square is not an element of x, but this set, the singleton x. So this one in E has no sense. According to the definition given in the paper, this property has no sense as well and should be corrected to this. A should be this, B should be this, and C should be this. This example is wrong. That is a further indication that the definition of intraregularity needs correction. There is a mistake in this example, and it is not any hypersemigroup, but this does not affect what we said about the definition of intraregularity. That is always given in this way. This is not any hypersemigroup. It doesn't matter. Most of the results of ordered semigroups can be transferred to ordered hypersemigroup. The published papers on ordered hypersemigroup consist from results transferred from ordered semigroups. Whenever we have a look at any published result on an ordered hypersemigroup, we immediately know that the theorem on ordered semigroup from which has been transferred. There is no any result on published papers on ordered hypersemigroups that does not come from ordered semigroups. Let us give the following some proposition to justify what we say. This is the definition of a poegroupoid. If S is a poegroupoid, at the same time a semilattice, and a right ideal element, a B and left ideal element of S, then this is a quasi-ideal element of S. If we have this, then we can, from this, we have as corollary the case of hypergroupoid as corollary, and then if we can show it for ordered groupoids, this is the proof from an ordered groupoids, and then to pass from ordered groupoids, we do not have to do anything. We have to delete this C dot and put circle instead. This is a theorem by Javas, Tambas, and Davas. This. Whenever we look at it, we immediately say that this comes from a lesson group. The proof, I copied from the paper, the proof is as follows. This does not have any sense. This also does not have any sense. This is actually the result from ordered semigroup in which the C dot has been replaced by circle. Now, if we want to show it in the way they showed it, we can show this one for ordered semigroup. This is the correct. This is the proof from ordered semigroup, and then this is the proof from ordered hypersemigroup. If we want to show it in the way they showed it, but on the other hand, this can be obtained immediately from a less semigroup. This is, if we get this one, then we have the analogous from ordered semigroup, and if we get from ordered semigroup, it is very easy to pass to ordered hypersemigroup. If I do not everything is so the same is so. For example, let us look at this one. Let us be an ordered hypersemigroup. Then we have the following: this and this. We get the proof from semigroup and put this one. Biraz vakti var mı acaba?
Hocam tabii ki buyurun devam edebilirsiniz.
Biraz this is the theorem by Ardegani and Davas, for example. Let S be an ordered semigroup such that this, for all right hyperideal N and left ideal B of S, then S is a duo and this one holds. This also comes from a less semigroup. This is. This is, if we want to show it from order semigroup, this is, and then it is trivial how to pass to order semigroup. If S is a POF semigroup, for example, this is the bi-ideal generated by A. Okay. From this, we can pass to order semigroup. This is the proof. And then it is trivial how to pass from to impair semigroup. This is the theorem by Jambas and Davos. An impair semigroup is left and right sample if and only if does not contain proper bialgees. Its proof, though not written in the best way, is on the line of proposition of a paper of mine joined with Professor Ponizovsky and Chingelis. There is no reference in our paper, but on the other hand, this can be put in another much more easy way as well. This is from Farooq Davas. S is regular if this one holds that these two properties are equivalent. Well, as soon as we look at it, we immediately understand that this is from this. That means that people working on impair semigroup, they take this one and they convert it into impair, but they do not do that correctly. All definitions are wrong. This is by Farooq, Khan, and Davas in soft computing. S is regular, this and this. This also comes from LS semigroup. A POF semigroup is called weakly regular if this one holds. The following are equivalent, this, and this. We can transfer it very easy. We can transfer it to order semigroup, and then we have the analogous one from impair semigroup. A POF semigroup is said to be quasi-simple if A is the only quasi-ideal element of S. This proposition holds, and if we have this one, then we have the corresponding one for ordered semigroups, and the ordered impair semigroup follows. According to Bioalgebraic and Davos, an ordered impair semigroup is called regular if this one holds. This is the lemma 3.2 in this paper. An ordered semigroup is regular if and only this. And its proof is as follows. They give this proof. The correct proof is as follows. This proof given by the last Bioalgebraic is wrong. If S is the regular ordered semigroup, impair semigroup, and B is generalized by ideal of S, then B is the bi-ideal of S. This also comes from the LS semigroup. If S is a regular POF semigroup and B bi-ideal elements of S, then B carré is less than or equal to B. According to people by Jambas and Davos, every quasi-hyperideal of an ordered semigroup is the intersection of a right hyperideal and a left ideal. And this also comes from this proposition. If S is an LE semigroup at the same time as semi-lattice, a distributive lattice, and the quasi-ideal of S, then there exists a right ideal element and the left ideal element such that this one holds. This is from Ardegani, Kamali, and Davas. If S is an ordered semigroup, hypersemigroup, if for all A in S we have this, then this is intraregular. This comes from this. If S is an LS semigroup, suppose for every A in S we have this, then S is intraregular. If we have this one from LS semigroup, then we can pass to ordered semigroup, and this is the corresponding result from ordered semigroup. If we get this theorem for ordered semigroup and put circle instead of shadow in its proof, then this is the theorem by Artegani and Davas in a more general form, because we have shown it by sets and not only for elements. Note, in the paper by Javas and Davas in Italian journal mentioned above, and not only, the authors wrote, we tried to use sets instead of elements in the proof of our results, similar to CAP and 35, this is not mine, of the references. If they know the meaning of this statement, then they should know that the published results on ordered hypersemigroups in the bibliography come from the LS semigroups. Every result in their paper can be proved using sets. This has been said several times. I've published many papers on that. Conclusion. In the present paper, we gave some results on LS semigroups and the analogous results for ordered semigroups. The results for ordered hypersemigroups are the results on ordered semigroups with some explanations. The question is, why is it so? The answer is the following. The correct definition of the hypersemigroup is as follows. But on the other hand, this is equal to this. So the definition of the hypersemigroup can be written in the following way as well. If now identify the singletons with the element they contain, then we can write this one. And if we write circle instead of star, then we have this one. We are then in a semigroup, and we do not have anything to prove, as everything has been proved for semigroups. But certainly this is not a correct way to work. The investigation on ordered hypersemigroup is based first on the correct definitions, 2 on the associativity of star, 3 on some lemma for which corrected proofs are needed, 4 examples that also come from ordered semigroups. So at least the definitions, the necessary few lemmas and references should be given in a correct way. In addition, we have not seen any independent results on ordered hypersemigroups that cannot come from ordered semigroups. According to the bibliography, the hyperstructure is a very important subject, having application in many fields of pure and applied mathematics, and not only. If we search for applications of the theory of ordered hypersemigroups, then we have to search them among the Lie semigroups. That is a much more simple structure. But it is usual to say such things to attract the interest of referees, editors, and authors. As an example, the commutative Abel-Grassmann groupoids are semigroups, while some authors say that an AG groupoid is a generalization of a semigroup. According to a paper published in New York Journal of Mathematics, an AG semigroup is a generalization of semigroup and has vast applications in semigroup as well as in other branches of mathematics. Çok teşekkür ederim.
Hocam biz teşekkür ederiz kıymetli katılımınız için.
Ederim.
Thank you very much for your valuable talk and
Beni davet ettikleriniz için çok teşekkür ederim.
biz teşekkür ederiz hocam katıldığınız için.
Ben say söylüyorum, derginiz dünyanın en iyi dergisidir.
Teşekkürler.
Çalışanlarınız ve bütün herkes çalışanlar şey için, bu dergi için çok iyi gece gündüz çalışıyorlar. Bu hiçbir ülkede olmuyor. En iyi dergi. Onur duyarım bu iyi dergi için.
Çok teşekkürler hocam tekrar katılımlarınız için. Ekran paylaşımınızı kapatabilir misiniz hocam?
Sorular varsa tabii bekliyorum.
Is there any questions, dear attendees and panelists? If you have any questions, please use Ask and Question button. Hocam, there is no question. Thank you again for your participation and contribution.
Again for your değerli mecbuanız için.
Çok teşekkürler hocam.
Çok teşekkür ederim.
Now we will continue with the regular session moderated by my colleague Eda Nur Taştan.
Thank you so much, Figen Hocam. Good afternoon to all the attendees, and you are all welcome to this session. Let me briefly introduce myself. I am Eda Nur Taştan, and I'm so glad to moderate this session. And well, we are going to start first speaker of this session, Professor Fatma Muazzez Şimşir from Turkey. And the title of her talk is that In Memoriam Cem Tezer. And now, I would like to invite Professor Şimşir to start her presentation. Please, you are welcome to do your presentation, Professor Şimşir.
Hello, everybody. May I record my presentation to my computer if you give me the permission?
Please, okay. First of all, you can share your presentation.
Yeah, I will. Okay. Okay. I think, can you see it now?
Yes, we can see it.
Okay, thank you very much. First of all, I would like to thank to the organizers for giving me a chance to speak in this webinar. And it's my honor to give a talk about my beloved supervisor, Cem Tezer. Indeed, 15 minutes is not enough. It's less than enough to even introduce his colorful personality and his mathematical background and how he understands mathematics to the mathematical community. So this will be a really, how to say, short talk, introductory talk for those who does not know him. And it will be a memoriam talk for those who met with him. And I would like to say something in Turkish. Baki kalan gök kubbede hoş bir sadaymış. So Cem Tezer was a fastidious, meticulous, highly idiosyncratic and versatile scientist. Çok titizdi, müşkülpesentti, zor beğenirdi, nevi şahsına münhasır ve bir kişiydi, bir zattı. Without him, Turkish community of mathematics would be incomplete. Our sense of gratitude for his work in various areas of mathematics, history of sciences, literature, music, and his encouragement to do mathematics for only its beauty was hardly unique and even unusual. After he died on 27 February 2020, while working actively at Middle East Technical University, The number of colleagues and former students described the ways in which their studies and indeed their view towards mathematics had been transformed by having known him might have surprised only those who had never met him. In this talk, not only his contributions to mathematics will be classified and summarized, but also his unique and distinguished personality as a mathematician will be emphasized. So, okay, this is a short life story of him. I would like to call it as introductory life story. You can find his article about his life called My Life in the web page of Ali Sinan Sertos, Bilkent University. So from his verse, you can learn about his life. Okay, he was born in Bilecik in 1955, and due to his work of his father, he traveled a lot in Anatolia. He started primary school in Amasya Mersin in 1960, and then he went to, they came to Ankara with his family, and he studied secondary school there, and they went to Elazığ. He loved Elazığ. Yeah, he told me a lot about those years. And they went back to Ankara again, and he finished high school in Ankara Atatürk Lisesi. And then by the advice of his father, he started Istanbul Technical University Civil Engineering Faculty, but he decided to carry out mathematics. He loved mathematics and philosophy from childhood on. And then his father told him that do it this in the perfect place in Cambridge University, and he went to some language courses there, and then his bachelor degree is from Cambridge, and his PhD is from the University of Heidelberg. Generalized solenoids of the dancing type is the title of his PhD thesis. And then from 1984 to 2020, he was actively working in Middle East Technical University. Actually, at this stage of my talk, I would like to share the obituary notice written by his beloved friend and colleague, Professor Hurşit Önsiper. Firstly, okay, I will try to introduce him with his words. Also, I share the ideas of Professor Önsiper, so I would like to put this part. So, he was an outstanding member of mathematical community in Turkey. So he was a scholar of amazing diversity, okay? He was a distinguished mathematician and a teacher with a remarkable energy and enthusiasm. In written expositions, numerous conference, seminar talks, and in private discussions, he generously shared intriguing ideas, questions in math, history, literature, and music. So, as I told you before, his bachelor degree was from Cambridge University, 1976, and PhD was from Heidelberg University. So the influence on Cennet Tezer, of which the rich cultural, historical, and academic heritage he observed in these two outstanding institutions was the main source of inspiration in his academic and intellectual work. This influence led him to a principle which he employed at each stage of his mathematical research. Study only the classical works of the true masters of the field. I heard this sentence quite a lot from him while we were doing our PhD thesis. He was keen to avoid, so to say, reader-friendly mathematical expositions. He was also critical of fashionable techniques, most of which did fade away very rapidly without leading to any substantial progress. So he adored mathematics as a human endeavor. He did not try to comply with the dominating academic attitude formulated in the cliché, publish or perish. On contrary, his attitude was that of masters, few but thrive. His research articles span 4 basic fields, namely topological dynamics, differential geometry, mechanics and the elementary geometry. And yeah, I agree with Professor Ansper that he liked elementary geometry. It was his favorite. He quite often emphasized the neatness, simplicity, and the beauty of the ideas and the techniques in elementary geometry. So the ideas, the methods, and the results in each and every research article of Cem deserve a careful investigation, which I also believe, and everyone believes, that will lead to further interesting research. Actually, he had a great interest in history of mathematics pertaining to the late Ottoman era, combining his deep mathematical insight with his competence in the language and the script in which these articles were written. Cem contributed significantly to the studies on the mathematics of that period. And on several occasions, he was invited to the Dil Tarih Coğrafya Fakültesi at Ankara University. So it's one of the leading departments of history in Turkey to teach graduate courses in the field. And literature and music were two other endeavors which fascinated Cem. His poems, most of them were in Turkish. I will share one of them, a few in English. And he has some unpublished articles on Turkish literature. He again preferred classical over the fashionable. And then he had a trilogy on three famous of the most influential and controversial Turkish poets, Yahya Kemal Beyatlı, Tevfik Fikret, and Mehmet Akif Ersoy. And I shared with him the same passion for music. I, as a student, and all the department members of METE still remember vividly the joy and the pleasure of listening to Cem rehearsing the prelude in the department, occasionally late in the afternoon after the lectures. So I share the apology of Professor Ansper. Okay, I know this talk falls short of reflecting the passion, the accomplishments of my dear supervisor, Cem. And if we listen to this talk, he would point out many shortcomings and most likely would say, okay, kağıt sabırlıdır, the paper is patient. Now I would like to share some pictures from him. This is the famous musician Erkan Oğur, and they are playing music. He is playing bandire, traditional music instrument, with those Ahmet Aydoğan and Erkan Oğur. And he's again with Erkan Oğur and Ercüment Ortaçgil, a famous respected mathematician, Ercüment Ortaçgil, actually the brother of famous musician and singer Bülent Ortaçgil. They were doing music together. Now I would like to share one of few poems in English from him, Chide Me If You Must. And look at this picture. Contrary to his appearances, he had a delicate soul. Okay, I am excited too much. If you ask me, I will share this part of the presentation, the poem. I don't want to read at the moment, actually. But this, if you read it, it describes his delicate soul, delicateness of his soul. Chide me if you must. Yeah. And I communicated with the supervisor of Professor Cem, Wolfgang Kriegel from University of Heidelberg. And he told me that, yeah, okay, the things that I knew, but I would like to share with you. His thesis, he published the results of his thesis, Solenoids of the Van-Bensing type, in Israel Journal of Mathematics in 1987, under the title of The Shift on the Inverse Limit of a Covering Projection. And then his thesis provided the motivation and foundation for some of his later work, in particular for his papers in Quarterly Journal of Mathematics and mathematician Said Sharif in 1999. And this is an important comment. Okay, Tezer's approach in these papers enabled others to obtain further results in this area. Under the heading of small spaces, the dynamics of solenoids as considered by Professor Tezer has become by now a prominent topic. Tezer's findings can be seen as an early contribution to this line of research. Now, I don't read those things, but I classified his publications. So those publications are his contributions to dynamical systems, ergodic theory, and topology. And those two are closely related to his PhD thesis. I like this paper a lot, shape classification of Klein-Bottle-like continuum. Okay, for those who would like to read, just look at mathematical reviews. Yeah, you can just easily find the articles there. And so this one is, it was the fruitful times on fixed points of dynamical systems, and then shift equivalence in homotopy, and then automorphism groups of class of expanding attractors, a technical note on weak shift equivalence, and recent geometric developments in the theory of anaxial diffeomorphisms. These are those articles took their spirit from his PhD thesis, mainly from his PhD thesis. Okay, and in 1911. In the similar spirit, we had we published a paper called "The Natural Occurrence of Shift Equivalence." Okay, together. He shared his excitement and his knowledge about this topic with me. And I'm grateful to him for sharing his knowledge. And let's come to differential geometry and classical mechanics. So, in his paper in French, sur les transformations conformes de la sphère admettant une connexion invariante, conformal transformations of the sphere admitting an invariant connection, he has an outstanding result. He showed that a conformal transformation f of the standard sphere Sn for n different from 1, 3, and 7 admits an invariant connection if and only if it admits an invariant Riemannian metric. Also, it has a nice corollary. Since my time is limited, I skip fastly. So this is my PhD thesis. This is an article which came from my PhD thesis, conformal vector fields with respect to the sociogeometric tensor field. So we show that, let Tm be the tangent bundle of the Riemannian manifold Mg endowed with the sociogeometric capital G defined by the metric on the Riemannian manifold, small g. In this paper, we have shown that we characterize the conformal vector fields on the tangent bundle of dimension at least 3 with respect to the sociogeometric. We show that if Mg is a compact Riemannian manifold with dimension greater or equal than to 3, then a vector field A is conformal with respect to the sociogeometric if and only if A is a Killing vector field with respect to G. Now, this is a nice contribution by him and Tabarrok and Stiliano, not on conversation principles in classical mechanics. So they considered the existence of the momentum on Jacobi conversation laws in classical mechanics from the variational point of view. And okay, his contributions to geometry requires a separate, every work of him requires at least an hour-long speech. Okay, so you can read in Matematik Dünyası his works with Hüseyin Demir. Actually, Hüseyin Demir influenced him a lot. So these are many contributions to the elementary mathematics by him, collaborated by Hüseyin Demir. And he was very keen on publishing the questions asked by American Mathematical Monthly and Mathematical Magazine. Actually, while we are carrying our master's and PhD studies, he was asking questions, especially in topology, from American Mathematical Monthly as a take-home exam questions. So together with Hüseyin Demir, he answered many questions asked there. And the last but the least, okay, this is from Başhoca İshak Efendi's Mecmuayı Ulûm-i Riyaziye. So Journal of Mathematical Sciences, or the Book of Mathematical Sciences. He was an expert on this area. So look at the equation. So I just share a part of it, do not describe the things. And I also would like to share his beautiful handwriting from elementary geometry. And okay, he was very happy to be in Çakılarası Mathematics Village together with Şahin Koçak. Yeah, dear Şahin Koçak. And this is the opening lecture carried by him. Yeah, Şahin Hoca is actually there. And then the mayor of Eskişehir is also there, listening carefully to him. And the last thing, okay, somehow I would like to show the last page, not the full screen somehow. Somehow it doesn't work. So, okay, let me share it again. Sorry, I got too much excited. So, okay, I would like to, I guess this was a payaway sentence from his writings. Yeah, hissi kabilel vuku in Turkish we say. Budalanın önde gideni kendisinden daha zeki pek çok adam bulunabileceğini bir türlü anlamayan kişi değil midir? Bu gerçekten böyle. Ne akil ne de bali olmadan, kemalin kendisini değil, yolunu bulamadan geldim, gidiyorum. And the last thing, I would like to share one of the lectures, just few minutes. Rest in peace. Ruhun şad olsun hocam.
So today I will talk about Theorem of Menelaus. Menelaus, Greek mathematician, lived in the 1st century in Alexandria. It's a simple theorem. It's a theorem of theorem with enormous applications, and all that, because in my opinion, it's one.
Let me show you the blackboard.
Okay. I mean, right. So that's the numerical relation. That's the numerical relation. Is exactly. So I can replace this object by xp to xc, yt to yc. YC.
I miss him. It was an emotional talk for me. I thank you for your patience. If you have any questions, I may answer. Or comments about him.
Professor Şimşir, we are very grateful to you for this valuable presentation in memory of Professor Cem Tezer. And we all remember Professor Cem Tezer with love and respect from here. I would like to thank you once again, Professor Şimşir.
I thank you too.
Okay. Professor Şimşir, could you please stop your screen sharing?
I thought that I stopped. Okay. Oh,
Okay, take your time.
okay. Oh.
Okay, we will continue with the next talk. And now I would like to invite Professor Sinesir Mali Larbi from Algeria to the presentation. Professor Sinesir Mali Larbi, are you here now? Okay, let me check. The planned speaker, Professor Larbi, will not be able to attend our webinar, I think. So we will continue with the next talk. And now I would like to invite Professor Abdelli Manel from Algeria to do presentation. The title of Professor Manel's talk is that well-posedness and exponential stability of porous elastic system with macro temperature.
Good morning.
Good morning, Professor Manel.
It's my paper visible?
We can see your presentation. Could you please share your screen?
Yes.
Full screen, sorry, in full screen.
It's okay now?
Yes, it's okay now. If you are ready, you can start.
Yes. Yes, it's okay.
Yes,
Do you
it's
hear
okay.
me?
Yes,
Yes.
you can start if you are ready.
Yes. Good morning, ladies, gentlemen. Firstly, I would like to thank you for accepting me to be a part in your conference. I'm Abdelli Manel, PhD student from the University of Skikda from Algeria. Our research is divided. I will present to you now this work under the title Well-Posedness and Exponential Stability of Poroelastic System with Microtemperature. Our research is divided into 3 sections. Section 1 is Introduction. Section 2, Well-Posedness of the problem. Section 3, Exponential Stability. In this work, we are in the process of studying the result of the existence and uniqueness and exponential stability of the regular solution of Poro-type system with macrotemperatures and internal distributed delay. We consider the following system. In order to have a well-posed of the problem, we impose the following Dirk-Newman and Dirk boundary condition and these initial conditions, and they provided that the system 1 is exponentially stable if and only if this very important condition satisfying mu by rho equals sigma by g, where the parameter rho is the mass density and g is the product of the equilibrated inertia by the mass density. The functions u, phi, and w are the displacement of the solid elastic material, the volume fraction, and microtemperatures, respectively. These coefficients are positives, constant, satisfying condition 4,
And this condition also is satisfying. 2, 1 and 2 are two real numbers. With this condition, mu2 is positive constant, mu1 is positive constant, and mu2 is positive almost everywhere, such that this condition satisfying. And this initial data belong to a suitable space. Now, in this section, we first prove the existence and uniqueness of the regular solution to problem 1 and 3 by using semi-group theory, introducing the following new variable, which satisfies this equality. So, problem 1 is equivalent to the system with these initial conditions. Introducing the vector, this function where v equal ut and phi equal phi t, system 7 and 8 can be written as system 9, where the operator A is defined by this relation. We consider the following spaces. We will show that A generates a C0 group, semi-group on H. Let these two vectors, and under this assumption, we keep it the Hilbert space H with the following inner product. H is a Hilbert space. In this case, the above inner product is equivalent to the latter inner product defined on H. The domain of A is given like this. Here we have this important theorem. Let this vector in H assume that the hypothesis 5 holds. Then for any initial datum U0 in H, there exists a unique solution U in this space for problem 9. Moreover, if U0 in the A, then U in this space. About the proof, to obtain the above result, we need to prove the following two steps. The A in H is dissipative and AD subtract A is surjective. About the step 1, in this step, we prove that the operator A is dissipative let U using the inner product and integration by parts, we obtain this equality. Now, by using Cauchy-Schwarz inequality, we can estimate this. Therefore, from the assumption 5, we have this inequality, that is, the operator A is dissipative. We pass now to step 2 to prove that the operator ED subtract A is surjective, that is, for any G in H with CQ in the A, satisfying this equality, which is equivalent to the system. Finally, from equation 1 and 3 in system 13, we conclude that V and phi in this space, and it's also clear that Z in this space. Hence, there exists a unique solution U in the A such that 13 is satisfied. Therefore, the operator ED subtract A is surjective. Consequently, the existence result flows from the Hilbert theorem. We pass now to section 2 about stability result. We show that the solution of the system 7 and 8 decays exponentially if and only if this very important condition satisfying. To achieve our goal, we use the energy method to produce a suitable Lyapunov function which leads to an exponential decay result. We can prove that the energy is decreasing. More precisely, we have the following result. Let this vector be the solution of 7 and 8. Assume that mu by U equals sigma by G, then there exists two positive constants, alpha and gamma, such that this inequality is satisfying. In order to prove such result, we need several lemma. We started by this lemma. Let's this vector be the solution of system 7 and 8. And under the assumption 5, the energy functional defined like this, and satisfying this inequality. About the proof, multiplying equation 1, 2, and 3 from the system 7 by ut, phi t, and wt respectively, and integration over 0, 1 using integration by parts and the boundary conditions, and summing that, we obtain this equality. Now multiplying equation 4 from system 7 also by mu2 z, integrating over this interval, we get this equality, which together with the 17 and 5 and using Young's inequality gives us the result 16. Let's now this vector be the solution of 7 and 8. The functional E1 defined like this and satisfies this estimate. The same for the second functional, it's defined like this and satisfying this estimate. The same about the functional E3, E4, and E5, which satisfying this estimate. Now, for some positive constant n, n1, n2, n3, and n4 to be chosen appropriately later, we define the Lyapunov functional by this inequality. Next, by taking into account 16, 19, 21, 23, and 25, 27, we obtain this inequality. Now, we must choose the functional very carefully in order to make them negative. Firstly, we choose n2 like this. Secondly, we choose n1. Then we choose n3 like this. Next, we select epsilon 1 and epsilon 2 small than out, so that this inequality is satisfied. Moreover, we pick n4 larger than out. Finally, once all the above constants are fixed, we choose n large enough such that this inequality is satisfied. Consequently, there exists a positive constant rule such that 29 becomes like this. Then, from 31 and 34, we define this inequality. Moreover, we have the following lemma. For n large nodes, we have this inequality for two positive constants C1 and C2. Finally, recalling 13.5, we get this inequality by simple integration yields this inequality, and using again 13.6, we find this inequality. Thus, we complete the proof of Theorem 3.1. Here are now some references which I used in my work. And thank you so much for your attention. Thank you.
Professor Menel, thank you so much for valuable talk. And dear all participants, do you have any questions or comments to Professor Menel? Okay, let me check. Professor Menel, it seems there is no questions and comments.
Okay.
Thank you so much again for valuable contributions.
Okay, thank you.
Okay, we will continue with the next talk. And now I would like to invite Professor Sneser Molly Larbi from Algeria to do his presentation. The title of his talk is that Three-Dimensional C9 Manifolds. Professor Larbi, are you here? Okay. I can see your name between our participants in Zoom. Could you please open your microphone? Okay. Can you hear me, Professor Larbi? We can see your presentation. Everything looks perfect. Professor Larbi, I guess your microphone is closed. You make sure that your microphone is mute. We cannot still hear you. Okay. Could you please click on the microphone in your screen? Just click on the microphone in your screen, as you can see in your screen. Okay, we can hear you.
You can begin.
Yes, but you should turn up the volume of your microphone a little bit. Increase your volume.
Volume?
Yes, we can hardly hear you.
Now?
Yes, it's okay.
It's okay.
Already you can start.
You can start. Thank you very much. I am Senator Moulay Larbi, Mascara University of Algerian. This presentation is about three-dimensional C9 manifolds. In 1960s and 1970s, the almost compact manifolds were studied as an dimensional content of almost complex manifolds. The worked product was used to make example of almost manifolds. There are different classifications of almost compact.
Sorry, Professor. Sorry, Professor.
Yes.
Sorry for interrupting, but we cannot see your slides.
In the next.
Just change the slide.
Sorry?
Can you change your slides?
Can you change your my computer? Can you change my computer? Can I change my computer into the Prussian science?
Sorry, can you repeat again?
Can you read? Yes, can you? Can I repeat?
Profesörler bir
Professor Larby, can you hear us?
Basically, he wants to change their computer.
Maybe we can continue with the next speaker until Professor Larby is ready.
Okay, thank you, Hande. Because of we have a technical problem, then we will continue with the next talk. And now I would like to invite Professor Nazlı Irkıl from Turkey to start her presentation. The title of her talk is that on behavior of solutions to a logarithmic wave equation with nonlinear dynamical boundary. Please, you are welcome to your presentation, Professor Irkıl.
Hi. I will start my share screen.
Yes, of course.
Okay. It's okay. Can you see?
Yes, we can see. Could you please share your presentation in full screen?
Yes, I know which screen.
Okay.
It's okay?
Yes, it's okay.
Okay, thanks. Hi, dear participants. My name is Nazlı Irkıl. I am attend from Didi University, Turkey. We study with this presentation with Professor Erhan Bişkin. First of all, I would like to thank the committee for giving me the chance to attend the webinar. The title of our presentation is On Behavior of Solutions to a Logarithmic Wave Equation with Nonlinear Dynamical Boundary Conditions. In this presentation, we studied the following problem. I want to give some information about our problems. You can see we can call this type of problem wave equations, and we have initial and boundary conditions for our problems. The first conditions is related with the initial conditions, and the second and the other conditions are related with the boundary conditions. And you can see we have the damping terms, and because of these terms, we can say we have the logarithmic source terms. We studied this problem in a bounded domain, and we call this domain with omega. The omega is a regular domain, and this boundary of omega domain can be called with del omega, and del omega is defined with gamma 0 and gamma 2. And we give some conditions for gamma 0 and gamma 2. You can see at these conditions. And we must have some features for K and P. And you can see K and P big equal to 2. and these constants are positive. And we give some features again about this positive contrast when we study the global existence or the blow-up results. You know, differential equations also play a central role in mathematics. Many problems in science, engineering, medicine are modeled as a differential equations. Therefore, it is very important to find solutions to these problems. But every time we couldn't give solutions for this problem. So we try to find the mathematical behavior of this solution or numerical solutions. When we start to look the literature, we can see there is a lot of work about the qualitative theory of these equations, these problems. For example, we can look for local existence, global existence, asymmetric behavior suggests the decay or growth of solutions, and the blow-up, global non-existence of these solutions is an important area for the mathematicians. In the absence of the logarithmic source term and for negative source term, our problems like one was studied by Chan, Legnus, and Zozo. In the absence of the damping term without UT and for the logarithmic for the source term, if we taken at this form, this problem was studied by Levin and Payne and Levin and Smith in different times. Levin and Payne obtained the blow-up results for the negative initial energy. Levin and Smith studied the global existence under suitable initial conditions. Then later Vicilaro studied our problems one without logarithmic source term, and he take the source term as it's a polynomial source term. And the author obtained local and global existence in bounded domains. Later, they et al. And 2020 near times considered nighttime blow-up of solutions at critical energy level or high energy level. We can say again, at this problem, the authors don't take the logarithmic source term for their problems. Now we can must give information about the logarithmic nonlinearity. Well, equations with the logarithmic nonlinearity have many applications in many branches of physics, such as optics, geophysics, and nuclear physics. The first works was obtained by Bialnitsky, Birula, and Misalski in 1975. It was a classical field equation whose popularity increased, especially when it was shown in Buljan and Birula and Misalski. In recent years, hyperbolic wave equations with logarithmic source term have attracted much attention. In 1980, Jazeneva studied the existence of solutions. The following equation you can see in 2 in R3. Later, Gorka studied the global existence of the SAM equation in the one-dimensional case. There is a lot of works about logarithmic source terms with different problems, for example, for Kirchhoff equations, or Laplacian type equations, viscoelastic terms, and the other studies the different theory of these problems. For example, blow-up, for example, global existence, and we refer the consonant reader for the study of different kinds of this type problem. You can see Chen and Liu, Pishkin and Çalışır, and we study this area very attractive Kapin and Mesudi studies at this area. You can see in our reference. To best of our knowledge, logarithmic equation with dynamic boundary condition has not been studied yet. So our aim is aim in this presentation paper is to extend the blow-up results for this type problem. For this, we must define some norms and unit products and some lemmas which will be used in our proof. Firstly, we denote the norms which is related with our energy functionals, and we define T, and we define Banach space and a supplement of Banach space. You can see in our presentations. Then we define the total energy of functions. It is very important for us. You can see our total energy function of related with the problem 1. We given 3 equal. According to definition of total energy, the initial energy for T equal to 0 can be considered as to 4 equal. Then we will give some lemmas which will be used in our proofs. The lemma is about the Sobolev-Benedict inequality. We firstly give some conditions, and our aim is to show that the norm of P and gamma 1 can be embedding to H gamma 0, and we give this inequality in 5. The other propositions is related with the logarithmic system. Because of we have the logarithmic system, we couldn't use the trace Sobolev-Benedict directly. So we must have some conditions for this. And at these propositions, we give some conditions for this lemma. The other lemma is about our total energy, the differential of total energy, and we can say our total energy is non-increasing function, and we can state this. We can state the function inequality in 3. For the proof of this, firstly we multiplied equation 1 by ut and integrating on this on omega, and we use some green formula, and we have the inequality 6. The other lemma is about logarithmic source term. So our aim is to estimate the logarithmic source term and write these terms as a norm. So we must use the lemma 3, and you can see the following inequality 7. We will use for the global existence and for the blow-up results these lemmas. The local existence, we give the only theorem, but we not give the proof of this theorem in our presentations. We use the Bioalgebraic method and show the fixed point theorem for our proof. In proof, our aim is to show that the every norms can be bonded in a domain, and we can say our problems have a local existence for 0 to t. we considered the theorem for related with local existence suggests. Firstly, we say we give information about T, and then we considered the solution of the weak solution of our problems one at this space, and we give the energy like as like, and we can say T equal to this conditions, and T is decreasing in the first variable. I say again, Fedoraki method will be used, and we try to give an approximation solution for local existence, and then we say the norms of these approximation solutions are bounded so that we can extend the T from the Tm to T, and we can have local existence. We introduce the potential var. Potential var is important for us, and for this, firstly, we define the some useful functionals. The first functionals can be called as a potential functional. The other functional can be called as an Hari functional. By combinations of 8 and 9, we have the 10, and later by the definitions of the total energy, we can the elements equal. The potential space is important. Firstly, we can say the potential wall depth is defined as 12, can be used for global existence. We can say if our solutions U under elements of the W, we can say we have a global existence. The other spaces V, and we can say we use this space for the blow-up results. Then we define the depth of potential well as and D is derived with the potential functional lambda U.
Professor Urkel, sorry for interrupting, but you have 1 minute.
Okay, I will go. We have potential well depths, and in lemma 5 we have root 4 equations. Later we have a proof. You can see at this. I want to come our blow-up results. And the lemma alt is written with the, our potential well depths, and we proved that our that there is a positive contents, and you can see for lower bound for D, and we have a proof. Our aims is to prove the lower bound for blow up time of the problem one. Firstly, I said we must have the that all of the solutions U and UT must be element of V, and we prove this by contradictions. You can see. Later, our the main theorem is suggests we can say the unital unital conditions elements V, and under these conditions over the P, our problem our solutions goes to the infinity when time goes to the T1 minus. And we can have a level one suggests. For this, firstly, we define a function in 21. Then we test the problem one by UT, and we have the 22. By differentiating the HT, we and use this equal, we have 23. Later, because of our conditions, we can have a traceable embedings, and we can attend. We can get this inequality, and for this we use some logarithmic inequality for estimate the logarithmic source term. And biocentric 24 into 23, we have this. This completes our proof. Our reference is suggests. Thanks for your attention.
Professor Erkal, thank you so much for your valuable talk. Dear all participants, do you have any questions or comments? Okay, let me check quickly. It seems that there is no questions, and thank you so much again for your valuable contributions.
Thanks again so much.
And now we will continue with the next talk. And now I would like to invite Professor Jonas Bhatt from India to start his presentation. The title
Yes,
of
ma'am, I'm present here.
Sorry?
Yes, ma'am, I'm present here.
Yes, okay. Let me introduce you, Professor. The title of his talk is that Wigner-Wheel distribution associated with the Cartesian quadratic phase Fourier transform. Okay.
Okay, ma'am, is my screen visible?
Yes, we can see your screen. And
first of all, I would like to thank the organizing committee for providing me a chance to present my talk in this webinar. Myself, Dr. Muhammad Yunus Bhatt, and I am the Assistant Professor at Department of Mathematical Sciences, Islamic University of Science and Technology, Awantipora, Jammu and Kashmir, India. Today, I am going to talk about Wigner-Wheel distribution associated with the Quaternion quadratic phase Fourier transform. So in this talk, we'll talk about these contents. We will have some introduction.
Sorry for interruption, Professor.
Results. Then we will talk about, yes?
Professor, can you click the green circle in your screen for making full screen? In the left part of your screen. Yes.
Okay, ma'am. Thank you.
Thank you very much.
We have some preliminary results. Then we will have, we obtained the Wigner-Wheel distribution associated with the Quaternion quadratic phase Fourier transform. Then we obtained the convolution and correlation theorems for this transform. And lastly, we have some references. So let us start from the introduction part. The quadratic phase Fourier transform that we will denote by QPFT, introduced by Castro and his colleagues, that is given in the references 1 and 2, is the superlative generalized version of the Fourier transform. This novel transform has overthrown all the applicable signal processing tools, as it provides a unified analysis of both transient and non-transient signals in an easy and insightful fashion. The QPFT is actually a generalization of several well-known transforms like Fourier fractional transform, Fourier transform, fractional Fourier, and linear canonical transforms, whose kernel is in the exponential form. As a generalization of the real and complex Fourier transform, the Quaternion Fourier transform QFT is of the interest of researchers in this present area. The researchers community has successfully studied the useful properties of QFT, including modulation, shift, differentiation, energy conservation, convolution, correlation theorems, uncertainty principles, and many more. The Quaternion Fourier transform plays an important role in the representation of multidimensional signals. It transforms a real or quaternionic 2D signal into a quaternionic valued frequency domain signal. The 4 components of this QFT separates 4 cases of the symmetry into real signals instead of only 2 as in the complex Fourier transform. So in this section, we mainly review some basic factors on the quaternion algebra and the quaternion quadratic phase Fourier transform. So the quaternion algebra, this is an extension of the complex number to 4D algebra. It was invented by W.R. Hamilton in 1843 and classically denoted by this fancy H in his honor. Every element of this fancy H has a Cartesian form that is given by this equation, where this Qi belongs to, these are the real numbers for I from 1 to 3, and I, J, K are the imaginary units, and these obey the Hamiltonian's multiplication rules, like I square is equal to J square is equal to K square is equal to -1, and this equation. Let Q this Q naught and Q is equal to this denotes the real scalar part and the vector part of the quaternion number, this Q. Then from the references to entry, the real scalar part has a cyclic multiplication symmetry that is given by this equation first. The conjugate of the quaternion Q is defined by this Q bar is equal to this equation, and the norm of Q that belongs to this fancy H is defined by this equation. It is easy to verify that the bar of PQ is equal to QP bar, and modulus of PQ is equal to mod Q mod P for all PQ belonging to this fancy H. The quaternion modulus of this function space L to R square H are defined by these functions. These are the functions from R square to H with this restriction. We now introduce an inner product of the quaternion functions f and g defined on L to R square H that is given by the inner product is defined by this equation with the symmetric real scalar part given by these equations. The associated scalar norm of f of x belonging to this space is defined by this norm of f is the inner product of f, and this is given by this integral form. So we have lemma 2.1 that is proved in the reference third. If f and g belongs to this function space, then the Cauchy-Schwarz inequality holds here. And if and only if here is a condition that f must be equal to minus lambda g for some quaternionic parameter, this lambda belonging to h. When we have f is equal to minus lambda g, we will have this inequality will be replaced by the equality. So in this next subsection, we will introduce the definition of novel 2D hypercomplex, or this is called quaternionic quadratic phase Fourier transform, which is a generalization of the classical quadratic phase Fourier transform. Because of the non-commutative property of quaternionic multiplication, there are three types of the quadratic QQPFT: the left-sided, the right-sided, and the two-sided QQPFT. In this paper, we mainly focus on two-sided QQPFT. So this definition of QQPFT is given by, let mu s denotes this matrix for s is equal to 1 to 2. Then the two-sided QQPFT of any signal f belonging to this function space is defined by these equation second, where this bold w, this is the tuple and it belongs to R square. Similarly, this bold t belonging to R square, and we have these kernels. These are given by this lambda I and lambda j. These are the two kernels which are given by the equation 3 and 4. So we have a reconstruction formula for this QQPFT, that every signal f belonging to L to R square can be reconstructed back by the formula given by this equation 2.6. Similarly, we have the potential formula for this transform, that if we have two any functions f and g belonging to this function spaces, then the inner product is inner product of these f and g satisfies the equation f, and the norm of f is given by this equation 6. Now here from this section our work starts. In this section we introduce the definition of novel integral transform coined as the Wigner-Willi distribution associated with the quaternionic quadratic phase Fourier transform. This transform is constructed by substituting the quadratic phase Fourier kernel with the quaternionic quadratic phase Fourier kernel in the quadratic phase Wigner-Willi distribution definitions that are given in the references 3 and 2. Further, we investigate some basic properties of this transform which are useful in signal processing. So we first of all we provided the definition like this: let mu s be this matrix as defined earlier, be a given set of real parameters with bs not equal to 0, then the cross Wigner-Willi distribution associated with this two-sided quaternionic quadratic phase Fourier transform for any signals f and g belonging to these function spaces are given by, this Wigner-Willi distribution is given by this equation 7, where this fancy W, this is the tuple that also belongs to here R square, and these are the two kernels which are given by the equations 3 and 4 as defined earlier respectively. So if we take f is equal to g in the definition provided, then we will call it as an auto Wigner-Willi distribution, and this is denoted as fancy omega f mu1 mu2 bold t omega, and is defined by this equation 8. Let us define the quaternionic correlation product given by this equation. Then 7 can be reshaped as given by the equation 9. If we apply the inverse quaternionic quadratic phase Fourier transform on both sides of this equation 9, then we obtain this equation, which implies that this correlation is defined by this equation 10. By varying the parameters, this mu as the proposed transform that we gave in the definition in the equation 7, this boils down to various well-known integral transforms associated with the Wigner-Willi distribution. For example, if we take this matrix mu1 as 0, -1, 0, 0, 0, and mu2 is equal to 0, -1, 0, 0, and 0, we will have the quaternionic Wigner-Willi distribution. And if we take this matrix as cot θ1 minus cosec θ1 cot θ1 0, 0, and mu2 like this, we will have quaternionic fractional Wigner-Willi distribution. Now, prior to investigating the properties of this transform, we will establish its relation with the quaternionic Wigner-Willi distribution. So from definition 4, we obtained this property, which represents quaternionic Wigner-Willi distribution. So in this subsection, we establish some fundamental properties of this transform. These properties are vital in signal processing, and we present some general properties of the novel Wigner-Willi distribution and their detailed proofs. So we first of all, we obtained this theorem that is actually the complex conjugate. For any functions f and g belong to this function space, we obtained this equation 11, where this mu s is equal to this matrix minus as minus bs and so on, for s is equal to 1, 2. We skip the proof here because we have not yet published this paper. Next, we obtained the symmetry conjugation result. So that means that if we have any function f belonging to this function space and it is a quaternionic signal, then we have the equation 12. Next, we establish the non-linearity of this Wigner-Willi distribution, which states that the Wigner-Willi distribution does not satisfy the superposition principle, which is not suitable to the analysis of multi-component signals. So we obtained the non-linearity result for these functions for this transform and the boundedness property for the proposed transform that is given in the shape of these two theorems. So the following theorems guarantees the reconstruction of the input quaternionic signal from the corresponding Wigner-Willi distribution quaternionic phase Fourier transform within a constant factor. So we have provided in this paper, we have obtained the reconstruction formula, how we can reconstruct a signal back, and we have also obtained the Mueller's formula for this proposed transform. So next, we have obtained the convolution and correlation theorems for this proposed transform. So convolution and correlation operations are fundamental signal processing algorithms in the theory of linear time variant systems, pattern recognition, signal detection, and optics. In the following, we first define the convolution and correlation for this transform. Then they are the extensions of the convolution and correlation definitions that are already provided in the literature. We then establish the convolution and correlation theorems for the Wigner-Willi distribution associated with quaternionic quadratic phase Fourier transform. But due to the non-commutativity of the quaternionic exponential components and quaternion multiplication, we only establish a special condition of the convolution and correlation theorems for this transform. So we first of all provided the definition of the convolution operator, how we can define the convolution operator for this proposed transform. So as a consequence of above definitions, we get the following important theorem, which invokes the Wigner-Willi distribution to separate the unwanted components appearing in the input signals and see its effect on the convolution given by the equation 17. So we have obtained the convolution theorem, the well-known theorem for this Wigner-Willi distribution quaternionic quadratic phase linear canonical transform. Next, we have, first of all, we defined the correlation operator, and similarly, then we obtained the correlation theorem for this proposed transform. So first of all, we provided the correlation definition for this transform. So we have then the correlation theorem for let f and g belong to L to R square be the two real valued signals. If we assume this a real valued function, then the following result holds, means we have obtained the correlation result for this transform. So the conclusion of this paper is, in this paper, we presented a novel concept of quaternionic Wigner-Willi distribution in the quaternionic quadratic phase Fourier transform settings. Based on the properties of this transform and classical quaternion Wigner-Willi distribution, the relation between these two notions are present. Important properties such as complex conjugate, symmetry conjugation, nonlinearity, boundedness, reconstruction formula, Moyal's formula, Plancher formula are derived. Finally, we have obtained the convolution and correlation theorems for this proposed transform. These are some of the references that we have used for this work. And thanks for your kind attention.
Thank you so much, Professor Bat, your valuable talk. Dear all attendees, do you have any question or comment? Okay, let me check. It seems that there is no question, Professor Bat. Thank you so much again.
Thank you. Thank you.
Okay. Now we will continue with the next talk. I would like to invite Professor Abir Kisha from Algeria to start his presentation. The title of his talk is that New Stability Criteria of Nonlinear, Non-Autonomous Systems.
Good evening.
Good evening. Could you please share your presentation in full screen?
Okay. It is visible now?
Just you can try to click Control L, Control plus L.
The presentation is visible.
Okay, it's okay now. If you are ready, you can start.
Thank you. Good evening, everyone. My name is Kisha Abir from the University of Jijel, Algeria. I am going to give a presentation titled "A New Stability Criteria of Nonlinear Non-Autonomous Systems." This presentation is divided into 4 parts. In the first part, general notations, definitions, and system descriptions are given. In the second part, I will present a direct Lyapunov theorem on global uniform stability. In the third one, I will introduce a converse Lyapunov theorem on global uniform stability. And in the last one is the Ash-linearized stability of nonlinear systems. So I start by consider the nonlinear non-autonomous differential system described by 1, where T is the time, X is the state, and F is locally Lipschitz in X uniformly in T. Let xt equal xt t0 x0 be denoted by the unique solution of system 1 throughout x0 where t equal t0. So we consider now the second system which is the linear time variance system given by 2, where A is a matrix whose elements are continuous functions on R plus. The general solution of system 2 is given by xt equal phi t0 x0, where phi t0 is the state transition matrix associated with A. The following theorem presents the existence and uniqueness of solutions of system 1. We pass now to the meaning of H stability. In 1984, Peto introduced a new notion of stability called H stability with the intention of obtaining results about stability for a weakly stable system, at least weaker than those given exponential stability and under some perturbations. That is, Pinto extended the study of exponential asymptotic stability to a variety of reasonable systems called H systems. The notion of H stability is quite flexible because it includes the classical notions of uniform exponential stability within one common framework. We move now to the definition of H stability. Assume that H is positive, continuous, and bounded function. The system 1 is said to be uniformly H stable if there exists constant C greater than or equal 1 and delta greater than 0 and dependent of T0. That's for all T0 and for all X0 less than or delta. The solution satisfies the following estimation. The system is called globally uniformly H stable if the previous definition is held for all X0 in Rn. Here, HT minus 1 equal 1 divided by HT. From the above definition, we can see that the uniform H stability coincides with non-types of stability like uniform stability, where when HT equal B for all for B positive is a positive constant. The uniform exponential stability when HT equal exponential minus lambda t, where lambda is a positive constant, and the polynomial stability where when HT equal 1 divided by 1 plus t power gamma, where gamma is a positive constant. We can characterize the global uniform H stability of system 2, which means x point equal AT xt, in terms of the transition matrix phi t x t0 in the following lemma. Next, we introduce the definition of uniform boundedness of system 1. A solution of system 1 is said to be globally uniformly bounded if for all eta greater than 0 there exists theta greater than 0, such that if the initial condition is bounded by eta, then the trajectory of the system is bounded by theta. We move next into part 2. First, we give the definition of a Lyapunov function. Let D be a domain that containing the origin, and V be a continuous differentiable function. We say that V is a Lyapunov function if the following properties are held, where V point is the derivative of V along trajectories of system 1, which is given by the following expression. Now we are ready to present the fundamental results of this part. Suppose that H is a positive bounded continuous decreasing function on R+, with H prime exists and continues on R+. Moreover, suppose that there exist constants and the function V satisfying the following properties. Then the system 1 is globally uniformly bounded. The following example is a direct application of the previous results. Consider the scalar equation. We set the Lyapunov function Vtx equal x power 2 and the function ht equal 1 divided by 1 plus t power 2. Our hypotheses of theorem 2 are held, then the system is globally uniformly bounded. We see that the trajectory of the system approach to a compact set when t over plus infinity, and we select here the initial states x0 equal 1. We move now to the third part, and before present the converse theorem, we give the following hypothesis. We state now the converse Lyapunov theorem when the origin is a globally uniformly H-stable equilibrium point for the linear system 2 by defining a Lyapunov function that satisfies certain properties. So the theorem 3 gives the Riccati solution, and theorem 4 is the Lyapunov converse theorem. We arrive to the last part. The existence of a Lyapunov function for linear systems will now be used to prove a linearization result and to determine the uniform stability of the nonlinear non-autonomous system. In what follows, the results of the preceding parts is combined to obtain one of the most useful results in Lyapunov stability theory, namely linearization method. The advantage of this method lies in the fact that under certain conditions, it enables one to draw conclusions about a nonlinear system by studying the behavior of a linear system. So consider the nonlinear non-autonomous system 1, where f is continuously differentiable and D is the domain that contains the origin. Here, we suppose that the origin is an equilibrium point of the system, and the Jacobian matrix is uniformly bounded and Lipschitz on D. We make that ftx equal atx plus ctx, where atx equal the Jacobian matrix in the point of 0, and xtx equal this expression. So the goal is to approximate the nonlinear system 1 by its linearization in a small neighborhood of the origin. The next theorem states Lyapunov's indirect method for showing the uniform stability of the origin in the non-autonomous case. We will see that the uniform stability of the linearized system reflects the uniform stability of the nonlinear system. So let the origin be an equilibrium point of the nonlinear system x point equal ftx, where f is continuously differentiable in the D, which D equal this subset. So suppose that the Jacobian matrix is bounded on and Lipschitz on D uniformly in T, and let's AT equal that. Then the origin is uniformly H power half stable for system 7 if it is uniformly H stable for the linear system x point equal ATX with the H verifies the hypothesis H. The following example is an application on the above theorem. We consider the second order problem, the following second order problem, and the Jacobian matrix of the linear system 8 is given by. So the linear system is uniformly H stable with C equal 1 and HT equal 1 divided by 1 plus T power A, which is verifies the hypothesis H. So by applying theorem 5, the system is uniformly H power half stable. We see that the trajectory of the system tends to 0 uniformly. We state here the initial state x1, 0, x2, 0 by 1, 2, and A equal 3. Here some references have been used. And for more details about the H stability, you can browse the following articles. And thank you for your attention.
Thank you so much, Professor, for your valuable talk.
Thank you.
Do you have any question or comments to Professor? Let me check. I think there is no question, and comment. Thank you so much again for your valuable talk, Professor Kisha. Could you please stop your screen sharing?
Okay.
Professor?
Thank you.
Thank you. Okay, we have come to the last presentation of this session. And now I would like to invite one more time Professor Sinasir Moli Larbi from Algeria to do his presentation.
Yes, I am ready. You can start.
Okay.
You can start. Okay. I start. Okay. Thank you.
Could you please share your screen?
Yes.
Okay.
Okay. It's okay. It's okay now.
Okay, we are waiting.
Yes.
Okay, we can see your screen and everything looks perfect. If you are ready, you can start.
Yes, thank you. Hello, everybody. I'm Sinasir Moulay Larbi, University of Mascara of Algeria. This presentation is about three-dimensional C9 manifolds. In 1960s and 1970s, the almost compact manifolds were studied as an dimensional multifold of almost complex manifolds. The worked product was used to make examples of almost manifolds. There are different classifications of almost compact structure in reference number 3. Chenia and Gonzalez have defined 12 classes of almost metric manifolds. According to reference number 3, in dimension 3, these manifolds are reduced to 5 classes. To class of cosymplectic manifolds, C5 class of beta Kenmutsu manifolds, C6 class of alpha Sazakian manifolds, C9 manifolds, and C12 manifolds. Most of the research related to almost compact metric structure is concerned with the normal ones. That means the first 3 classes. For the last 2 classes, C9, C12, 12, which can never normal, there are a few papers on C12 manifolds. For example, in the reference number 1 and 3.
Sorry for interrupting, sir, but you don't forget to change your slides. Keep your slides.
Yes. Yes. Yes. Now this presentation is devoted to three-dimensional C9 manifolds, which which are never normal. Firstly, we study their fundamental properties and give concrete examples. Secondly, we test such structure in three-dimensional algebra. This work will be according to the following plan. In the first section, we give some definition and properties of almost compact matrix manifolds. In the second, it's about three-dimensional C9 manifolds. In the third, we give 2 examples of C9 manifolds. The last section is for testing the Lie algebra that accept C9 manifolds. Section number 1. Through this representation, always M, G denote three-dimensional Riemann manifolds, and X, Y, Z are vector fields on M. Now, definition of almost contact matrix manifolds is the quantiple M bulky Xi eta G, such that these conditions are satisfied for each X and Y on M. The definition of fundamental 2 phi is given by this expression. The almost contact matrix structure Barfi Xi eta is said to be normal if N1 defined for this expression equals 0, where N phi is given by this expression. Now, this classification of Chinilla-Gonzalez I talked about in the introduction. In this classification of Chinilla-Gonzalez, C9 manifolds are defined by this theorem. C9 manifolds in dimension greater or equal 3-dimensional is defined by this formula. Now, this proposition given the some properties concerned the 3-dimensional manifolds. For proposition number 2 is given equability between these 3 conditions. This condition is important. Now, in the section number 2 concerning the 3-dimensional C9 manifolds, we start by this essential theorem. For any C9 manifolds, we have this expression, nabla Xi alpha Y equal this expression. For prove this property, this equality number 1, you can see the first theorem, and we calculate the two sides. The first side is calculated by this way, and the second side is calculated by this way. We obtain the equation number 5 and the equation number 7. By the theorem number 1, this theorem, we have this quantity equal this quantity. Then we return of the equality number 5 and equality number 7. We obtain your result, this equation. Now we give the proposition number 3 in the 3-dimensional C9 manifolds. We have this expression. We have this expression in any dimension, but in the 3-dimensional, this expression equals this expression, according to Orszak theorem given in the first property. The property number 4, proposition number 4, in the 3-dimensional C9 manifolds, we have this result. Nabla 6 equal 0. For just using the expression number 9, this expression, we put in place x Xi and here Xi. Then we obtain this result. For proposition number 5, we have these properties. Yes, but we have the Roman. According to proposition precedent, the three-dimensional C9 manifold is never normal. But for proposition number 6, in the three-dimensional C9 manifold, we have this polite relation. For proof is easy. And number 7 gives some properties for C9 manifolds. We have these properties. Beta equals 0 and dphi equals 0, and this is your proof for the first one and the second one. Remark: the three-dimensional C9 manifold is almost completely concentric because it's not normal, and dy equal d eta equal d phi equal 0. You can give now the characterization of the three-dimensional C9 manifolds by this formula. The relation number 1 and the relation number 3 is easy to prove this. Now, for the second section, we give some examples. Example number 1 is given in the reference number 4. Let G be the Lie groups of real matrix of the form, this form, with G is metric and the structure, the following structure, multi xi eta. Yes, we can use Cauchy's formula for calculating the connection of Lebesgue beta is given by this formula. And finally, can easily check for each Ig in this set. We have these properties. Hence, an almost compact metric structure, multi xi eta G on G, is of class C9. For the second example given here, G is metric defined by this matrix where rho, Po, and C are three neo-zero functional, and the structure given by this formula, multi xi and eta. Let the orthonormal basis given by E1, E2, Xi by this expression. Using again Cauchy's formula, the neo-zero component of the Lebesgue beta competition are given by these expressions. And we calculate this quantity for I in take 1, 2, 3, we obtain this result. This is yes. And finally, hence is this almost compact metric structure manifolds to be of class 9 if and only if we have this condition. This equals 0 and nabla 6 equals 0. If this is equivalent to this condition, then if the functions rho eta xi given by this expression then my almost contact matrix vector is of class C9. Now, the last section is for testing the algebra of 3 dimensions, but accept C9 structure. For this, here there is the listing of non-abelian 3 dimensions, and using the Gonzalez formula for find the component of the Levi-Civita connection. For each algebra, we have this result. For algebra A31, there exists one C9 structure on this algebra with Xi equal E2. For A32, there exists no C9 structure in this algebra. For A33, there exists also no structure C9 constitution. For A34, there exists one C9 structure with C equal 0. For the next A35, there exists no C9 structure in this algebra. For the algebra A36, there exists one C9 structure on this algebra with Xi equal 3. For the A37, A38, A39, there exists no C9 structure. Finally, this page is for some preparation. Thank you for your attention.
Professor Larbi, thank you so much for your valuable talk. Dear all participants, do you have any questions or comments to Professor Larbi? Okay, let me check. It seems that there is no question, Professor Larbi. Thank you so much again.
Thank you.
For valuable contributions. Okay. Could you please stop your screen sharing? Thank you so much. And I would like to thank all the attendees once again for finding time and their patience. We will continue with my colleague Talha Arıkan for presenting next session. We will take a break until the next session. The next session will start in 7 minutes. Have a nice day.
Dear participants, welcome to this section. I am Talha Arıkan and I will moderate to this section. We have four talks in this section. For the first talk, I would like to invite Professor Harun Selvi Topi from Turkey. He is going to talk about numerical investigation of damped wave type MHD flow with time-varied external magnetic field. Welcome,
Hello,
Professor.
Hello.
Hello.
Are you reading and can you see my screen?
Yes, we can. Please make it full screen.
Okay. Just a minute. It's okay, I think.
Yes, it is fine. You are welcome to study, present your study.
Okay, thank you. Hello, everyone. I present a numerical investigation of that wave type MHD flow with time-varied external magnetic field. First of all, I'll give some abstract, think about the MHD flow, that wave type MHD flow, and I'll give the after that I'll give the mathematical model of the physical problem. Then I'll apply the finite element formulation for the space variable of the problem and finite difference approximation for the time variable of the problem. I'll give some results, numerical results, and discuss at the end of the presentation. The MHD flow problem is a very hot topic about the scientists, especially because it has lots of application areas such that nuclear fusion apparatus and MHD pipes, maybe health devices. So there are lots of studies about the MHD flow problems in the literature, numerical and theoretical, but lots of them are numerically because it's very difficult to obtain the theoretical results about the MHD flow because this flow problem is coupled to each other. So it is coupled partial differential equations. So it is difficult to obtain. But now, what is the differences this study in the literature? This study is a damped wave type. We will consider the MHD flow damped wave type for the induced magnetic field. I'll speak about the physical problem, and I speak lots about this in this section. The mathematical model of the problem is a coupled convection diffusion heat type for the velocity and wave-like for the convection, damped wave-like for the convection diffusion type equation for the induced magnetic field. We will apply the finite element method for the spatial variable and finite difference method for the temporal variable to obtain the numerical simulation of the problem for the different values of the problem parameters. In the problem mathematical model of the problem, there are a time-varied oblique magnetic field, and we will consider it several functions of time as polynomial, exponential, and trigonometric, etc. And we will consider the problem. We will take the numerical simulation of the problem for the different values of the Hartmann number and different directions of the induced magnetic field. We will give the numerical results by the contour plots. We can say, first of all, the mathematical model, I can speak a little, but I can say that, I want to say that the mathematical model of the aforementioned problem is governed by Navier-Stokes equations and Maxwell's Ohm law. So we will consider it a sufficiently long pipe in the z direction of the rectangular cross section omega. We will consider the solution domain omega. I will the mathematical model of the physical problem is a convection diffusion type equation for the convection diffusion heat type equation for the velocity of the fluid, and damped wave type convection diffusion type for the induced magnetic field. Here we consider the velocity v and induced magnetic field p. Sorry, yes. And the mathematical model of the problem is like in one. In general, I will say the problem has take heat type for the velocity and the induced magnetic field. In this study, we consider it a wave-like induced magnetic field. wave-like convection diffusion problem for the induced magnetic field. Here, HAX is the Hartmann number, product FT and cosinus alpha, and HY is the Hartmann number, FT sinus alpha. Alpha is the direction of the induced magnetic field. Here, HA is the Hartmann number, tau is the, we can see, light speed, and gradient P is the applied constant pressure. We take it -1 in this study, and we consider the problem no slip boundary conditions. There is no fluid at the boundary of the flow. There is no flow at the boundary of the fluid. We will consider like that, and we x by t 0 and b again at the boundary of the solution domain. Omega is the solution domain. D omega is the boundary of the solution domain. We will consider the initial conditions like that. VB and DTB, V0, B0, B1. We have to take the DTB because the problem is wave-like for the induced magnetic field. Here V velocity and BD is the induced magnetic field again. Yes, now first of all, I apply the finite element formulation, standard Galerkin finite element to the problem and for the space variable. And to take the to discretize the temporal variable, I will use the central difference approximation for Vt and Btt. First derivative of time for V and second derivative of time for B. First of all, I'll product the omega 1 and omega 2 weighted functions for the whole equations here, and we can see the linear form of the considered problem. We can see like that. We can, I wanna say the L space. L space is the second differentiable function space, and H01 is the basis of it. We can take the omega 1 and omega 2 at L again. Now we will discretize the Vt and Bt using the finite difference approximation. We can say is central difference approximation for the first and second derivative of the V and B, time derivative of the V and B. Here dt is the denotes the time step size, and n denotes the time level. We can see Vn and Bn, xi, yi, yj, and tn. Applying this approximation at the this equality, we take the b theta and b minus theta of the equation. This sigma is the theta sigma. We can say theta sigma. In this study, we can consider theta 1 for the implicit sigma and theta for 1/2 for the correct distance sigma. We will consider theta for 1/2 because the because the correct distance sigma is second order convergence for the time variable. So we choose to use the correct distance sigma. We can say b theta here like that, and b minus theta like that, and we consider theta 1/2. We will apply for the boundary conditions and initial boundary and initial conditions. Of course, for the time initial conditions, we will discretize it again central difference approximation, and we will consider the solution domain omega -1 product -1 product -1, and we take the delta t time step size 0.01. We will discretize the solution domain using 3,721 discretization point, and we take the 7,300 linear triangulation element. We will use here the linear shape functions because it is not complicated problem. The solution domain is not complex, and the problem is linear type problem. It is enough. Linear shape function is enough to obtain the stabilized numerical solutions. Here I'll give some numerical results, numerical simulation at different time points, and I'll speak about the numerical results. First of all, we take the FT1 and Hartmann number is 1, tau, the light speed is 10, and alpha is pi/2 at the time 0.5, the first column, And second column is at time equal 0.5. Here 1 and 2 for the numerical solutions. If we see and examine the velocity of the numerical results, we can see that the velocity numerical results is decreasing as time progresses. But if you see the magnetic field here, it is decreasing and increasing. So we can see that, or we can say that the wave-like of the induced magnetic field, we can see at the figures the wave-like of the induced magnetic fields, the wave properties. And in this numerical simulations, we take FTE power t, and Hartmann is again 1, light speed is 10, alpha is pi over 2. The first column is at time 0.1 and 0.5 second column. And we can see time equivalent 2 again. And we can say the wave properties, we can see the wave properties of the magnetic field at the figures. We change the FT again, cosine is 2pt. The other parameters is equal. I don't want to say, yeah, lots of things, yeah. This one is different. Why? What is difference? Sorry, it is same. FT is tangent t. I wanna show the yes. FT is tangent t. Hartmann is 50. Light speed is 10 and alpha is different, pi over 3. And we can see the numerical simulations again at time 0.1 and at 0.5 again. This one is at 1. We can see again at the figures, magnetic fields figures, the wave properties of the equation we can observe from the figures, and we can observe from the velocity. The velocity is increasing as time progresses. Thank you for your attention.
Thank you, Professor Selvi Topi, for this nice talk. Is there any question or comment to Professor Selvi Topi? So there is no question. Thank you again for your contributions, Professor.
Thank you. Okay.
So the next speaker is Professor Mejaj from Algeria. Are you there, Professor Mejaj?
Yes, I'm here.
So she is gonna, Professor Selvi Topi, please close your microphone.
Yes.
Okay.
Professor Mejaj is gonna talk about global existence results for second order neural function differential equation with state-dependent delay. Welcome again. Please make it full screen.
Yes. 1 minute. Okay.
Okay, it is fine. You can start your study.
Okay. At the first time, I want to thank the committee for the acceptance of my presentation. I'm going to talk about global existence results for second order neutral functional differential equation with statement delay. I'm going to give you some here we can find some reference about same topic. We are going to give some condition to the existence of my solution. The delay is unbounded. Here we can find some reference. At the first time, let us give the problem. The problem is 1, 2. Here we have a second order where f and g are a given function and the operator A is infinitesimal generator of strong continuous cosinus family. And the state belongs to the history. It is the history of the state. Now we denote by you say the space of bounded uniformly continuous function. We equip this space but we equip it with this standard norm. We denote this Banach space of all bounded continuous function. We use it to found my solution. I'm going to give the definition of family of sinus and cosinus bounded linear operator. We say that this family is cosinus family of bounded linear operator if this family satisfies the condition, the three conditions. And now the sinus family is given by this formula. We will use to find the existence of my solution Schauder fixed point theorem. We need a convex closed non-empty subset of E and the mapping N such that N to B is relatively compact. For proof that we need the lemma of Cordonier. D is relatively compact if the condition A, B, C, D holds. We have a no bounded delay. That's for we must introduce the notion of phase space, which is B equipped with this norm. We say that is a phase space if he satisfies the axiomatic definition A1, A2, and A3. I give this example of phase space. Now, this condition HV is used when the delay is unbounded. Let us begin for existence of our might solution. We will give at the first time the definition. The definition Y is said my solution of the problem 1, 2 if he satisfied the two conditions. Let us introduce the following hypothesis. The first one say that the cosinus and sinus family are compact, the operator, and the existence of the two constants, M and M'. And we have F is the Kara-Theodori, existence of condition, Lipschitz condition about F, and the same for G, Kara-Theodori, and the existence of Lipschitz condition. And H, we have two properties. This is the theorem of existence. If the condition H127 and HV are holds, plus this inequality, we can say that our problem has one mild solution on BC. For the proof, we are going to transform our problem on fixed point problem. It means we are consider this operator N, BC to BC, from BC to BC, is defined like this. If this operator has fixed point, that means that our problem has mild solution. When the delay is infinite, we must decompose our operator by defining xt and zt. We are going to prove that A from BC prime 0 to BC prime 0, which is defined like this, has fixed point. We use Schauder theorem. When we want to use for Schauder theorem, we need closed convex and bounded sets. We are going to prove the existence of radius, positive radius, which satisfy this condition, such that A transform the operator A, transform BR into BR. Then our proof will be given in the several steps. The first step is to prove the continuity. We will pass in the subsequence and use the fact that F and G are the Kara-Theodori. And for the next steps, it's clear because we have defined BR such that A to BR into BR. The three steps is to prove that ABR is equicontinuous. That means this quantity tends to 0 when 2, 2, 2 tend to tau n. We will use the fact that C and T are the family of cosinus and sinus family are compact. And for the steps 4, it's clear because it satisfies from the condition H7. And finally, we will prove that ABR is equiconvergent. That means that this quantity tend to 0 when T tend to plus infinity. And as a consequence of these steps 1 to 5, we're using the lemma 1, and we can conclude that A is continuous and compact. From the Schroeder theorem, we can deduce that A has a fixed point Z star, then there exists Y star who equal Z star plus X, which is the fixed point of the operator N, which means our mild solution. We are going to give an example. Let's E equal to, and this is the phase space in these cases. We are going to use the operator who is well known that he generated infinitesimal stronger continuous cosinus family, which is compact, and satisfy this condition, the existence of M and M prime. This is a natural differential equation of second order. So we are going to prove that this problem satisfies the condition H2 to H7 and H3. If they are satisfied, we can say that our problem has at least one solution, mild solution on BC. This is the reference used for this work.
Thank you,
Thank
Professor
you for
Mejash.
attention. Thank you.
Thank you, Professor Mejash, for your good talk. Is there any question or comment about the presentation? Let's wait for a while. So I think there is no question. Thank you again for your contribution.
Thank you very much. Thank you.
So for the next talk, I kindly invite Professor Daira from Algeria.
Good evening, sir.
So welcome again. She's gonna talk about time scale positive periodic solutions for two kinds of nonlinear neural dynamic equations with variable delay. So it is okay.
Okay.
You are welcome to present your study.
You can hear me?
Yes, we can.
I start?
Sorry, there's a problem with your voice. We hear you more than one times.
Okay.
Please check your microphone. So, can you try to speak?
Good morning, good evening, all of you. I will present my work entitled by my study on time scale, the existence of a positive periodic solution for two kinds of the nonlinear natural dynamic equation with a variable delay. We start by a planner of travel, abstract, K-works, introduction, a notion and the results preliminary, existence of a positive periodic solution, and the reference. Abstract, let it be a periodic time scale The purpose of this paper is to use a Krasnodębski fixed point theorem to prove the existence of a positive periodic solution for two kinds of the nonlinear neutral dynamic equation with a variable delay on time scale. We inverted this equation to construct a sum of the contraction and the complete continuous mapping with which is stable for applying the Krasnodębski theorem. The result obtained extend the work of the Lohr and Shen and Arjuni and Giorgi. K works positive periodic solution, nonlinear neutral dynamic equation, fixed point theorem, and time scale. Introduction. Let T be a periodic time scale such that for 0 in T in this paper we are interested in the analysis of the qualitative theorem of the positive periodic solution of a dynamic equation motivated by the papers 1 and 7, 10 and 19, and the reference theorem. We considered the following two kinds of the nonlinear dynamic equation with variable delay 1 and 2. Rather, this paper we assume that 2 and that E means 2 is strictly increasing, so that the function x is well defined over T. Our purpose is this is to use the Krasnodębski fixed point theorem to show the existence of the positive periodic solution on time scale for equation 1 and 2 to reach our
Professor
and
Daira, sorry for interrupting. Please close your computer voice. I think you connect. You use two computers. Please close the voice of one of them.
Okay. Now you can hear me.
Better, thank you. You can continue.
Okay, to such our this rate and we have to transform 1 and 2 in integrate. We written and some of 2 mapping. 1 is a contraction and the other is a completely continue. After that, we use Krasnodębski fixed point theorem to show the existence of a positive periodic solution for equation 1 and 2 is the special case T equal R. In 2, we show that 1 and 2 have a positive periodic solution by using Krasnodębski fixed point theorem. Notion and the results preliminary. A time scale is an arbitrary mathematically closed subset of the real number. We start by giving someone definition necessary for our work. Definition of definition 1, let T in an empty closed subset a time scale of R, the forward and backward jump operator, rho and P and R greenness are defined respectively by this set. A point T in T is called left dense if T is this inequality, and P equality left scattered if P this equality right dense if and right scattered if. Definition 2, function P is said to be regressive provided for all T in T. The set of all regressive RD continuous function is denoted by. Now, in this lemma, we see our property of exponential function in a time scale, property 1, 2, 3, 4, 5, and 6. In this lemma, we understand the exponential function between in time scale between 0 and 1. Now, theorem of Krasnodębski fixed point. Let M be a bounded convex multiple subset of the Banach space. Suppose that phi and C map M into B such that the condition 1, 2, and 3 is above that. If we want to apply the above theorem, we need to construct two mapping, one a large contraction and the other is mapping. now the existence z in d with the z equal a z plus b z let t let t in t be fixed and t different r and t equal np for someone n in n by the notation interval a b we are this set unless otherwise specified the interval this interval are defined similarly by this set. We see is the space of the continuous real valid function in T, then is the Banach space with the supreme norm. We will need to follow in lemma whose proof can be founded in reference then. In this lemma, let x in Pt, then the norm of x exists, and this norm in the paper we use the notation the sigma and assume that sigma in R plus and B in T are continuous, and for T in T3 we ed is endly function on T. Also we assume we also assume that the function g and the f are continuous in the respective argument and periodic in T with the parity that is 5. Suppose 4 and 6 hold if x in Pt, then x is the solution of the equation 1 if only if this equality where g equal 6. Prove let x in Pt be a solution of 1. Firstly, we write the equation. Multiply both sides of the above equality by exponential function. We get this equality. Above we are this equality. Lemma to suppose 4 and 6 hold if x in Pt, then x is a solution of the equation 2 if and only if this equality 7 where g is given by 8. Existence of a positive periodic solution. To apply theorem 2 or 4, we need to define the Banach space B as a closed convex subset D of B, and contraction mapping. One is a contraction and the other is a compact. So we let Banach space and this set we are L is a non-negative constant and K is a positive constant. We express equation as where A1 and AB are defined by this equality and equality 9. In this section, we obtain the existence of a positive periodic solution of 1 by considering the two cases G. The two cases G1, case 1 and case 2 for all t in R and x in D, we assume that the function g is locally Lipschitzian continuous is in x, that is the existence of positive constant such that this inequality denoted f by is the case. If this case we ask that there exists non-negative constant k1 and positive constant K2, we such that this equality for all t in this interval x and d, we are this equality. Lemma in this lemma for A1 divided by 11. Suppose that the condition 4 and 6 and condition 15 and 17 hold. A1 for D and 2B is a compact. Lemma 2 suppose 4 and 6 and 14 hold. For B1 is given by 13 is a contraction. The condition the equality 14, then B is a contraction. In this theorem, suppose 4 and 6 and 14 and hold, and this equality T0 in this interval such that such that this equality for L for and in x in D, then equation 1 is a positive periodic solution x in the in the subset D. In this theorem, suppose 4 and 6 and 14 and 19 and 21 is hold. We positive periodic solution for 1, 2. We express equation 9 as this equality where A2 and B2 are defined by this equality and this equality denoted by H. We suppose a condition with the following condition. In this lemma, suppose 4 and 6, 14 and 9 and 18 hold if B2 is given by 23, then B2 is a contraction. In this lemma, for A2 defined by 22, suppose that the condition 4 and 6 and this condition and the 24 fall, then A2 is compact. In this theorem, suppose 4 and 6 and this all the condition and condition 24 hold, and this exists T in this interval such that for this inequality for any T x in D, then equation 2 has a positive T periodic solution in the set D1. Now some reference. Thank you for your attention, and any question you can find me at this email.
Thank you, Professor Daya. Let me ask the participants, if you have a question, you can use question answer button to ask Professor Daira about her presentation. If you have further question, you can use her email address. So it seems there is no question. Thank you again for your valuable contribution, Professor Daira.
Thank you so much.
So please stop sharing. Okay, thank you again. The last speaker of this session.
Sir, please, I forget my camera, over my camera, please.
Yeah, there is no problem.
Okay, thank you.
So the last speaker of this section is Professor Tuna from Turkey. She's gonna talk about dual generalized complex Fibonacci P numbers. So please open your microphone and if possible, please open your camera. So we cannot hear you.
Hello, can you hear me?
Yes, it is okay now. If possible, please open your camera.
Okay. Can you see me, I guess?
Yes, it's fine. You are welcome to present your study.
Thank you. Hello, my name is Nilay and I am a master's student in Ankara University. In this talk, I would like to talk about a study on dual generalized complex Fibonacci P numbers. And this work is a joint work with Elif Tan. First of all, I would like to give some brief explanations related to literature. Hypercomplex numbers are defined by Cantor and Solodovnikov in 1989, and actually they are defined as an extension of real numbers. They have many applications in trigonometry, geometry, color image processing, and quantum mechanics. And in algebraically, they form finite dimensional algebra over real numbers. And non-commutative examples can be given as quaternions, octanions, and sedenions. And also they have commutative examples. They are two-dimensional hypercomplex numbers and
quaternions. Let's give the definition of n-dimensional hypercomplex numbers. They are defined like this. Here, A0, A1, and n-1 comes from real numbers, and E0, E1, En-1 are hypercomplex units. Now we focused on two-dimensional hypercomplex numbers, which are commutative examples of hypercomplex numbers. They are defined by 1893 in Lee. This is the set of two-dimensional hypercomplex numbers. Here, A0 and A1 comes from real numbers again. And unit J is defined like this. Here, this calligraphic P and Q are real numbers, and this set isomorphic to this ring. And also, Yaglom showed that this ring isomorphic to these three types of system, and if this discriminant is negative, then it corresponds to elliptic system, and if it is equal to 0, then it corresponds to parabolic system, and if it is greater than 0, then it corresponds to hyperbolic system. Now we consider a special case of two-dimensional hypercomplex numbers by taking Q is equal to 0. And actually, this number system are called as a Januzite complex numbers, and their geometric properties are defined by Harkin and Harkin. In a set sense, it can be defined like this. Here, J square is equal to P, and this P, if it is equal to -1, it corresponds to complex numbers, and if it is equal to 0, it corresponds to dual numbers, and if it is equal to 1, it corresponds to hyperbolic, or known as a purpose or double numbers. It corresponds to hyperbolic numbers. Now recently, Gürses et al. Defined the dual Januzite complex numbers. Here, Z0 and Z1 comes from Januzite complex numbers, and here our unit epsilon is a dual unit, and epsilon square defined like epsilon square is equal to 0, but epsilon is different from 0. By using the Januzite complex numbers, this set also can be expressed like this. Here, epsilon is a dual unit, J is Januzite complex unit, and also J epsilon is a dual Januzite complex unit. Also, as a special case of calligraphic P is equal to -1, 0, and 1, these numbers correspond to these special numbers, which are defined by the authors. It is known that there are many generalizations of Fibonacci numbers, and now we focus on Januzite Fibonacci P numbers, which is defined by Kocher et al. When n is greater than P, NTH Januzite Fibonacci P numbers are defined with these recurrence relations, and similarly, the Januzite Lucas P numbers are defined with the same recurrence relations, but the different thing is their starting points. Lucas starts from P plus 1, but Fibonacci P numbers starts from 0, as you can see. And it can also be easily seen that when n is equal to 1, these numbers reduces to classical Fibonacci and Lucas P numbers. And if it is P and M is equal to 1 at the same time, then they reduces to classical Fibonacci and Lucas numbers. And their Binet formulas can be given like this. Here, alpha k's are the distinct roots of this polynomial. Now, our goal is to bring together Januzite Fibonacci P numbers and dual Januzite complex numbers. The NTH Januzite dual complex Fibonacci P numbers are defined with this relation. Here, it can be easily seen that our coefficients comes from Januzite Fibonacci P numbers. And similarly, dual Januzite Lucas P numbers can also be defined like this. Here, epsilon is our dual unit, J is Januzite complex unit, and J epsilon is dual Januzite complex unit, as we mentioned before. By defining these new numbers, we generalize the following works, which are given in the literature. For example, if we take m is equal to 1, p is equal to 1, and calligraphic p is equal to -1, it corresponds to dual complex Fibonacci numbers. As a special case of m, p, and calligraphic p, we obtain these numbers. You can see this table. Here we see addition and multiplication of two dual generalized complex Fibonacci p numbers. The addition part, we define the addition just adding corresponding coefficients. And for the multiplication, we use the multiplication rule of dual generalized complex units. And it is known that for the dual generalized complex numbers, there are 5 different conjugates and modulus. So we can give the corresponding conjugates for our dual generalized complex Fibonacci p numbers like these. And by using the definition of conjugates, we define the corresponding modulus like this. Again, we have 5 different modulus in here. And by using the definition of conjugates and modulus, we can obtain these 6 equalities for complex Fibonacci p numbers. By using the definition of dual generalized complex Fibonacci and Lucas p numbers, we give these recurrence relations, and the last equation gives us the relation between dual generalized Fibonacci and Lucas p numbers. By using recurrence relations, we obtain generating function for the dual generalized complex Fibonacci p numbers like this. And for the Lucas one, we obtain this generating function. And their Binet formulas for dual generalized complex Fibonacci and Lucas p numbers can be given like this. Here, alpha k star is dual generalized complex numbers, which is given like this. And also we know that alpha k's are the roots of the characteristic polynomial of generalized Fibonacci p numbers, as we mentioned before. Now, by using this Binet formula of dual generalized complex Fibonacci and Lucas p numbers, we can give this summation formula. And we also know that the matrix method is very useful way to obtain the properties of Fibonacci numbers. Now, finally, I would like to talk about matrix representation of dual generalized complex Fibonacci p numbers. Considering this QP square matrix whose size is p+1, which is defined by Kocher et al. And for n is greater or equal than p, by using induction, it can be easily shown that the nth power of QP matrix can be given like this. Here, the important thing is our entries comes from generalized Fibonacci p numbers, as you can see. And similarly, by using this idea, and we define the matrix Kn, whose entries are dual generalized complex Fibonacci p numbers. And by using nth power of QP matrix, and considering this Kn matrix when n is equal to 0, this matrix product gives us the matrix Kn. And also, if we take the determinant of both sides of matrix equality, we can obtain the generalized Cassini's identity like this. Here, it can be easily seen that if we take p is equal to 1, then it gives this relation. Considering these matrix equalities and then equating the corresponding entries of both sides of matrices, then we obtain these identities, which is also known as the Honsberger identity. And finally, as a concluding remark, in this talk, we consider dual generalized complex Fibonacci p numbers, and we bring together dual generalized complex and generalized Fibonacci p numbers. Similarly, instead of taking dual generalized complex numbers, Gürses et al. Defined the hyperbolic generalized complex numbers and complex generalized complex numbers. Several different number sequences can be combined by using this idea and using these numbers. So our results can also be investigated for these numbers. And here you can see our references. Thank you very much for your attention.
Thank you for this interesting presentation. Is there any question or comment to Professor Tuna? If you have a question, you can use question and answer button. Let's wait for a while. So I think there is no question. Thank you again for your contribution.
Thank you.
Please stop sharing your screen. This is the end of this section. Thank you for your attendance and patience. We have nearly a half-hour break. After the break, we have an invited speaker, Professor Jean Zhang from United States. Professor is gonna talk about information geometry and statistical mirror symmetry. See you at next section.
Hello, dear Professor Cenk.
Yes, hello. Hi.
Hi, how are you?
Hi. Hi, Hande.
Hi, welcome to our webinar.
Right. I will open up my file, see whether you can work or not.
Now our timer is open, so it's
Right.
possible.
Just a second. Yeah, let me see. Yes, okay. Now, so I guess I'll do the sharing, right? Do you want me to try out the sharing?
Yes, you can try now.
Okay, let me see.
We can see your screen. It's okay.
You can see the screen? Screen is good? Okay, let me just
Yes.
check. Let's see. Let me also check one more thing.
Maybe you can click the green circle.
Yes, right. Let's see. Yeah, I see the live here. Okay, just a second. Let me do one more thing. I want to do the full screen and see whether that'll work because
Of course, take your time.
Yeah, is that okay?
Yes, it's perfect.
Okay, it's moving? Is it moving, right?
Yes, it's moving. Yes.
Okay,
we can
good.
see your mouse.
All right. Sounds good. So
now we are waiting just a little bit.
all right, sure. Yeah, no problem. I
yes.
will be coming back in about 10 minutes. Yeah.
10 minutes, yes.
Right.
We can closing now, then timer is open.
Right. Okay, sounds good.
Okay. See you.
Yeah.
Hello again, dear participants. Welcome to the last invited speaker talk of the webinar. We are going to start in a couple of minutes. Let me kindly introduce our invited speaker, Professor Zhang. He's a psychology professor at the Michigan University, and he's attending from the United States of America. We are very glad that he was able to arrange his schedule to attend this webinar, even if a big time difference. And now he is going to talk about the information geometry and statistical mirror symmetry. Professor, you are welcome.
All right. Thank you very much. Thanks for the organizers for the invitation to give this talk. So let me first put up my slide here. Let's see. Just a second. Okay. All right. So I hope you can see this now.
Yes, we can see.
Yeah. Okay, good. Okay. Yes. So my talk here, just slightly modify two words. So conjugate connection and statistical mirror symmetry. First, I'd like to acknowledge my collaborators for this work over the years. So let's see. The plan of today's talk is that there are three parts. One is that I will give a basic introduction to the essence of the information geometry, namely the conjugate connection, the notion of the conjugate connections. And I'll give some motivations from statistics as to how this mathematical structure arises. So I will be talking about both the statistical structure, the standard information geometry structure, as well as the so-called partially flat structure, which my colleagues and I will have worked on in the past. And then I'm going to talk about how the conjugate connection would interact with a compatible triple on the manifold. So in particular, we are going to focus on transformation of the connections via or through this compatible triple, and how the statistical structure can be extended or enlarged to Hermitian structures and Kähler structures. And finally, we talk about the construction of statistical mirror symmetry. And this is something which comes out very naturally for any parametric statistical models. So we'll explain its construction and use the example of the univariate normal distribution. All right, so let me first start with conjugate connections on the Riemannian manifold. So we are given with the Riemannian manifold and an arbitrary affine connection that may carry curvature or torsion. So we define the conjugate connection with respect to this Riemannian metric as follows. So basically, you have the given connection operates on the vector fields X, and the conjugate connection, well, another thing that operates on the other vector fields so that the G, the inner product, is preserved. Well, it needs to be proven that this is indeed an affine connection, and this can be done. In other words, you can verify the axioms for the affine connection and show that this is indeed an affine connection as well. And with this, we can also show that actually this operation of conjugation by G is involutive. So if you apply twice, it becomes the original connection. So we can then write this above equation and change the slots of its application. And this can all be verified. And that's our starting point. In other words, we are given with the nabla, and then we have a G, and the G, using the G, we define a conjugate connection, which is another connection on the same manifold. Now, this nabla and nabla star, the two connections operates on the sections of the tangent bundle, okay? So they operate on the vector fields. The average of that is parallel with respect to the metric. It may carry torsion though. So having defined the idea or the notion of the conjugate connection, let us also define another notion, which is called the Kudazi coupling between G and nabla. So the Kudazi coupling of the G and nabla is basically that nabla G is symmetric. So the covariant derivative of G is symmetric with respect to, so here you can see that's a definition. So the covariant derivative is of course defined in the usual way. So we have defined the conjugate connection and we have defined a Kudazi coupling of the nabla and G. Now we can show very readily that these two conjugate connections, they satisfy this equation with respect to the Riemannian curvature tensor. This says that the conjugate connections, they must be curvature-free jointly. In other words, if one is curvature-free, the other is also curvature-free. Now, with respect to torsion, it turns out that you also have an identity. The identity is that the left-hand side okay, sorry, I there's a disconnect on my side, I guess. Let's see. Let me just re-pull this up. Sorry about that. Okay. Okay. Okay. So I have to reshare my screen here. Just a second. Okay, sorry about that. So let's see, coming back again. So with respect to the torsion, then, so we just talk about for curvature, they are jointly curvature free, but with respect to torsion, so the difference on the left-hand side is equal to the difference of the torsion tensors between nabla and nabla star. So the notion of the Kudazi coupling, that is to say, if nabla G is symmetric, right? That's the definition of the Kudazi coupling. When nabla G is symmetric, then the left-hand side would vanish, which means that the torsion of nabla and nabla star would be the same. So we can say that the torsion of the conjugate connections, they are preserved under this conjugation. So the torsion is preserved under this conjugation by the G. And curvatures, they would vanish jointly. And this is very important for us when we construct the statistical mirror symmetry. Now, let us then recall some standard definition of the statistical structure. So there are several equivalent definitions of statistical structure. So Amari first came up with this structure where you have a Riemannian manifold and a pair of conjugate connections, and that they are both torsion-free. So that's the definition of a statistical structure or a manifold, a statistical manifold. This definition can be equivalently stated in the case of Loritan. Just basically, on the manifold, you have a Riemannian metric and a symmetric 0,3 tensor. So a Riemannian metric with a symmetric 0,3 tensor field, you can show by this symmetric 0,3 tensor field, you can construct this K, which is a 1,2 tensor field, and then construct a pair of conjugate torsion-free connections. So that's another equivalent way of defining a statistical structure. And thirdly, we have a Riemannian manifold and given a connection such that the covariant derivative of the connection with respect to the metric would be symmetric. So these are all three equivalent ways of defining this so-called statistical structure. And this is the data we have when we carry out the subsequent discussions. I'll mention that this is actually the standard definition for the statistical structure, or the S structure. And we're going to talk about some other an extension or generalization of this kind of conjugate connections. But let me first explain why this structure, the statistical structure, is an important object to study for applied mathematics, in particular in statistics, machine learning, information theory, etc. This is because we start with the so-called contrast function. So a contrast function on a manifold is a two-point function. This two-point function is non-negative and smooth, that is differentiable up to second order. So given this contrast function and working in any local coordinate charts, we have the following expression. We have the following requirement indeed. That is, so it's non-negative, it's 0 if and only if x is equal to y. And it is smooth. The first derivative vanishes as x equal y at the diagonal. And the second mixed derivative, if minus of that, is the positive semi-definite. So here the subscript d sub I is the partial derivative with respect to the xi, and the comma I is the partial derivative with respect to the yi. So we have these notations. It turns out that in 1992, a Japanese statistician, Eguchi, showed that any contrast function would induce a statistical structure along the diagonal of M cross M. So I'm going to explain this method, the Eguchi's method for inducing the statistical structure from the contrast function. So contrast function, basically, when you expand it, when you do Taylor expansion, the first order would vanish because of its definition. So the only first surviving term is the second order. The second order, if you do the mixed derivative of xi and yj, which can be shown, readily seen, is actually symmetric with respect to yi and xj. And this is a symmetric and, by assumption, positive semi-definite matrix here. Now, if you look at the third order, namely, we perform derivative with respect to x twice, xi, xj, and then do yk, and set them y equal x. That, we call it this gamma. We perform yi, yk, and then x, yi, yj, and xk, we call it gamma star. It turns out that these quantities, which are derived, would satisfy this equation. And this is the equation, which is the expression of the conjugate connection in local coordinates. So therefore, from any contrast function, we can perform this procedure and derive what will be a Riemannian metric and what will be a pair of torsion-free affine connection. Now, torsion freeness is because of, you look at this subscript ij, and we perform the partial xi, xj, so it is obviously symmetric. So it's torsion free. So both gamma and gamma star are torsion free. Now, this construction is very useful for the study of statistics. For statistics, let us consider a parametric probability density, a family of probability density functions indexed by some parameter theta. So random variable here is indexed by omega. and the parameter theta index the particular probability function. And theta then can serve as a coordinate chart and then form this manifold M sub theta. So each point on this manifold is just a probability density function. And turns out that César, he was information theorist in 1967, he defined a class of function called F divergence or F contrast function. Divergence and contrast are synonymously used in this community. So it's F divergence. So F divergence measures the directed difference or the directed distance between two probability density functions indexed by theta prime and theta. And this F function, you can show that it defined is a proper divergence function or contrast function. And once we perform the Eguchi's method on this divergence function, here I use the L to denote the log of P, Then you can immediately derive that the Gij, the G, is of this form. Is the expectation of the so-called score function in statistics. So this is a well-known Fisher information. It's a Fisher information, which is the most well-known quantity in statistics. So since this Fisher information is used as a Riemannian metric, this metric is called the Fisher-Rao metric. And the fact that Fisher-Rao metric is the lowest order approximation for the so-called Kullback-Leibler divergence, which is a very special case of this F divergence. And this is known to statisticians in 1950s. So this structure arises very naturally from statistics. Now, if we perform the Eguchi's method to obtain a pair of conjugate connections, gamma star and gamma, and then we take the difference of them, this is the 0,3 tensor we obtain, Cijk. This quantity is also an important statistical quantity. Chenzov in 1972 showed that G and C are unique second and third order invariants under the Markov morphism, that is relabeling of the random variables. And then Amari in 1980s first obtained this kind of a dualistic geometry, the gamma and gamma star. Well, here gamma now is just the coordinate representation of nabla. So the dualistic geometry was obtained by Amari, and then Lauritsen further clarifies that the C tensor here is just gamma star minus gamma. So statistical structure basically is the data on the manifold, which is given by parametric probability models. So it is the Riemannian structure along with this conjugate connections that underlies all statistical models. So this is the data G nabla nabla star or GC or G nabla, where nabla G is symmetric. This is three different ways of representing the same geometric data on M that we start with. So what is information geometry? Information geometry, if we very narrowly speaking, this is the differential geometric study of the manifold of this probability, parametric probability distributions or probability density functions with the following given data, that is the G and a pair of conjugate connections, and L is the log likelihood function of the probability model. So you can see, given any probability model, a parametric probability model, we can induce these geometric quantities. So that's the narrow definition of information geometry. Now, broadly speaking, information geometry can be defined as a geometric study of this kind of this dualistic structure of a manifold that relates to the conjugate connection. So the essence of this is the conjugate connection. Now, in recent years, people are extending the statistical structure while still keeping or looking at this conjugate connections. So Kurose, a Japanese geometer, defined the following structure. So manifold M, G, and nabla. Now, instead of assuming nabla G to be Kudazi coupled, that is nabla G is symmetric, he defines this case when nabla, the torsion of nabla is equal this difference in symmetry of this left-hand side. So when nabla G is symmetric, the left-hand side is 0, so torsion is 0. So you can think about Kudazi coupling as a special case where a connection is torsion-free, right? So this would be a more, it's not a generalization, but it's an alternative way of coupling nabla and G. This is called a torsion coupling. If nabla is torsion coupled to G by this definition, you can show very easily, you can see actually that the conjugate connection is torsion free. Okay, so these are so in this case, we would also have a pair of connections, and this pair of connections have the following property that one of them is torsion free and one of them carries torsion. Now, if we further assume that this connection nabla is curvature free, this is called the partially flat manifold. Partially flat in the sense that the nabla, the connection is free, is curvature free, but may carry torsion, but nabla star is curvature free because they are curvature free jointly, and then it carries, it does not carry torsion. So this is a flat connection. So this is called a partially flat manifold. So this is an alternative model for the parametric probability family, and also with the conjugate connection. In this case, in the partially flat model, essentially the parameter theta is being treated as an affine coordinate chart. And when we take the Fisher-Rao metric G, then it forms in generally a partially flat manifold. So let's give an example for the probability family. So this is the familiar example of the univariate Gaussian distribution on the real line R. So we have this where omega is a random variable taken on the real line, and mu and sigma are the parameters. So for this parametric family, the parameters mu range through R, and the sigma range through the non-negative number, real number. So when sigma go to 0, this is essentially the distributions, the delta distribution. And when sigma go to infinity, it's a uniform distribution. These are non-proper densities. They are linear functional on test functions, but they are the limiting case for this family. So if we geometrically present that, so we represent mu as the real line here, and we have an XY plane. The upper half plane indeed is a representation of the family of normal distributions. Sigma can take from 0 to infinity. So all the points along this line are these delta functions, in non-proper density function, and the point at infinity is also the uniform distribution, also a non-proper density function. So each point represents a normal distribution, which is on the right-hand side. So the univariate Gaussian distribution or normal distribution is, so 4 normal distribution mapped to 4 points here. So well, from statistical consideration, it is obvious that these two distributions are actually farther apart because they have smaller variance. These two, which are closer, they have larger variance. Okay, given that the separation of the mean is the same. So that's from statistical. statistical meaning is very clear. With respect to this family, the Fisher-Rao metric, we can derive it, which is has this very simple form. And in fact, this is if we actually calculate its Riemann curvature tensor for the Levi-Civita connection, it is constant negative curvature. It's a constant negative, the curvature has a constant negative value. So it's the hyperbolic space of the upper half plane. But this metric is not a Hessian metric, and we'll explain more later. So if we actually calculate the Levi-Civita connection, so this is the Levi-Civita connection expressed as Christoph symbol of second kind. Okay. So the Levi-Civita connection has constant negative curvature, but interestingly, when we calculate the conjugate connections, turns out that they are curvature free. So in fact, on this hyperbolic space, we can prescribe a family of connections, alpha. Alpha is a real number. So we have a family of alpha connections in which zero connection is the Levi-Civita connection, and the alpha connection and minus alpha connection are conjugate to each other. And this gamma and gamma star is just 1 and minus 1. And this pair turns out to be both, they are both curvature free, and of course they are also torsion free. So they're both flat, they're dually flat. So they form what is known as the Hessian manifold, So because of that, we know then there need to exist the affine coordinate system on this manifold as well, even though mu sigma is not an affine coordinate system, because the metric expressed in mu and sigma are not Hessian metric. So, but we can find the Hessian metric. Okay. So if we look into finding the affine coordinates, the Hessian metric and its meaning, we realize that normal distribution, originally it was a so-called location scale family because it has centered on mu, and it has a variance of sigma as a location and scale. Turns out that this normal distribution with location and scale variables mu and sigma, we can also write it as in this form after we do some manipulation. Now, this F1, F2 are the given functions, random functions, these are random variables, and X1, X2 are the new parameters as a function of the old parameter mu and sigma. Okay, so X1, X2 can be written just as a transformation of the mu sigma in this way. This form is known to statisticians as the exponential family, So the exponential family, and with exponential family, and then we also, if we perform the expectation on these random variables on this F1, F2, which are called the sufficient statistics in the exponential family, what we find is that U1, U2 are also given by this mu and mu and sigma. So they are also the functions of mu and sigma. So we have the U1 and U2. And U1, U2 are also related to X1, X2 in this way. And this, if we calculate the Legendre dual of this phi is a generating function for the exponential family, right? Phi is like this. Phi is here. It's a normalizing function. This function makes this exponential family normalize to 1, which is has this form here. This is the phi. And if we take its Legendre conjugate, turns out to be nothing but entropy, the Shannon entropy function. Okay, so from this analysis, you can see that all these properties are embodied in the geometric structure, because from geometric structure, we first derive that there is the Hessian manifold. There is the dually flat structure, the affine connection have a dually flat. So we go about and trying to find these affine coordinates. And the affine coordinates turns out to be x1, x2, and u1, u2, which are transformations of the mu and sigma. And these convex potentials have meanings in information theory, in statistics. They are the Shannon entropy. So that gives us some encouragement as to why we want to actually study this geometry. So when we write the Hessian, when we write the Fisher-Rho metric in these coordinates x1, x2, we actually indeed get a Hessian metric using the phi. And we will write this in U, then we also get the Hessian metric. So we have two. Well, this is one and the same, because if you do a coordinate transformation, this is the same. In fact, the Riemannian metric is the same, but the fact that it can be written as a Hessian on this with respect to these special affine coordinates. And this is something that can come out very naturally from a geometric analysis. Now, I'm going to now talk about this notion of the conjugate connection and then compatible triple and how they interact with a compatible triple. So, so far in the standard information geometry, we studied the G conjugate with respect to the Riemannian metric. Over the years, my colleagues and I, we studied other notions of conjugation, in particular, the conjugation with respect to non-degenerate two form. Okay, so in this case, we can also define the conjugation in the same way as for G. Of course, we need to verify this is indeed an affine connection and has the same property that it is involutive. So it can be defined, well defined for each of the slot. Now, this is joint work with Fei-Ten. So we can show that actually in this case, now the so-called Kutazi coupling, this Kutazi coupling, because of omega is a skew symmetric, Kutazi coupling is the same as saying that the nabla and its conjugate connection, nabla-dagger, are the same, which then imply that the torsion of nabla and nabla-dagger are the same. So nabla and its omega conjugate are the same if and only if their torsion would be equal. Now, let us also look at the situation where, well, here we assume the dimension for the manifold is even dimensional. So we look at the endomorphism of the tangent bundle and the section that and the map that it induced on its section. Okay, so this we denote this L. L is also known as the gauge transformation. Okay, so we apply this gauge transformation to the nabla, which is defined in this way, to obtain the nabla L. So nabla L, given the nabla and given the L, and we can define this, which can be shown to be an affine connection, the gauge transform of an affine connection. Now, this set of invertible operators, or the L's, the set of invertible L's on here, they will form a gauge transformation group, and with the group operation defined in this way. So it is easily shown that the average of these would be parallel with respect to L. Okay. So we can also define the Kutazi coupling of L with respect to nabla. And it is known that this nabla and L, if it's Kutazi coupled, then nabla L inverse is also Kutazi coupled, which is the same as the torsion being equal. Okay. So I need to hurry a little bit because I'm but we are going to look at a special case where L square is plus minus identity. So in this case, we are looking at the almost complex structure, J square equal minus identity, or para-complex structure, K square equal plus identity. And we look at its compatibility with respect to the Riemannian metric. J is, in this case, a standard almost complex structure compatible with the Riemannian metric G. And here it's had to be pseudo-Riemannian metric because it had need to have split curvature. But in both of these cases, we can have the compatibility. We can write out the compatibility condition, and also we can construct a skew symmetric two form, and we form a compatible triple. We form a compatible triple in this case. So now, with respect to a given connection, with respect to G, we have the G conjugate. With respect to omega, there's omega conjugate. With respect to L, we have the L gauge transform. And in this case, when they form a compatible triple, we show that if they form a compatible triple, then these transformations, these three transformations, conjugate transformations, along with the identity operator, would form a 4-element Klein group. In other words, they are commutative, and they are involutive, and the composition of them gets to the third. Any two composition gets to the third. Okay, so you have this very nice structure of the transformation of the connection for any connection. So here, nabla can be any connection. We didn't restrict it to any quasi-coupling or torsion freeness and so forth. So this structure is of great interest to us. And it turns out that, yeah, I want to mention a little bit about this, a cousin of this structure with the anti-Hermitian or the northern structure, which is, I think, very familiar to many people in this audience. So, so we looked at the we have looked at the para-Hermitian structure K, in this case, with the split curvature, with the split signature of G and a skew symmetric omega. But we can also have the so-called anti-Hermitian structure, which is different than the para-Hermitian structure. It's also have a split signature on G, but it has a twin or associated metric. It's a symmetric form as opposed to skew symmetric form here. So it turns out that these conjugate connection on the northern manifolds has also has been studied. And turns out also they would obey this kind of Klein transformation group as shown by Professor Giza and his colleague. So this proof was following the proof that we gave for the case of the Hermitian and para-Hermitian case. So a lot of these structures can be extended or can have their analog in the northern manifold situation. And this is something that can be
There is a little internet connection problem. We are waiting for Professor. Dear participants, we have a little problem about the internet connection of the Professor Zheng, and we are waiting their connection until he came. We give a little break. Please follow the timer in the screen.
Well, sorry, just
Okay, no problem, Professor. It's possible when we are making a webinar.
yes. So this is okay. Am I still getting here? Let's see. Okay, let me just put this on again.
Don't be hurried, take
All
your
right.
time.
Okay. Yes. Okay. So yeah, I don't know what happened with the network. This here is just maybe it's because of the snow. We had a big snowstorm right now.
Maybe
So
it's
this
possible.
is kind of, I don't know what's the situation. Okay. Oops. Okay. So
Okay, we are ready.
yeah. Okay. Yes. Okay. Sorry. Yeah. So okay. I think I will try to skip a few things. So basically, we can. Yes, we can derive the interaction of the nabla with the compatible triple, and then in particular, I want to mention one thing is that we investigated the case where how an integrable structure of L, how the integrability of L can be linked with the torsion of the nabla on the manifold. So this is some, we derive some conditions, what we call the torsion matching condition of nabla with L. And we show that this actually extends the canonical connection, the first canonical and second canonical connection along the Kardashian line of connections. So this is a generalization of their notions. And we also showed that on an almost Hermitian manifold or almost para-Hermitian manifold, given any nabla, of course, we have the quadruple of connections, the G conjugate, the L conjugate, the omega conjugate. And turns out that if any of the four is quasi-coupled to G, and if any of the four is torsion coupled to G to L, then all of them have to be quasi-coupled to G, and all of them will be torsion coupled to L. And the average of this is the Chen connection. The average of nabla with nabla L, the average of these, they are the Chen connection in the sense that, so they are parallel with respect to G, omega, and L. So we can generalize the standard, structures that's studied in complex geometry. And we have also looked at the case of the Kähler manifold, in which case then the nabla would be torsion-free, and we define the so-called quasi-Kähler structure, and then we show that for a statistical manifold, if there is a almost complex structure, almost paracomplex structure that's compatible with G and is quasi-coupled to nabla, then it is a Kähler manifold or para-Kähler structure. Okay, so this is again saying that for if we given a torsion-free nabla and its transformation nabla star, nabla dagger, nabla L for any compatible triple L,
Again, the same interruption occurs. Sorry for this situation. We are waiting the connection again. Dear participants, sorry for this interruption. Now we got some email from the Professor Can Zeng, and he sent his apologies because of the snowstorm happened in the USA. He could not attend again. So we need to continue our program as scheduled before. I would like to thank the Professor Zeng from here. It was a very exceptionally good talk, and I hope our participants are interested in this presentation so much. I would like to remind all of you, our webinar is broadcast live and recorded, and after the webinar you can watch them into the TÜBİTAK Ulakbim channel in YouTube. So you can reach our all professors by taking their email addresses from this videos. So the situation is welcomed for us. Thank you very much. After 3 minutes later, my colleague Ramazan Yaşar will continue to moderate this session. Thank you very much.
Okay, dear participants, welcome to the session 27 of our webinar. I'm Ramazan Yaşar, the moderator of this section. Now, I would like to invite the first speaker, Professor Eşref Erdoğan from Konya, Turkey, to do his presentation. Professor Erdoğan, do you hear me?
Hello.
Hello. Welcome to our webinar. Please open your presentation in full screen. Okay. The link and other facilities for the online presentation seems to be okay now. And it is a really great pleasure for all of us to have here Professor Erdoğan for his noticeable talk on fixed point results for almost F-type contraction. Professor Erdoğan, do welcome to your presentation, please.
Yes. Thanks to TÜBİTAK for this great organization. Hello, I am Eşref Erdoğan. I am a master student at such university. Seminar location, fixed point results for almost F-type contraction. Let's start. Fixed point theory students in complex metric space started with Banach in 1922. The Banach contraction method principle not only guarantees the existence of the fixed point of the method, but also show the uniqueness of this fixed point and how it can flow. The theorem, which is considered to be best known result of fixed point theory, and the beginning of the theory is given by the famous Banach fixed point theorem in the following form. Let X be a complex metric space and X2X a contraction method with an ellipsis constant. In this case, there has a single fixed point Z in X. Moreover, for any X0 in X, the sequence converges to this fixed point of T. A number of efforts have been made to enter and generalize Banach contraction principle because it plays a fundamental role in metrical fixed point theory. Theorem: let X be a metric space and let T be a submetric on X. If there exists beta real number such that S and 1, then there has a unique fixed point. Theorem: let X be a metric space and let T be a submetric on X. If there exists gamma real number such that S and 2, then there has a unique fixed point. Let X be a complex metric space alpha, beta, gamma real numbers with fx from X a function such that for each company of different points xy in X, at least one of the following contribution is satisfied, then F has unique fixed point. Let X be a complex metric space. Their generalization decayed contraction submetric of X, then it has unique fixed point. On the other hand, one generalization of the Banach contraction principle is the heterogeneous theorem. Let X be a complex metric space. Let T X to X be a given metric such that S and 3 then there has a unique fixed point in X. We have seen that the coefficients in the contraction we have given above. Now we will see that these coefficients or the sum of the coefficients will be 1 or the greater in the contraction we will give. This type of contraction was visible by Berinda in 23. Let X be a metric space. AMF X to X is scalar with contraction if there exists a constant delta and some L such that S in 4. Due to symmetry of the design, the weak contraction condition for Iblis inverse the following dual 1, S and 5. Consequently, in order to check the weak contractivity of it is necessary to check the work 4 and 5. Example, T symmetric defined by delta and is an almost contraction for L. Also, the fixed point of this mapping are 0 and 1. Theorem. Let X be a complex metric space and X to X a weak contraction. That is, let delta and L be S in 6. In this case, they have a fixed point at x. It should be noted here that is the Banach fixed point theorem. The uniqueness of the fixed point was guaranteed. However, in almost construction, as seen in the example above, the fixed point might not be unique. To answer this uniqueness, we can guarantee uniqueness by adding an addition requirement similar to almost contraction requirement. Theorem: let X be a complex metric space and X2X a weak contraction, that is, let delta and L be Sn in 7. In this case, there has a unique fixed point at X. The more remarkable generalization of the Banach contraction principle was given by Twardowski in 20th work by defining the concept of F contraction. In this generalization, Twardowski demonstrated that F contraction mapping in complex metric space have a single fixed point. Now let's first give the concept F contraction and some example of it. Then let's examine the fixed point theorem met with the help of the contraction. Let F be a matrix satisfying F1, F2, F3 conjugation satisfying. A matrix X to X is said to be an F contraction if there exists so such that S in A. Let X be a complex metric space and let the X to X be an F contraction, then it has unique fixed point in X. In this paper, we modified the concept of F contraction matrix to orthogonal set and provide some fixed point theorems for almost F contraction matrix in orthogonal complete metric space. But first of all, let's remember some information about orthogonal metric space. Definition: let X be a non-empty set and third be binary relation defined on X. If binary relation third fulfills the following criteria: 9. Behind paper pair X third knows as an orthogonal set. The element X0 is scalar and orthogonal element. We denote this O set or orthogonal set by X bar. Example: let X define M third and if there exists K such that it is to see that 0 third and 4 and n, hence X third is an O set. Example: let X third be an orthogonal set any two elements xy in X such that X third Y, then xy in X are said to be orthogonal relative. A sequence Xn is scalar orthogonal sequence if Sn 11. Similarly, a Cauchy sequence Xn said to be an orthogonal Cauchy sequence if similarly Sin 11. Let X third be an orthogonal set and D be a metric on X. Then X third D is scalar and orthogonal metric space. Definition: let X third D be an orthogonal metric space, then X is said to be a complete if every Cauchy or sequence is converse in X. Let X third D be an orthogonal metric space of a function fx2x is said to be orthogonal continuous at X if for each or sequence Xn converging to X if place of F is third continuous on X if F is F continuous at every X in X. Definition: let a pair X third be an O set where X be a non-empty set and third be a binary relation on set X. A mapping fx to X said to be third preserving whenever X third y and directly preserving if whenever x part y. Theorem. Let X be part B and O complex matrix space and lambda. Let Fx2 X be lambda continuous, lambda contraction, and lambda preserving. Then F has unique fixed point X. Theorem. Let X part B be an O complex matrix space with an orthogonal element X0 and the X2 X satisfy the following combination 1, 2, 3. The hand has a fixed point. Moreover, if the fixed point of the is unique. In this section, we got a definition of generalized orthogonal almost type F contraction, and using the contraction, we obtain some result on a complex orthogonal matrix space. X per D. Definition: X per D be an orthogonal matrix space. A mapping X to X cannot generate orthogonal almost F contraction if there are F in F. L and lambda such that the following condition holds: SN 13, 14, 15. Theorem that X per be an complete orthogonal matrix space with an orthogonal element X0 and the matrix on X satisfy the following continuous one S for preserving there's and generalized orthogonal almost type F contraction. There's per continuous, then it has a fixed point in X. Looking at the proof X0 in XP and orthogonal elements, it is shown that the sequence created with the orthogonal element S in 16 is an orthogonal sequence. In order to show that Xn is a Cauchy or sequence, consider since X orthogonal complex, the axis is a point where Xn converges in X, or the per continues to extent of a 5 point is shown. Theorem that X per be an complete orthogonal matrix space with an orthogonal element X0 and the self-mapping on X satisfy the following condition. T is per preserving this and generalized orthogonal almost type F contraction. T is per continuous. Also to satisfy the following condition that exists F1 in F L1 greater or equal 0 at lambda such that Sn 27. The hand has a unique fixed point X. Look at the proof for uniqueness. It assumes that it has two different fixed points and uniqueness is object in the triangle. Hence, it has unique fixed point. Let X per be an O complex orthogonal matrix space with an orthogonal element X0 and TBS mapping on X satisfy the following condition. One, there's per preserving there's an orthogonal almost a contraction such that there's per continuous and it has a fixed point in X. Let X be a complex matrix space and the X to X be a mapping such that for lambda Sn 13 1 it has unique fixed point in X. Reference. Thank you for listening to me.
Okay, we thank to Professor Erdoğan for his valuable presentation.
Thank you.
If there is any question or comment, please use the question and answer button. Let me check if there is. Okay, there seems no question or comment. So we thank again to Professor Erdoğan.
Thank you.
Stop your screen sharing, please. Okay, well, now I kindly invite the last speaker, the speaker of this session, Professor Nur El Huda Dija from Relizane, Algeria, to do her presentation.
I hope you
Do you
can
hear me?
Can you hear me?
Yeah.
Okay.
Please open your presentation with full screen. Mm-hmm. With Control L, maybe.
Yeah.
With full
So
screen.
good evening. Okay.
This okay. So the link and other facilities for the online presentation seem to be okay. It's a really great pleasure for all of us to have here Professor Dija for her noticeable talk on the geodesics of deformant Sasaki metric. Professor Dija, do welcome to your presentation, please.
Thank you, sir. Good evening, everyone. Thank you for having me with you. It's an honor to speak in front of such great audience. Well, I would like to speak today on the geodesic of deformant Sasaki metric. For that, let me give you a short introduction on Sasaki metric. I believe most of you already know Sasaki metric, but even though I like to recall some basic definitions and notions. So what's a Sasaki metric? Let's start by MG and M-dimensional Riemannian manifold, and Tm pi and b the tangent bundle, where here pi is the canonical projection from Tm into M. So if X is a vector field on M, then we have the vertical left xv and the horizontal left xh of X are given as follow. Well, here the basis is related to the local coordinate xi, yi. Wi. So Sasaki has discovered on the tangent bounded Tm a new canonical metric defined by S equal g of x, y on the horizontal side, as well as the vertical side, and gs between xh and yv equals 0. This metric is sort of natural metric, and it is also called diagonal metric. Since then, many authors have largely studied and this topic. I can mention, for example, Dombrowski or Prio. For more details, you can check this references right here. I recommend them. Well, in last years, many authors are studied and introduced a new vertical deformation of Sasaki metric. I can see it's significant work that inspired this paper. First of all, I like to introduce the metric of Shigren-Gromov, which is, I guess, the most known metric in this area. Many authors studied this metric in details. And the metric introduced by Professor Mustafa Jah, who chose to deform its Sasaki metric by multiplying g by the function f of x r right here, where f is called twisting function. The metric introduced by Professor Aydin Gizer, who add this part right here to g of x y over an almost anti-parahermitian based manifold. You can check these references right here for more details. Well, by the same way, we give another vertical deformation of Sasaki metric by using alpha r right here, beta r right here, where alpha and beta are smooth positive functions. We have this condition alpha plus beta r positive. This condition is very necessary for GDS to be defined positive. Well, we notice that if alpha equal 1 and beta equals 0, then GDS is this is a symmetric. Also, if beta equals 0, then GDS is one case of which is a symmetric. If alpha equal beta equal 1 over 1 plus r, then GDS is shear Gromol metric. Of course, the first thing we're looking for is the corresponding connection. In this case, which is verified, the following relations in here. For the proof, we use the causal formula, and we use also the fact that G of ZW equal this factor right here, multiplying GDS ZVWV. This relation between GZW and GDS ZVWV is very important for calculation. So what about the curvatures? Using the Levi-Civita connection, we can get the following proposition describing the behavior of the tensor curvature with respect to TM GDS. And we can note that in Formula 1 and 2 have a relation between the tensor curvature on TM GDS, the tensor curvature on M, G, which is good. But fortunately, on the vertical left, X, V, Y, V, have something else. We have a long term in here, and we notice that there is unfortunately no R side. But I guess this is not a problem. We consider the sectional curvature for P, which is given by the formula for right here, where P denoted the plane spanned by X cubed by Q. So if we take Ti an orthonormal frame on Tx such that T1 equals W over the norm of W, this family right here is an orthonormal basis on TPTM. Using this frame, we can get the values of the sectional curvature. Question, the sectional curvature, can it be constant? So the answer, if it is, then it must be 0. Wait, the formula number 2 here. We put 1 equals 0 and 3 equals 0. We get M is locally flat. So it's say the formula number 4 equals 0 and the formula number 5 equals 0. So the answer will be, if it is, then K must equal 0, M locally flat, and we should have this system here. I think we are certain that in Shiger-Gromov metric, the sectional curvature it's never be a constant. Honestly, I'm still working on the system. I hope I will find something different with this metric. So now we give the relation between the scalar curvature on MG and the scalar curvature on TM-GDS, which is given in the following theorem. And we can study some particular cases. I choose in here the case where M is locally flat, and we can notice that the scalar curvature in this case equals this equation. So can the scalar curvature be a constant? So if M equals 1, then it is the scalar curvature equals 0, and M equals 2, we need to study just part of the equation. The second part is the geodesics on the tangent band of TM with respect to GDS. So if we take XT smooth curve on G, then any curve CT which equal XTZT TM, we have C point equal the horizontal left of x point plus the vertical left of nabla x point z. This is important. For the proof, we can use dy point x equal h plus nabla xyv. Next, we try to give a necessary and sufficient condition for CT to be geodesic, and we found that CT is a geodesic curve if and only if the system A is verified. For the proof, we use the value of nabla DC C point, and of course, don't forget to replace C point by this formula right here. Okay. Now we can study some particular cases. For example, if we take the horizontal left, then which means that nabla x point z equals 0, have CT is a geodesic on TM GDS, and only if XT is geodesic on G. Second case, if we take CT equal XT x point t, which is called natural left of the vector, the curve xt, then xt is a geodesic on G. Xt is geodesic on MG. We have CT is geodesic on TM GDS. And notice that if we take a horizontal left curve CT, we have nabla x point z equals 0, and this gave us the value of zt, which equal in this case exponential to minus integral at dt multiplying k, where k in this case is a constant. This remark allow us to build several examples of geodesic curve over TM GDS. I choose one example to show you. So if we take m equal r, equate with the metric g equal exponential dx exponential x dx squared, then we have the gamma equal 1 over 2, and xt, the geodesic curve xt, taking the equation x double prime plus half of x prime to squared equals 0. And the solution of this equation equal a plus 2 ln bt plus c, here a, b, and c are real numbers. So we can construct a geodesic curve on TMCT by putting xt right here and zt right here. In the last part, we talk and we study the geodesics on the unit tangent bounded T1M. So what's T1M is an hypersurface on TM, which defined by the norm of WT squared equal 1. In this case, the unit normal vector to T1M is given by W over squared lambda V. So the connection on T1M equal the connection on TM minus this term right here. Well, this term is an orthogonal part of T1M and is also called the second fundamental form. In our case, this part equal rho W. So using this notation right here, we found that CT is a geodesic on T1 if and only if the system is verified. In here, rho is some function. So as natural question, can we determine this rho? Answer will be yes by using the following remark. We as we know, we have the norm of z squared equal 1. Then g z prime z equals 0 and g double prime z equals minus norm z prime squared. We obtain rho equal minus 1 plus b, which means is a constant. Therefore, rho is a constant. Now we try to characterize the geodesic curvatures on T1M. So we work on MG local symmetry. means that alpha r equals 0. So if we take CT geodesic curve on T1M, we have Z prime is parallel along the. Also, we have x2p is a constant. For the proof, of course, we derivate the norm x2p squared equal to gx plus 1 xp, and xp plus 1 equal rz z prime xp. Switching these two components right here, we found 0. Theorem, we prove that all the geodesic curvatures are of eta, of course. For the proof, we can use frame on along eta, and we use also the previous result on xp. That's right here. For perspective in the forthcoming works, we can characterize the harmonic and the biharmonic vector field with respect to GDS. Also, we can study some harmonicity of some canonical projections or inclusion of GDS. You can study also the geometry of this deformity geometric or any complex structure, for example, the Calarian. Here's some references that I use for this work. Thank you for attention. If you have any questions or comments, please let me know.
Okay, we thank the Professor Dija for her valuable presentation. If there is any question or comment, please use the question and answer button. Let me check. Okay, and there seems no question or comment.
Okay.
So we thank again to Professor Dija. Stop your screen sharing, please. Okay, dear participants, this is the end of my session. I would like to thank you for all contributing us. Next section will be started in a couple of minutes, I think 10 minutes later, and will be moderated by the Professor Figen Takılmutlu. Thank you again.
Good night, everyone. Welcome to this session. I am Figen Takılmutlu. I will moderate this session. Now, I kindly invite Professor Suman Sarkar from India to the presentation. The title of Professor Sarkar's talk is Analysis of Boundary Layer Flow over a Moving Plate in a Porous Medium. Professor Sarkar, can you hear me?
Yes, ma'am.
Yeah.
May I audible? Can you hear me?
Yes, we can hear you. Also, a little bit, your voice is high. Professor Sarkar, you are welcome to your presentation, please.
Okay, ma'am. Is it visible?
Yes, it's visible.
Good evening, everyone, and welcome to my presentation entitled on Analysis of Boundary Layer Flow over a Moving Plate in a Porous Media. Myself, Suman Sarkar, a senior research scholar at the Department of Mathematics, National Institute of Technology, Rourkela, India. The outline of my presentation will be following. Let's begin with introduction. And first of all, we will discuss about boundary.
Professor Sarkar, we cannot hear you.
Yes, ma'am. May I audible now?
Sorry, we can hardly hear you.
Sorry, ma'am. There is some problem. May I audible now?
Sorry, we can hardly hear you. Please raise your voice.
Everything is okay. Can you hear me, ma'am? Now?
Yes, we hardly hear you.
Can you hear me, ma'am?
It's perfect.
May I audible now?
Yes. Please, you can start in the first slide.
Ma'am, may I audible now? Hello?
Hello, we can hear you. Yes, please go on.
Okay. Let's begin with introduction. And first of all, we will talk about a brief of boundary layer problem, and then we discuss our main problem. After that, via literature survey, a few questions will arise, and that develops our research objectives and goals. First question arises in mind: what is boundary layer? A boundary layer refers to the layer of a fluid in the immediate vicinity of a bounding surface where the viscosity are significant. In fluid practical engineering, one of the biggest breakthrough is concept of boundary layer, and it was demonstrated by Ludwig Prandtl in 1904. Some examples of boundary layer are the atmospheric boundary layer is within 1 kilometer from the surface, and human boundary layer around human's body surface is given in picture. And in this, after Prandtl boundary layer theory, a numerous applications for boundary layer theory has been described by numerous researchers. In this problem, we consider viscous fluid flow past a rough plate through a porous medium. We consider a plate velocity is uw and free stream velocity is u infinity. According to the velocities, two types of boundary layer arise. and the schematic diagram of the boundary layer flow domain is given in figure A and figure B. And this type of moving plate problem first examined by Blasius, a former student of Prandtl. He considered the problem of fluid flow along a stationary plate. In contrast with Blasius, Sakiadis considered the fluid flow over a moving plate in a quinset fluid. Due to its industrial and practical applications in modern engineering applications such as metal and polymer extraction, crystal growing, and many others. This type of problem has been extended by various researchers by adding various physical phenomena such as magnetic field, porous media, non-Newtonian fluid behavior. Cortell combined both Blasius and Sakiadis problem by considering boundary layer flow for free stream passed along a moving plate. Fang et al. Consider the effects of slip boundary conditions over a moving plate. Bhattacharya et al. Describe the effects of slip flow over a stationary plate when the plate is embedded in a porous media. It is noticed that the governing equations with viscosity are known as Navier-Stokes equation, which are nonlinear coupled elliptic equations. This nonlinear partial differential equation can be reduced into a ordinary differential equation by choosing a suitable similarity variables. To understand the flow behavior, the reduced differential equations are solved numerically in absence of analytic solutions. And for numerical solutions, other researchers conjecture regarding this existence and uniqueness behavior of the solutions, and one can verify it mathematically. There are many general tools to verify this existence, uniqueness, analytic behavior. And Poulet, using topological shooting method, demonstrated the existence and uniqueness results in his paper. By above literature survey, our aim is to carry existence and uniqueness results of the resulting governing boundary problem along with numerical solutions. So we first consider a boundary problem. Our main objective, first consider a boundary problem, then we reduce the governing Navier-Stokes equation into nonlinear OD, then we discuss the analytical results, the existence and uniqueness results of the reduced differential equation. Next, numerical results, and discuss mathematical formulation. The mass and momentum conservation equations are given in equation 1 and 2. And the boundary condition at the wall is U equal to UW plus lambda star del U del Y. Here lambda star is for slip parameter. When lambda star equal to 0, the velocity at the wall is equal to plate velocity. Our UW is plate velocity, and far from wall, our velocity is equal to free stream velocity, that is U infinity, when our y tends to infinity. In this case, we consider the similarity variable in this form, where U is the summation of plate velocity and free stream velocity, and f zeta is one of the dimensionless stream function. Substituting 1, 2, 3, 4, substituting 5 in 1, 2, 3, 4, the governing equation 1, 2 reduces into equation 6, and the boundary condition 3, 4 reducing in 4, 5. So our aim is to discuss the existence and uniqueness results for the governing equation 6 with boundary condition 7 and 8. Here the governing parameters are gamma, and gamma is the ratio of U infinity by U, and U is the summation of U omega plus U infinity, and therefore clearly our gamma lies between 0 to 1, and our this omega is related to our porous medium, and it is always greater or equal to 0, and lambda is related to our slip parameter, and lambda is greater or equal to 0. So our aim for these governing parameter values, we want to prove the existence and uniqueness results of the solutions. To prove the existence results, we need to prove the following theorems. For any omega greater than 0, and gamma lies between 0 to 1 and lambda greater than 0, there exists at least a solution to the boundary value problem. And further, we also prove that the solution's first derivative is monotonic, and it is also decreasing if our gamma is less than 0.5 and increasing if gamma is greater than 0.5. We use topological shooting argument to prove the existent results. In topological shooting argument, we first transform our boundary value problem into initial value problem by considering f double dash 0 equal to alpha, and this is our initial condition where alpha is free variable. We can choose from anything, a real value. For any real value, there is a solution of initial value problem. Our governing equation 6 and this equation 9 has a solutions, and the solution is depend on and alpha also. Hence, the solution of initial value problem, IVP initial value problem, are denoted as f zeta alpha. And our aim, therefore, not all alpha will satisfy the boundary condition at infinity, that is f dash infinity equal to gamma. So our aim is to find at least one alpha star such that f dash infinity at infinity alpha star tends to gamma. This is our aim, is to find one alpha star, and this proof is divided into two cases when gamma lies between 0 to 0.5 and another case is 0.5 to 1. It is worth mentioning that the boundary value problem has a exact solutions at gamma equal to 0.5. Gamma equal to 0.5 means our free stream velocity and plate velocity are equal, and that time the exact solution will be f zeta equal to 0.5 zeta. And for this case, we first assume our solution's first derivative lies in gamma to 1, and in topological shooting argument we need to choose shooting domain. The parameter alpha is called shooting parameter, and we choose the shooting domain is minus infinity to 0, and considering two set x1 x2 in such a way such that solution does not lie into the set. And in this case we choose S1 is a collection of alpha such that f double dash corresponding solutions, so second derivative f double dash become 0 whenever or f dash greater than gamma, and in S2 is a collection of alpha such that f dash become gamma whenever f double dash greater than alpha less than 0. And using lemma 1, lemma 2, lemma 3, we basically prove that S1, S2 are both non-empty, open and disjoint set, and it is a subset of minus infinity to 0, and the minus infinity 0 is a connected set. So we cannot, S1 union S2 is a disconnected set using definition of disconnectedness. So S1 union S2 not equal to minus infinity to 0 is a symmetric diagram. Hence, there exists a alpha star which lies between minus infinity to 0, which neither alpha star neither in S1 nor in S2. Therefore, the corresponding solutions of alpha star will satisfy the properties f dash greater than gamma and our f double dash always less than 0 for any zeta greater than 0. Hence, from our main equation, it is easily proved that our f dash tends to gamma. This gives existing results for our boundary problem for this case. Now, in second case, it is also similar. In similar way, we can prove by considering these two set S3, S4, and using a similar argument, we can prove the results, existing results for the gamma when gamma is lie between 0.5 to 1. Now, for uniquely results, the following theorems will be proved. The theorem statement is the for any omega greater than 0 and gamma is lie between 0 to 1 and lambda less than 0, the solution of the boundary problem is unique. Unique means there exists only one alpha. We suppose, if not, we suppose there exists two alpha. One is alpha 1 and alpha 2. And the corresponding solution will be denoted as f1 and f2. And we satisfy all the previous boundary conditions with f1 double dash 0 equal to alpha 1 and f2 double dash 0 equal to alpha 2. This argument also partition into two cases, when gamma is less than 0.5 and when gamma is greater than 0.5. Now this is the outline of the proof. We in some consideration, there is a contradiction, we get a contradiction, and the contradiction is for that we consider there exists two alpha 1 alpha 2, but we have a contradiction, hence there exists only one alpha. And in similar argument for this case also, we get a contradiction, and hence the uniqueness theorem is proof for gamma when gamma is lying between 0 to 1. Now then, for different values of omega, lambda and gamma, the boundary problem are solved numerically. Table 1 represents the value of f double dash 0 for gamma, omega and lambda. In first part of the table contains when gamma is live, when our omega and lambda is 0, and we compare our results with Cottel's results, and it seems a good agreement, and we are confident enough for further computation. It is also noticed that f double dash 0 is negative when gamma is live between 0 to 0.5, and f double dash 0 is positive when gamma is live between 0.5 to 1. It is also noticed that when omega is increasing, the values of f double dash 0, the absolute value of f double dash 0 increasing, but opposite scenario has been seen when and that time the values of absolute value of f double dash 0 decreasing. For validation of our existing unique results, we plot f double dash 0 with respect to lambda and omega for gamma equal to 0.3 and 0.7. In both cases, it is observed that f double dash has a unique value. It is also worth mentioning that in figure A, it is noticed that for large value of lambda, the flow domain does not remarkably affect for permeability parameter omega. In figure 3, in all the pictures, the velocity profiles are plotted for the velocity ratio parameter gamma equal to 0.3, and it is observed that all the velocities are decreasing for increasing our parameter values omega, lambda, and in this case omega. And in figure 4 is plotted, velocity profiles are plotted in figure 4 for the ratio gamma equal to 0.7, and in all of the cases it is noticed that our velocity increases for increasing both the parameter values lambda and in this case omega. So summary of our work, the following significant outcome may be summarized based on present analysis. We first prove that the solution exists for our resulting nonlinear singular nonlinear boundary problem. We also observe that when plate velocity is greater than free stream velocity, then both the velocity profiles are decreases for increasing our slip parameters or porous medium parameter. Again, when plate velocity is less than free stream velocity, both the velocity profiles increases with increasing slip and permeability parameter. And we found an exact solutions when our plate velocity UW is equal to free stream velocity. And it is noticed that when lambda is large, that is larger value of slip parameter, the permeability parameter omega does not affect remarkably on the flow domain. And that is all. And this is my references. And is there any question?
Professor Sarkar, thank you for your valuable talk. Is there any questions or comments? If you have any questions, please write your questions in the answers and section question and answer sections, please. I think there is no questions and or comment. Thank you again, Professor Sarkar, for your contribution.
Thank you, ma'am.
Professor Sarkar, could you turn off your screen sharing?
Okay, ma'am.
Thank you.
Thank you, ma'am.
Now, dear participants, now I kindly invite Professor Gakar Sheikova from Kazakhstan to the presentation. The title of Professor Sheikova talk is Analytical Methods in the Theory of Nonlinear PDEs, Two-Dimensional Hirota Systems of Equations. Professor Sheikova?
Yes, do you hear me?
Yes, we can hear you. You are welcome to your presentation, please.
Thank you. So let's... So, do you see my presentation?
Yes, we can see.
Okay. Sounds is good?
Yes, it's good. Okay. Also.
Okay. Okay. Thank you. Good evening, dear organizers committee and participants. Today I would like to present my talk, Analytical Method and the Theory of Nonlinear Partial Differential Equations. Namely, I would like to say about two-dimensional Hirota system of equation. So this is research was prepared in the Department of General and Theoretical Physics in Eurasian National University country in Kazakhstan. So my outline of the talk, first I would like to say about this is equations, how look these equations. Also, I would like to say about reduction of the Hirota system. Also, because this system is integrable, I would like to show a Lax pair or second name like a Lax representation of the systems. And also, I would like to show how to find Darboux transformations and also exact solutions. And also, finally, I would like to say about conclusion and some open problems. This is my outline of today's talk. So, it is well known that nonlinear partial differential equation is generally applied to model nonlinear process in many domains of mathematical biology, chemistry, or physics. For example, one of the famous equations, it is one-dimensional Carteret-de-Vries equations. This equations is integrable, nonlinear, and also dispersive equation. This equation defines evolution of small amplitude dispersive waves that occur in the shallow water. Another example of famous nonlinear partial differential equation, it is nonlinear Schrödinger equations. This equation is universal model that describes the evolution of nonlinear wave in media with cubic nonlinearity. So, due to the interest of these problems, various analytical solution methods, like inverse scattering problem, Darboux transformation, Hirota method, and sine cosine method, and also hyperbolic Tann method, so were developed. So in our talk, we would like to say about the dimensional Hirota system of equations. So great interest in physics and mathematics is studying the nonlinear excitation of the spin models. So in these motivations, one of the author of this research, Murzakulov, and also Professor Lakshmanan and et al. Had been presented various integrable spin system in two dimension by proposing the interaction of spin field with vector potential or scalar potential. So their work was published in Work Symmetry in 1915. So in this work, researchers obtained Lax pairs and different interesting reduction in 1 and 2-dimensional. So two-dimensional Hirota system of equation has following form, which is given in equations 1 and 2, 3. So in this system, Q is x depends from independent variable x, y, t, is complex functions. V and omega are real functions, and delta plus minus 1. Alpha and beta, it's real constant. So why is this study of this equation is interesting or important? One of the reason it is the reduction of this Hirota system. So in this page, as we see, we present two cases of reductions. For example, if alpha equal 1 and beta equal 0, we can get two-dimensional nonlinear Schrödinger equations. Second case of if alpha equals 0, beta equal 1, we obtain the two-dimensional complex modified KdV equation. So it is means if you find solution for Hirota system for two-dimensional, then in some reductions, we can find also solution for two-dimensional Schrödinger equation or for two-dimensional complex modified KdV equations. So as I say, this equation is integrable. Integrable, it means we have one of the definition of integrability that the equation is have Lax pair or second name like Lax representation. So Lax, this system admits Lax pair, a corresponding Lax pair of equations 1 and 3 presented like 4 and 5. So A and B, this is matrices. Phi is Psi is vector eigenfunctions. So general form of the matrix A0, sigma 3, B0, B1 are given by this page. So the compatibility conditions of equation 4 and 5 is 6. So if you substitute matrix in the compatibility conditions, we can find two-dimensional Hirota system, system of equation 1 and 3. Also, equation 6 called like zero curvature conditions. So let's try Darboux transformation on this page. Firstly, we have to consider the transformation about linear function phi, which is presented by transformation 7, where C, a matrix S and I given in this page. So Darboux transformation 7, transform the original Lax pair 4 and 5 into a new Lax pair. So new function C1 satisfies equation 8 and 9, where A1 and B1 depend on Q1 and V1, omega 1 and lambda. So our goal to find Q1, V1 and omega 1, this is new solution which we'll find in this talk, which we'll present it in this talk. So in order to hold equations 8 and 9, the functions T must satisfy the system 10 and 11. So by substitution, the expression A1, B1, and A and B in T into equations 10 and 11 and collecting the different powers of lambda I of the equations 10, we obtain the following set of identities. So from 10, we can obtain equations system with equations like 12, 13, and 14. And also from 11, we can get 15, 16, and 17. So finally, after some calculation from system, so from previous system 12 and 17, we can obtain the first iterated Darboux transformation for two-dimensional Hirota system, like in this form. So, we have to find elements of C1 and C21 and C11. So in order to define explicit form of these elements, we assume that matrix S, this is multiplication of the matrix H and big lambda and inverse H. So after multiplication of the three matrix, we can find explicit forms of matrix S, and then this is form if we substitute in the this Darboux transformations, we can find finally form. We can find new solution and final forms of the Darboux transformation for Hirota system of equations, which is presented on 18, 19, and 20. So next step in the Darboux transformation, we have to find exact solutions. So having the explicit form of the Darboux transformation 18 and 20, we are ready to construct exact solution of two-dimensional Hirota system. So we assume trivial seed solution like Q, V, and omega equal 0. This seed solution we take usually we take when we want to find soliton solution. If you want to find solution like Rogge wave or periodic wave, we have to change or we have to take another seed solutions. So solving linear system for A5 under zero background, we can get following solutions, which 21 and 22. This is eigenfunctions. So explicit form eigenfunctions. So after after substitution eigenfunction in our Darboux transformation, we can find exact solution of the Hirota system of equations. On this page, we only show first iterations or another name like one-fold Darboux transformation. Of course, researchers can apply second iteration and so on. For example, if you want to find the two soliton solution, we have to do second iteration and use second fold. So in this figure, we present one of the picture of solution as it's given, as presented, solution like one soliton solutions. So shape of the same, velocity same, and duration of time. So in picture, we see graph on the t minus 2, t minus 0, and t1. So Q1 is a one soliton solution. This is bright soliton. So Lax pair of two-dimensional Hirota system is presented. Darboux transformation is constructed. So, which is open problems on this research. We would like to find other type of solutions, property for solutions, also conservation law. So there is a reference which we presented our research work. For example, in the first case, this is work where a two-dimensional Hirota system of equation is presented. Another work, this is our research team present our research in these journals. This is some reference. So thank you for attention.
Thank you for your presentation, Professor Sheikova. Is there any questions or comments? If you have any questions, please write your questions in the question and answer sections. It seems there is no questions. Thank you again for your contribution, Professor Sheikova.
Thank you.
Now, the next speaker is Mustafa Altın. Now, I kindly invite Professor Mustafa Altın from Turkey to the presentation. The title of his talk is Weighted Minimal Translation Surfaces According to Semisymmetric Connections in Euclidean and Minkowskian Three-Space with Density. Professor Altın?
Okay.
You are welcome to present your study, please.
Thank you. I am Mustafa Altın from Bingöl University, Turkey. Firstly, I would like to thank you, Symposium Organization Committee. I will start with weighted minimal translation surfaces according to semisymmetric connections in Euclidean and Minkowskian three-space big density. In this paper, we define and classify weighted minimal translation surfaces according to a kind of semisymmetric metric connection and a kind of semisymmetric non-metric connection in Euclidean three-space and Minkowski three-space with density EAZ. For partial X, partial Y, partial Z, the standard basis on Euclidean three-space. When Wang identified spatial semisymmetric metric connection and semisymmetric non-metric connection, this here, where G1 Euclidean metric. Are you hearing me?
Yes, we can hear you.
My screen. Burada donuyor hocam. Burada donmuş.
Dear Professor, are you hearing me?
I open it. 1 minute.
Okay, share your screen, please.
One, okay.
At the bottom, green button.
Okay.
Your presentation, selecting. And
Are you
full
hearing
screen,
me?
please. Full screen, please.
Okay.
Control L maybe is okay. View.
Okay.
Perfect. You can continue.
I am sorry. For the connection, semisymmetric metric connection of Euclidean three-space non-zero derivatives are given by here. For the semisymmetric non-metric connection, Euclidean three-space, the non-zero derivatives are given by here. Similarly, for the Minkowski space, semisymmetric metric connection here, semisymmetric non-metric connection here, where G2 Minkowski metric. For the semisymmetric metric connection, the non-zero derivatives are given by these. For the semisymmetric non-metric connection, the non-zero derivatives are given by Furthermore, manifolds with density or weighted manifold are very popular recently. In this context, first Gromov has introduced the notion of weighted mean curvature or p-mean curvature of an in-dimension hyperspace on a manifold with density Phi as this. Here, phi is density function and is unit normal vector field H mean curvature of hypersurface. In this study, we will divide three types of translation surfaces which are defined by type A or type B or type C. In this session, we classify the type A, type B, and type C translation surfaces with zero weighted mean curvature according to semisymmetric, metric, and semisymmetric non-metric connections in Euclidean tree space with density EAZ, where A is real number different zero. Firstly, we consider translation surface of type A in Euclidean tree space with density EAZ parameterized by this surface. For this surface, unit normal vector fields, first fundamental forms, and second fundamental forms, this here. Thus, the weighted mean curvature of translation surface of type A in Euclidean tree space with density EAZ is given by this equation. For HP is zero, we have this equation. Now we will solve 8. Firstly, let us assume 8 is minus 2. On this assumption, from 8 we get this equation. The left side of equation is a function of S, while the right hand side is function of T. Does there exist a constant C1 such that second derivative f this equation and second derivative C is here? For C1 is 0, we solve the equation 10 this like this, and C1 is not 0 like this. We can write following theorem. Weighted minimal translation surface of type A according to semisymmetric metric connection in Euclidean tree space with density E minus 2Z can be parameterized by this surface and or this surface. Now for E not equal minus 2. Here we have 4 cases. Cases 1, first and second derivatives of f and c and g are different from 0. If we make necessary calculation, we can see that we have no solution. Case 2, let us assume that second derivative f is different from 0 and second derivative c is 0. Second derivative g is 0. In this case, we have this function. Case 3. Let us assume that second derivative g is different from 0 and second derivative f is 0. In this case, we have this function. Case 4. Let us assume that second derivative g and f is 0. In this case, we have this is a contraction. So we have no solution in this case. So we have following theorem. The weighted minimal translation surface of type A according to semisymmetric metric connection in Euclidean 3 space with density EAZ. E is real number different minus 2 and 0 can be parameterized by this surface or this surface. Since we have no time, now we will give the similar theorems for translation surfaces of type B and type C. For type B, weighted minimal translation surfaces of type B according to semisymmetric metric connection in Euclidean 3 space with density E minus 2Z can be parameterized by this surface and this surface. And theorem, weighted minimal translation surface of type B according to semisymmetric metric connection in Euclidean 3 space with density EAZ. A is real number different minus 2 and 0 can be parameterized by these surfaces. For type C, weighted minimal translation surface type C according to semisymmetric metric connection in Euclidean 3 space with density EAZ will be the same type B. Now I want to show our theorems for translation surfaces according to semisymmetric non-metric connection in Euclidean 3 space with density EAZ. Weighted minimal translation surface of type A according to semisymmetric non-metric connection in Euclidean 3 space with density EAZ can be parameterized by this surface or this surface. For type B, weighted minimal translation surfaces of type B according to semisymmetric non-metric connection in Euclidean 3 space with density EAZ can be parameterized by these surfaces. For type B, for type C, weighted minimal translation surface type C according to semisymmetric non-metric connection in Euclidean with density EAZ will be the same type B. Now let me give the weighted minimal translation surfaces of type A, B, and C according to semisymmetric metric and semisymmetric non-metric connections in Minkowski 3 space with density EAZ. Weighted minimal translation surfaces of type A according to semisymmetric metric connection in Minkowski 3 space with density E to epsilon Z can be parameterized by these surfaces. Weighted minimal translation surface of type A according to semisymmetric metric connection in Minkowski 3 space with density EAZ. A is not 0 and 2 epsilon can be parameterized by these surfaces. For tip B, weighted minimal translation surface of tip B according to semisymmetric metric connection in Minkowski tree space with density A to epsilon z can be parameterized by these surfaces. The different A is not 0 and 2 epsilon. The theorem. Semisymmetric non-metric connection with density E AZ, tape A, for tape A in these surfaces. Semisymmetric non-metric connection EAZ for tip B, these surfaces. These are my reference. Thanks for your attention.
I would like to thank you, Professor Alton, for his valuable presentation. Is there any questions or comments? It seems there is no questions. Thank you, Professor, again for your contribution.
Thank you.
Now, I kindly invite Professor Yahya Rahrovi from Iran to the presentation. The title of his talk is Hybrid CAS and Block Pulse Functions for Numerical Solution of Fractional Population Growth Model. Professor Rahrovi, can you hear me? Professor Rahrovi? I think, yes.
Hello, Mr.
Professor Rahrovi.
Hello, Professor.
Share your screen, please. Professor Rahrovi, please, your screen sharing. Can you hear me, Professor Rahrovi?
I apologize. One moment. I am sorry due to this problem.
I think Professor Rahrovi cannot share your screen. Am I right?
Excuse me, Professor Sakil. Do I have audio and video? It's my sound and image.
Professor Rahrovi, please click on green button in the Zoom screen.
Do I have audio and video?
Yes. Just a moment, please. Yeah, yes, we allowed you to video.
Okay.
Professor Rahrovi,
Title hybrid.
please listen to me. You should share your screen by using Zoom screen, please. Open it. Zoom screen. We are hearing you and we are seeing you with video, but we couldn't see your presentation, please.
Okay.
Share your screen using the green button. Below the screen, yes.
Okay.
Full sharing, please. F5. Press F5.
Once?
From the keyboard, press F5. Do you understand me?
F5.
Yeah, F5 is okay. Thank you.
Okay.
Yes, thank you, Professor Yaşar. Professor
I
Rahrovi, you are welcome to present your study.
These programs. Title hybrid cast and block pulse functions for numerical solutions, fractional population growth model. Contents: abstract introduction, fractional integral, cast wavelets, block pulse functions, implementation of the method, error estimation, conclusion. Abstract: in the present paper, a computational technique is proposed to solve the fractional population growth model. For this purpose, the operational matrix of fractional integral was used for cosine and sine wavelets. The error estimation is provided. Finally, numerical solutions of presented model and comparisons with two other methods are presented to show the validity and efficiency of the technique. Introduction. For a long time, fractional calculations have improved their positions and efficiency in various fields of science such as mathematics, engineering and technology, biology, social science, and etc. For example, applications such as modeling of nonlinear earthquake oscillations, color vibrations, fluid dynamics, dynamic economics, signal processing, and so on can be mentioned. References 2 to 4.
Professor Rahrovi, can you hear me? I think he's having internet problem. We will wait a couple of minutes. Professor Rahrovi, can you hear me? Professor Rahrovi, please open your microphone. Professor Rahrovi, please open your microphone.
Okay.
Yes, we can hear you. Please share your screen. Professor Rahrovi, can you hear me?
Yes, yes.
Yes.
Screen share.
Please
problems.
click on green. Please click on green button in Zoom screen.
Okay.
We cannot hear you. Please share your screen by using green button or screen share in the Zoom button, Zoom screen.
Okay.
Yes, we can see. Also, please make it full screen by using F5. Thank you.
Therefore, with the increase of the domain of applications of fractional calculations, many techniques are presented for solving fractional differential equations, such as Adomian homotopy perturbation method and the Black-Pass functions methods, Haar and Lejeune wavelets. The combination of orthogonal functions such as Lejeune, Chebyshev, Cas wavelets, and others with Black-Pass functions is a useful technique for generating efficient approximation of function on L power 2 R. The main and useful advantage of using orthogonal bases is to turn the main problem into a system of algebraic equations. Therefore, it can be concluded that the method will simple has a high speed of calculation during executions. This can be done by limiting the extension of series in orthogonal base functions to obtain unknown solutions of the method under consideration by using operational matrix. Fractional integral, the Riemann-Liouville fractional integral I alpha of the order alpha greater than 0 on L1 several intervals 0b is defined the form below. Some of the most important properties of I alpha are as follows. I power 0 of x equal fx و Cas wavelets. In this section, we bring some of the required definitions of Cas wavelets. Then we obtain the function approximation using Cas wavelets and Black-Pass functions. Cas wavelets are defined as follows, where Cas index m is equal cosine 2mpt plus sine 2mpt. And in 0, 1, the compact support of Cas wavelets is as follows. Support sine index in MOT. Here we present the usable symbol and notation related to Cas wavelets as follows. Laplace functions. And M said all black box functions on interval 0, 1 is given by where important properties of black box functions include disjointness, orthogonality, and completeness. Function approximation by black box functions. Any function F elements of L2 interval 0, 1 is represented using the black box functions and above relation as follows. About T semi-equal summation Fi bit is equal transpose F b out T or equal transpose b out T F, where Fi this statement. Function approximation by Cas wavelets. The set of Cas wavelets forms an orthonormal basis for F blank L2 interval 0, 1. From the recent phrase, it can be concluded that its function fx determined on interval 0, 1 is extended by about T semi-equal summation this statement. Also C and psi are 2 power k 2m plus 1 time 1 column vectors as follows. Mathematical integral Cas wavelets can be extended with M' term of black box functions where this statement equal is established. Therefore, psi index M' of T is equal phi M' time M' P' of T, where phi index M' time M' is equal diagonal phi and is 0, phi and is index 1, and phi n for n, this statement where lambda is in point-wise product. Implementation of the method. Now we use Cas wavelets to solve the following fractional population growth model. Kappa the alpha u out t minus u out t plus u power 2 out t plus ut integrals 0 t u out t u out tau d tau is equal 0. U and this u cipher is equal u index 0. Alpha greater 0 smaller than 1, where the expression ut is the scale population of identical individuals at time t, and the coefficient kappa is equal C of AB, is a non-dimensional parameters. Let d alpha ut semi-equal transpose u psi t, where u is the unknown coefficient vector using the initial condition and above relation we achieve. Then u and u out t is equal semi-equal transpose a b index M' tau. The rest of the expressions are obtained in the same way. Finally, we obtain a system of algebraic equations as follows, which is a non-linear system of equations. By solving this system, the unknown vector u and then a are specified. The approximate solution to the desert problem is obtained in the form as u out t semi equal transpose a b index M' of t. Error estimation. We can check the accuracy of the approximate solution u out t semi-equal transpose A B M prime T of T. Error is equal absolute statement. Numerical examples of the population growth model have been solved in several articles 9 to 30. In this section, we use the Cas-Wavelets method to solve fractional population growth model. Case A. Firstly, we set U index 0 is equal 0.1. Alpha is equal 1, and solve the classical population growth model for different values of kappa, which is plotted in figure H. It is shown in figure 1 that for small values of kappa, the solution grows very fast. To this figure, alpha is equal 0.1, 0.2, alpha 0. Figure 8, the graph of numerical solution of the classical PGM with alpha is equal 1 for different value of kappa for case A. Case B, for the next attempt, we take U index 0 is equal 0.1, alpha is equal 1, 2, and solve the problem with different value of kappa. Figure 2 shows the graph of numerical solutions for this case. The graphs show that the population rate grows faster for small values of kappa. As kappa increases, the population growth rate decreases. Case C. In this case, we set U index 0 is equal 0.1, kappa is equal 0.2, and change alpha. The result is plotted in figure 3, which show that the solution increases faster as kappa decreases. Figure 1, figure 2, the graph of numerical solution of FPGM with alpha is equal 1/2 for different value of kappa for case B. Kappa alpha is constant 0.5, but with different value of kappa 0.1, 0.2, 0.3, 0.4, 0.5. Figure 3, the graph of numerical solution of FPGM with kappa is equal 0.2 for different values of alpha for case C. Conclusion. In the present article, we solved the FPGM by using Cas-Wavelets and Laplace function with collocations technique. Analysis of the solution behavior shows that it increased with considerable speed along the logistic curve and starts to decrease exponentially again after reaching the maximum point. When the order alpha reduces, then the critical time and domain of the solution reduces, whereas the exponential decay increases. For small values of kappa, the solution grows very fast, so the accuracy of the solutions in the first of the interval is not very good. Then